Hello.
Hello. Yes, Shashank, tell me.
Hello.
Hello, Shashank, tell me.
Yeah, are you getting my voice clear?
Yeah, yeah, it's clear. It's clear.
Let me check with my. Let me check by sharing my screen.
Yeah, yeah.
Uh, now you are able to get my screen.
Yes, yes, Shashank.
Okay. Okay. Then we will start by 9:30.
Yeah, yeah, 9:30, 9:30.
Okay.
Okay.
All set.
Yes. Shashank, meantime, can I share my screen?
Yes. 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 Please. Yes.
Okay.
Yes.
Yes. Yes. Hello, Shashank. Oh, sorry. Very sorry, yeah? Very sorry.
Time. The time proves that we have come a long way to get where we are today. Dayanand Sagar University, with the legacy of 6 decades, had contrived to the achievements today and is throwing light on the way forward. Our visionaries understood the need to learn and know, to do and grow, to twiddle and tweak, creating the best of the thinkers, creators, innovators, and inventors. In fact, we believe in achieving more than ever before, instilling the commitment to strive continuously to serve the national and global needs. There are challenges we can't ignore, but remember, we are of humankind, and every objective is achievable by setting our minds, and Dayanand Sagar molds you to achieve the objectives in an environment that enhances creativity and innovation. If we all embrace the spirit that there really is no limit, if we rise to this occasion and come together across nations, if we integrate and ideate, we can make the future great and live the dream. Our legacy of education takes its root from our founding father, late Sri Dayanand Sagar, a visionary, an educationist, a powerhouse of knowledge and a believer in transforming the world, besides a leader par excellence. The institution has contributed to educating the world for over 60 years, carefully building alumni of over 100,000, including accomplished professionals, sports personalities, celebrities spread across the globe. We stand strong as a top-rated university, having 4 campuses with 350 teaching staff, educating 4,400 students with pride-filled and powerful alumni network across the globe. Dedicated faculty members who work across disciplines, collaborating and lifting us as the top university in the world, empowering the rising generation and nurturing entrepreneurs. Dayanand Sagar University. Live the dream.
Shashank, shall we start? Hello. Shall we start, Shashank?
Sir, this is Kushbu. Am I audible?
Yeah, Kushbu, you're audible.
Okay,
Shall we
sir.
start, or we'll wait
Yes,
for
sir.
another for 2 minutes?
So we can start.
Okay. Because still a few participants have to log in. That's why I
Okay,
thought another
okay,
for
okay. I can wait. I can
we
wait.
can wait, no?
Yes, sir.
Yes. Thank you, ma'am. Kushbu, madam, we will start now. Hello.
Okay, sir.
Yeah, they will join anyway. We will start with the session. Okay. Good morning, one and all. Welcome to the day 4 of the International Skill Enhancement Program on Programming and Simulation Software. Today we have the session on Typhoon Hill. The Typhoon hardware in loop, HIL refers to that. So it gives me an immense pleasure in introducing today's two experts who are working in Typhoon Hill. So the first one is Madam Khushbu Purwar. She is working as an assistant technical manager, Quab's Infosystem Kanpur since August 2017. She is HIL specialist certificate. She has obtained HIL's specialist certificate from Typhoon Hill Incorporation, Novi Sad, Serbia. She is expertise in Python programming. She is also supporting the sales and technical sorry at Quabs. She has delivered lectures on hill simulation in various online courses. She is working as an engineer in calibration and instrumentation department at CIPET, Lucknow. Apart from the industrial experience, she is also an academician, and she has worked for 7 years as a lecturer in the Department of Electronics and Communication Engineering at Central Institute of Plastics Engineering and Technology, Lucknow. She has taught the subjects like basic electrical engineering, basic electronics engineering, electrical machines, and control system. She is instrumental in developing the engineering labs at the CIPET Lucknow, and she has one publication in the international conference and two in national conference. She has graduated from the Gautam Buddha Technical University, Lucknow, in the year 2010 with first class, and obtained electronics and communication engineering degree. And she is expertise in simulation, real-time simulation, and agile simulation, Python programming, and physical laboratory setup. Welcome you, madam.
Yes, sir. Good morning, sir. Thank you.
I'll also introduce the other resource person for both the session 1 and 2. He is Sudipto Poddar. He is working as a marketing and support engineer, Typhoon Hill, India. He has completed his bachelor's in electrical and electronics domain. He is a certified agile specialist with more than 3 years of experience in Typhoon Hill real-time simulator technology and its application. Provided the expert lectures at NIT Jamshedpur, NIT Arunachal Pradesh, NIT Meghalaya, MNIT Allahabad, NITTR Chandigarh, JSS Academy Noida, BIT Mesra, PES Mandya, Hindustan University Chennai, Anurag Institutions, Hyderabad, etc. He has published a paper on real-time simulation of a three-phase grid-connected converter with real and reactive power control under different grid fault conditions at International Conference on Emerging Trends for Smart Grid Automation and Industry 4.0 held at BIT Mesra. And he has many more in the pipeline to get published the papers. I welcome Sudipto Poddar also. Uh, with this brief note of the resource person, I request them to take over and start the session. Thank you, madam. Khushbu, madam, you can start.
Yeah, yes. Very good morning to Honorable Professor, faculties from academia, people from industries, and all the respected participants. First of all, I would like to thank the host team of Dayanand Sagar University and Mr. Prashant sir, who is responsible for International Skill Enhancement Program organized. organized. So this is a very exciting opportunity for me and my company to deliver you the skilling, fruitful technology from Typhoon Hill, GmbH, Switzerland, the technology which is with a specific focus on hardware and simulation. We are pleased to introduce you with our simulation software, virtual device, and real-time ingredients for electrical domain and and electronics of our electronics smart system with the current year and
Khushbu, madam, sorry to disturb you. You're not very clearly audible.
so now I have my
It's not clear, madam.
it's not clear.
Yeah.
Okay. So give me one. Now, sir, am I audible?
Yeah, it's clear now, madam. It's clear.
It's clear now? Okay. Okay, once again, I just wish you all a very good morning to Honorable Professor, faculty from academia, people from industry, and all the respected participants. First of all, I thank to the host team University Administration responsible for which is an exciting opportunity for me and my work to deliver the upskilling technology from Switzerland with a specific focus on hardware. We are pleased to introduce you to our special software, virtual device, and real-time indicators and microgrid for digital mobility, the flow of advanced renewable energy, solar, energy, and energy. Already, Prashant sir introduced me, so I just go ahead for today's session. These are the contents for today's session, which we are going to see. That is introduction of Typhoon Hill, in which we will go through the brief introduction of testing development stages. Then, what is Typhoon Hill technology? Typhoon Hill real-time simulator, software installation. If those are interested to use our software, we will tell the steps how to do. And Typhoon Hill virtual hill device software. We will explore the Typhoon Hill control center like waveform generator, script editor, test editor, so schematic editor, hill SCADA. And the second session taken by Mr. Day4 will be the continued session for this. So here we will be discussing that what is Typhoon Hill and what we are going to offer. And you can link us with us on Facebook, Twitter, and as well as on LinkedIn, WhatsApp. Day4 Incorporation is the market technology leader in the rapidly growing field of ultra high fidelity controller hardware simulation for power electronics, microgrids, and distribution networks. We provide industry proven integrated test solution along with the highest quality customer support. The company was founded in 2008, and since then it has been creating distinguished by ultimate ease of use, unrivaled performance, leading edge technology, and affordability. Thus bringing the products to fruition, meeting time to time market goals as well. So, there are number of engineers behind the success and leading Typhoon Hill to the top market position. But there are three important persons who needs to be mentioned. First person who came to our mind, that is Ray Startup. He is the president of the board, co-founder of Analog Devices, and in 1990 he was elected to the American Academy of Arts and Sciences. He has several awards. And Dushin Vinay, he is Chief Technical Officer, PhD in Computer Science at the University of Norway. And one of the most important person and the founder, that is Chief Executive Officer, board member, Nicola Fisher, who is PhD in Electrical Engineering. He was earlier control and instrumentation engineer at ABB, Switzerland. They developed the processor technology called Martha, and Day4 is based on this technology. is the most powerful footing person of this typhoon hill, and so is the name logo, that is elephant, that is a mammoth. It is also very powerful. And typhoon hill is also powerful. Typhoon, as the word indicates, that it is a powerful sign. It is a typhoon hill. So the logo and the name, as like him, as he is the most powerful. This. I am working in Quantum Info System, which is working office in Kanpur, and it was established in 1982 and has educational sales for last 15 years, and it is not more than that. It is latest in technology and best in quality. And Quantum Info System is the sole authorized distributor in India into education sales. Working lead and CEO of this quantum ecosystem is Mr. F. Siddiqui, who played measured role in introducing its Typhoon Hill first product in India after it was globally introduced in 2008. Our first Typhoon Hill 6 double knot successfully working at Amrita University in Kollam. Second Typhoon Hill 4 double knot, that is 400 at NIT Surat, Karnataka. And so on, the list is endless. But some of the most important are still mentioned, like IITs, IIMs, NITs, NIT, government and private universities and engineering colleges, centers, etc. And we are well best known for after sales, that is technical support and selfless services which we are providing to the Typhoon Hill users in India. For this, our team is very hardworking and is making it nourish and bringing to fruition day by day. These are the Typhoon Hill users in India, like IIT Kanpur, IIT Delhi, IIT Indore, IIT Bhubaneswar, IIT Dhanbad, NIT Srinagar, NIT Uttarakhand, NIT Patna, and so on. And some of the industries, GE Bangalore, Schneider Electric, Bangalore, NDTV, Bangalore, Honeywell, and many more to come soon in this, to be added in this list. This is our first microgrid test bed installed at IIT Kanpur in year 2018 under Indo-US program. So here we can see that we have used 3 Typhoon Hill 604 boxes. It is 8-core dedicated FPGA 604. This is the hardware real-time generator. We will discuss in our latest. We will see in our latest slide. And this is the 5 hill connects which we have used, and 1 Typhoon Hill measurement terminal. So measurement terminal is basically for monitoring HIL signals, and HIL connect is true plug and play interface. With HIL connect, controller will feel like interface to LEM sensors, relays, and contentry, whatever you can imagine. So this setup has the capability to simulate 24 3-level 3-phase converter with time step down 500 nanoseconds for 50 plus IEEE standard node or bus system with loads and source connected at time step down 10 minutes. Also, we have used 2 Typhoon Hill 402, 2 boxes of Typhoon Hill 402, that is 4-core dedicated FPGA. Second second product which we installed at NITTR Chandigarh. So it has also the same configurations like similar, only we have besides using 3 Typhoon 604 and 1 Typhoon Connect, we have used Relay Connect from ABB and one HTC HIL controller from AI. It is Austrian Institute of Technology, and this is simulation. Here we are connecting your actual relay with your simulation using the relay connect. So this has capability to simulate 23 level converter and step down 500 nanoseconds and 450 plus IEEE standards. Also, the measurement terminals are used for high current and high voltage measurement. So this is Typhoon 604, that is, and 6 series, also like 602 plus and 604, 8 for dedicated FPGA, along varying the interfacing and experimentation. So this is the additional smart grid controller, inbuilt communication control to exchange your data modbus, which we have additionally used in NITTR Chandigarh. These are some of the customers also as like we are the partner at more than 12 industries like Panda project funded by European Union here, and we are partners with the EPC Power, then Schneider Electric, Flagship, Freedom System Center, and some other like MIT, AIT, Elbron University, HL, ABB, Woodward, Lincoln, Laboratory, etc. These are our pioneer users. We are also providing consultation. Also, I would like to inform you that simulation with Typhoon Hill is free of cost for unlimited number of users, with lifetime free upgrades, and real-time simulation and control hardware load is on cost, with lifetime free update of firmware and software for unlimited users, along with its unique and proprietary features. Here we can see that these are the testing and development stages. Simulation, as we all know, that it is an approximate imitation of power operation of processes or system that represents its operation over time. It can be used for performance tuning or optimizing, safety engineering, testing, training, and education. And when we say that it is virtual, it means that it operates on the platform of integrated software and hardware components. Means that in this manner, system accepts input from the user, like physical controllers, and produce the output to the user in the form of a display form. So these are the stages. Like while simulation, we have limited accuracy and flexibility. And for real-time simulation, we are having flexibility much more than this. And for hardware-in-loop simulation, again the flexibility increases, and here it is actual controller testing. And in hardware testing, it is full accuracy and limited flexibility. That is, you cannot make much more changes. Cannot change. So that is, here it is, you are getting the limited flexibility. So we have to go through these previous stages. So in simulation, in virtual simulation, what we do that we first define the model That is what is our requirement. That is using the characteristic equation or parameters of the actual hardware. Then we do the computer modeling, and then we solve the differential equation of the terms and other mathematics of the controller together using the non-visual laptop. Here we have flexibility to work anywhere. We can go beyond or below the ratings, unlimited time, and then we have the flexibility to test anything without any physical damage. For example, like if we want like induction motor at 2 amperes starting current, and if we want to go up to 8 amperes, we can go. We have the flexibility that we can go to 8 amperes. But when you are, so this is the first stage which we are using before the hardware testing, because here this flexibility we are not going to get, which you can get here. So this is the virtual hill simulation, that is the application of real world processing time. Now, what is the need for real time simulation? It's a work side effect to a project. There is no example of this area. That if you want to add to the scope, you can add only that is to the scope. But if you want to go beyond 349, 549, 600, plus 1000, plus 200, but you cannot do mentally by sitting. If you have the large calculation, so what you will calculate for the large calculation, and that means you want to use and also set for that. So for that, we can execute at the same rate as actual raw clock time. So we say this real execution. Because there is the word difference is that after compilation, both plant and controller going to process by specific device for real execution. And in this, both plant and controller going to by different processes. Plant by one processor and working in real time, that is the same rate as the actual work clock time, and you are not using physical hardware. So here also you have the flexibility and cost efficient also.
Khushbu madam, Khushbu madam, madam, sorry to disturb you. There is lot of echo and voice is very low, madam. The participants are not able to hear, and it's breaking also. The voice is breaking. You can look at the chat window also. The people are, I mean, participants are dropping in a message.
Now this is clear.
Yeah, it's clear.
Okay. From
Madam, you are using two
hello.
different systems.
Yes, the system laptop for slides and mobile phone for audio right now.
Okay, then now this is
Laptop, I
better.
think voice was not so clear.
Yeah, now this is better. But to avoid the echo, you can just mute your system. This thing where you are presenting, no, that you can just mute it.
It's already muted, sir.
Muted. Okay, okay, okay.
Okay,
Yes, madam. You can continue.
okay. Should I once again go with the slide or
No,
go?
no, no. You can continue, madam. You can continue.
Okay.
Thank you.
So, okay, thank you, sir. So this is how the real-time situation is fruitful when we are able to execute at the same rate as actual wall clock time. So in this, both plant and controller are going to process by different processors. That is, plant by one processor and controller by another processor. So this increases its accuracy as well as here also we have the flexibility go for the changes. Now this is hardware in loop simulation. Here this is plant and this is the actual controller. A Typhoon will allow us to test real devices integrated with the digital system in real time from testing all imaginable operating processes through control system verification to automatic process. This HIL provides us with all the necessary features to be work done, like CHIL, that is controller hardware, that is when controller is actual, and rapid control typing, that is when plant is actual and controller is virtual. Then PHIL, that is when some part of the plant is actual and some part of the plant and controller is virtual. So this is how the hardware in loop simulation works. We will see in my slide that how it is working here with the development stages as well as the cost and fidelity. Let's see in first figure, that is this. Here cost is very less and fidelity is also in comparison to this is less. This is normal simulation. That is for this we need only simulation software. And this red rectangle means this figure covered by dotted red rectangle. It shows that it is using one single processor. It is using one single processor and we use only simulation software. So here cost is less and fidelity is also less. Accuracy and the desired things are less because it may take time because it is using one processor. But when we are switching towards the real-time simulation, here you can say that you are doing the long calculation to mind, means using one processor only. But here, if you are using the two different processors, see, the two red rectangles are red dotted rectangles, means we are using one processor for the plant and one processor for the controller. So this is real-time simulation, means here you are going to use simulation software as well as real-time simulator. Cost is bit increased as well as fidelity has also increased because we are using two processors. So fidelity, the achievement of getting accuracy and results has increased prior to this. And when we switch to controller hardware in loop, where our plant is distal, this is plant. So plant is distal, surrounded by red rectangle, and this is controller, which is surrounded by blue rectangle. So here our controller is actual. So we are using the actual controller and plant distal. So this is controller hardware in loop. Here cost has increased bit from this and fidelity has very much fidelity. That is, it has reached to, we can say, ultra high fidelity also. But ultra high fidelity you will get in full power test much more better than this. So here we are at high fidelity, means our achievements are achieved with less cost prior to these two, and some cost has increased prior to these simulation and real-time simulation when we are using our controller as actual. Coming to this power HIL, that is power hardware in loop, where we need simulation software plus real-time simulator as well as power amplifier in power HIL. Here some part of the plant and controller is actual. See, some part of the plant and controller is actual, and some part of the plant and controller is virtual, surrounded by the red rectangle. That is the virtual part. That is digital, and here some part of the plant and controller is actual. So here we have increased our cost as well as fidelity is high, somewhat similar to this controller hardware in loop. These results we are getting here also with high fidelity and here also with high fidelity. This is full power test where both are actual, means plant and controller both are actual. So here cost has increased very much and fidelity is bit increased with these two. We can say these two are of ultra high fidelity, and we can say that here we have achieved super ultra high fidelity. So these are the differences, that why we go with these stages to in order to make ourselves cost efficient as well as to escape from the physical damage while testing the things. So I think this must have given you the idea about this product development, that what we have kept in mind while doing this. So this is the Typhoon Hill technology. Here in this, generally what happens, like if we talk of general simulator, so simulator uses the technology based on two processors, that is based on Intel processor, and other one is FPGA, that is, so general simulators, I'm not talking about Typhoon Hill right now, I'm talking about the general simulators, like generally what other simulators use. They use technology based on Intel processor, that is CPU as main processor. They use CPUs as main processor and they use FPGA as secondary processor. So, but in Typhoon Hill technology, we are using FPGA as main processor and CPU as secondary. In FPGA also, there are two types that you can use. Like one is normal FPGA, that is, there is logical part provided, and for logical action like RTX, Fintex, Spartan, so you can use that FPGA. But if you are using FPGA SoC based, and we are using FPGA SoC based, that is to avoid the delay, to avoid the losses. Means here we are not going to get delay and losses. That is very less, and this is best. That is system on chip, which perform logical. That is ARM, that is advanced RISC machine, which is a family of reduced instruction set of computing architecture that is used for computer processor configured for various environment. So here we are using in our Typhoon Hill, that is ARM Cortex A9. We will go through this first, then we will come to this slide once again. So this is, we are using here in system architecture. In CPU, we are using ARM Cortex, that is A9 32-bit in user CPU. for HIL 402 and HIL 404. These both are 4-core dedicated FPGAs. So here we are using 32-bit 667 MHz, which is megahertz frequency, then 256 KB on-chip RAM, 96 MB external RAM. So this we are using, and this is ARM Cortex A9 is a multi-core processor providing up to 4 cache coherent cores used by our Tyson Hill technology. So this is the ARM which we are using, and in similarly for 602, that is 6-core dedicated FPGA, that is 602 plus, and 604, that is 8-core dedicated FPGA, that is ARM Cortex A9 32-bit 800 megahertz 256 KB on chip RAM, 96 MB external RAM, and for system CPU we are using microblaze. We are using microblaze soft CPU, that is, it is used for slow dynamics, we can say. So our user CPU, that is user CPU is using ARM, which are under direct user control, we can say. This is under direct user control, and system CPU, that is microblaze soft CPU. This is a microprocessor code designed for Xilinx field programmable gate array, that is FPGA. And as a soft core processor, microblaze is implemented entirely in the general purpose memory and logical fabric of Xilinx FPGAs. So here we have an ARM user CPU, that is execution rate up to 4, and here in microblaze system CPU we have execution rate up to 2. Here you can see that we have used FPGA as our main processor, whereas CPUs as our secondary processor. So FPGAs are fast. I will let you know that why we have used FPGAs as main processor and why CPUs as secondary processors. Now coming, okay. So here you can see that we are using system CPU. This is the system CPU which is used for slow dynamics, that is for handling the components of electrical domain like RMS value, single phase component, sources or power load. So microblaze is here we are using microblaze and in system CPU, and this is for handling the electrical components, slow dynamics electrical components. But we when talk of user CPU, so user CPU is used for to execute models composed of signal processing. Here we are using ARM based, where simulation step are of multiple of the base simulation steps. So it is for user defined and it can be used for direct, means it is under user, it is under direct control of the user, that you can use one or more general purpose processors for this, and here we have used the ARM processor. So this speeds up and this make us fast execute the things, this FPGA solver. Now here in this figure you can see that there are marked, this is green rectangle, and then it is here we have marked as blue rectangles. So here this components framed by the green rectangle are fully and partially simulated on a system CPU. These components framed by the green rectangle are fully or partially simulated on a system CPU, but components framed by the blue rectangle are simulated on a user CPU. So this is for this is under direct user control, and this is specific purpose, and we are using ARM for this. And all the other remaining elements These are simulated on Typhoon FPGA solver. We will talk about this FPGA solver, that what is FPGA solver in detail in later slides. So all these are elements are simulated on this FPGA solver. Now let us have a watch that why we are using FPGA as main processor in our Typhoon Hill technology and CPUs as secondary for FPGAs, because it has a series of logical blocks which can be modified and configured by the user, but instructions in a sequential manner. FPGAs are ideal for parallel systems where multiple tasks must be performed simultaneously, and they are electronically wired in the form of discrete programmable logic blocks which can be configured to suit the user's need. But CPUs are optimal for single process system where code needs to be executed in a sequential or linear manner. They lack in implementing parallelism. So this is again one of the major factors that these are ideal for parallel systems. So we are using FPGAs as our main processor. Regarding the flexibility also, that is FPGAs is that the entire hardware can be reprogrammed and reconfigured as the user is permitted to determine the logic of each block of the system. But CPUs have some limitation. They have a fixed set of instructions that must be adhered to by the programmer, and the program itself can be changed multiple times from bug fixes to complete change the program. But here you can entire hardware can be reprogrammed and reconfigured. So again gives us the flexibility when we are using this FPGA as our main processor. Execution speed is very fast when we are using FPGAs, because nothing can beat a piece of this hardware designed to this programmable logic function. Therefore, a well-defined FPGA will always execute faster than a software code which is running on general purpose CPU chip. For portability designs, CPUs are also easy to port to other CPUs, given the user that had a high level programming language such as C and C++ or Java, and FPGA code is written in VHDL languages that is very long, and it can be ported to other FPGA types fairly easily. CPUs are more complex rather than compared to FPGA. It is of blocks already being designed by the manufacturer, but FPGA is on the opposite side. It is just like a blank sheet. It is just like a blank sheet. You can configure, you can modify whatever you have designed in your mind. You can how complex the design needs. This makes them much more and less complex to understand, as well as to modify the needs according to your need. You can design in FPGA. So this again provides you the flexibility when you are working with complex models, which is not able to happen with CPUs much more easily, because it has fixed instruction, fixed set of internal blocks and processes so that are being designed by the manufacturer itself. Regarding the time critical process, FPGAs are capable of performing complex and time critical processing even in parallel and other critical processing tasks. That's why in Typhoon Hill we are having compilation time less than 1 minute, because we are using the fast processor, fast executing speed processor, that is FPGAs, whereas CPUs are usually limited in this regard because they are not ideally suited for critical time processing, especially if requirements cannot accommodate with its capability. But we cannot leave. We have to, when we use the combination of these two, both FPGAs and CPUs, these are the best ones. So we are using the combination for this combination of this CPUs and FPGA simulators are also using. But we are using FPGA as main processor and they are using CPUs as main processor. And here we are using FPGAs as main processor, which is making our compilation time, execution speed fast. So the combination of these two both, that is CPUs and FPGAs, these both have the together as a singular entity, and these are the efficient features which help us to incredibly work with lots of flexibility, and we can have the most of the things that we can handle, like part that handles the bulk of the data processing, mostly general computing, whereas FPGA logical blocks comes to play for specialized and custom tasks which can be configured according to the user needs. So that's why we have used the combination of these two, CPUs and FPGA. Now we are here, this is the FPGA solver basics, which here we have used that these part means rest of the Typhoon Hill part, which is components are handled by this Typhoon FPGA solver. This is a specialized proprietary multi-core based processor. This is optimized for time exact simulation for electrical models, and it can execute models with simulation step. So this is the detailed structure of FPGA solver that here, which we are using. So here the used a dedicated multi-core processor architecture implemented in FPGA fabric. Consequently, in order to understand the fundamentals behind modeling principles and constraints, therefore it is important to understand the FPGA. This is a basic building block of the circuit solver, and it is in charge of simulating electrical circuits consisting of linear passive elements, constant and time varying, and control blocks consisting of ideal switches, contacted based on ideal and non-ideal switches. So this SPC, that is the standard processing code, is a basic building block of the circuit solver, and here you can connect n number of SPCs in this block. We are using these are interconnected, these SPCs are interconnected through a dedicated communication lines, which allows them to exchange variables with a single simulation step delay. Whereas time varying and non-ideal switches, these are optional, which we do in SPCs. These are optionals, means they may not exist in all configuration. There are different configurations actually, like for 402 we can configure up to 6 configuration. So in different configuration, maybe these are available in configuration 3, may not be present in configuration 1, like that. So but these are the, so for these like time varying and non-ideal switches, so that's why that is said that this is optional. If you want to use this, then you have to switch the configuration for HIL boxes, whether you are using in virtual or in with the hardware. So you have to switch these configurations if you want to use the time varying and non-ideal switches. Now, signal generator. This signal generator, it is in charge of generating arbitrary waveform at the full-time simulation rate. It is mainly used for independent voltage and current sources. It employs linear interpolation in cases where waveform sample rate is lower than that the simulation rate, and the number of the signal generators channels also depend on the solver configuration. That how many number of signal generators you can use, that is also depend upon the configuration in which you are working for different HIL boxes. Somewhere it is 1, somewhere it is 2. Means according to your needs, you can switch to the configuration, and this number of signal generator channel depends upon the solver configuration. This is LUT, that is lookup table unit, is used to simulate behavior of non-linear elements. Non-linear elements like such as a PV panel, battery, and saturable transformer. So again, this number of lookup tables channel depends on the configuration, that which configuration you are working. According to your use, you can switch to the configuration and the number of LUT channels you can use. Machine solver. It emulates a single electrical machine modeling, including its electromagnetic part as well as mechanical part and speed measurement devices such as encoder and resolver. So this also depends on the solver configuration, that the configuration you are going to work. PWM modulator. This is a multi-channel triangular PWM modulator. It can be used both internally to drive internal converter models and externally through digital outputs. It runs on FPGA internal clock, that is typically 150 megahertz, and features a built-in dead time generator. So again, the number of this PWM channels depends on the solver configuration. So you have to go for the solver configurations that according to your need, that which configuration you are going to work. Like with 20 nanoseconds, also the plus point here, it is that with 20 nanoseconds PWM sampling time to 500 nanoseconds simulation time step. So this provides us this simulation with the 20 nanosecond PWM sampling time. This provides us ultra low latency that has set the industry standard for ultra high fidelity real time emulation. Latency also depends on the sampling uncertainty, like hardware characteristic, software settings, and model itself. So here you will find that it is very less time delay while using, as we are using 20 nanosecond sampling, PWM sampling time to 500 nanosecond simulation time step. So this is the concept of using the FPGA solver basics, and FPGA as main processor, as configurations are tailored for specific application domains, and they differ in number and size of computational elements. So this makes the unique feature of our system. Now coming to these are the Typhoon Hill products. Typhoon Hill products, that is Typhoon Hill simulators. We have 4 series and 6 series along with the M series. We have M series also. So here you are going to look, that is 4 series, that is 402, that is 4 core dedicated FPGA. 4 core dedicated FPGA, it has 4 3-phase 3-level converters, simulation time step down to 500 nanoseconds for 3-phase, and for 1-phase for Typhoon Hill 402, that is 4-core dedicated FPGA, you have 12 converters, simulation time step down to 500 nanoseconds for number of single-phase inverters, and for number of IEEE standard 3-phase buses, you have 80 plus buses, simulation time step down to 10 microseconds. Even the controller, that is ARM Cortex A9, that is the user CPU and microgrid system CPU, that is here it is used for Typhoon Hill 402, it is used for low level and high level controller simulation, as well as you have the multi-rate simulation also. Coming towards the Typhoon Hill 404, that is the 4-core dedicated FPGA, but it is the new Speedster. We will discuss that how it is different from this 402. See how it is different from 402 in various respects. Like Here we are using for 402, that is 4-core dedicated FPGA having Zinc 7 SoC based, but here we are using Zinc Ultra Scale SoC. And rest of the things for HIL 402 and HIL 404, like input output, that is 16 analog inputs for 402 and 16 analog, same input analog inputs for 404. 16 analog outputs for 402 and 16 analog outputs for 604, and 32 digital inputs for 402 and 32 digital inputs for 404 as well. Then 32 digital outputs, that is digital outputs for 402 and same as for 404. Only the processor difference is that here we are in 402 we are using Xilinx Zinc 7 SoC based, and here we are using Zinc Ultra Scale. Here we have the built-in scope for both, that is HIL 402 as well as for HIL 404. In this table, I have only mentioned the main differences for HIL 4 and HIL 402. Where the differences are there, that ones are mentioned in HIL 4 table, and where they are same, so these are kept common for both. When we look for the connectivity, that is here, HIL 402 can use one USB and one Ethernet, but here we are having the multiple connectivity. That is, you can use one USB, two Ethernet, then two CANs, then two RS-232, then two SFP, and then two GPIO. Then power, that is 12 volt 5 ampere adapter is available with HIL 402 as well as HIL 404. The housing same for both. These both are compatible with HIL DSP interface. Both are compatible with HIL DSP 180 interface. Both are compatible with HIL breakout board, HIL DSP interface. Now, here are some differences, like in HIL 402, we are able to simulate up to 500, simulate time step down to 500 nanoseconds with HIL 402. But with 404, it is also possible to simulate time step down to 200 nanoseconds. This is the plus point of 404. 402 can work as standalone. Means if we have 10 devices, then we are going to work standalone. We cannot cascade it. But in 404, you can cascade up to 4 multiple devices. With 404, you can cascade up to 4 multiple devices. Here you can see that you can connect up to 4 HIL devices in parallel, and you can have the communicate with any other real-time device. You have interfacing also you can do with the different connectivity like Ethernet, CAN, RS, R2, S32. This is the HIL 404. With 402, we can go up to configuration, that is 6 configuration. We can go up to 6 configurations, but for HIL 404, we can go up to 2 configurations. Here in 402, that is input output update rate. Input output update rate generally and resolution, that is 1 microsecond for all, for 4 series as well as 6 series. But 404 has one special feature, that here it is 0.5 microseconds, that it has the input output update rate is 0.5 microseconds. So this is the plus some advantages of 404. That is why we say that 404 is newest pedestal, and we can use 404 up to 2 configurations and 402 for 6 configurations. So according to the user need, we can switch to the series. Now coming to the 602 plus and 604, these are the 6 series devices. For 6 series devices, if we are talking about the 6 series devices, so here we can see as the figure of the box, you can see the difference, that here you are getting 2 connecting boards. And in each connecting board, you are having 3 rows available for analog and digital inputs for both, that you can use for the connectivity in all. But here in 602 plus, you can see that here are 2 And in 604, there are four interfacing boards, connectors with four connectors, 1, 2, 3, and 4. Here you can connect with 4. Means this is the flexibility you are getting with Typhoon Hill 604. That is 8 core dedicated FPGA. And 602 plus is 6 FPGA. Here you can 602 plus. Here a number of three-phase converters, that is you can have 6 three-phase 3-level converters, simulation time step down to 500 nanoseconds. Whereas in 604 you can have 8 three-phase 3-level converters, simulation time step down to 500 nanoseconds. Then for single phase you can have 18 converters, simulation time step down to 500 nanoseconds in Typhoon Hill 602 plus, and 24 converters, simulation time step down to 500 nanoseconds for 604, that is 8 core dedicated FPGA. Then number of IEEE buses, that is IEEE standard three-phase buses for 602 plus, that is 120 plus buses, simulation time step down to 10 microsecond. And for 604, the number of buses, that is 150 plus buses. Here it is 120 plus and here it is 150. And for controller, that is ARM controller, ARM Cortex A9, that is user CPU and microblade system CPU. The controller here for 602 plus, we are using for low level and high level controller simulation, and similar for the Typhoon Hill 604. And multi-rate simulation for all. So these are the basic technical general specifications for all 4 series and 6 series. Coming to this, the basic now the processor things, you can see the technical specification, that is in 602 plus we are using the processor Zen 7 SoC based, and 604 also Zen. Here the input and the output channels, analog input outputs, that is 16 analog input outputs for 602 plus, and for 604 we are going to get 32 analog inputs, then 64 analog outputs for 604, whereas in 602 it is 602 plus it is 32 analog outputs. Then 32 digital input outputs for HIL 602 plus, and 64 digital input outputs for HIL 602. Built-in scope is available in both. Here it is the connectivity, that how you can connect with USB, Ethernet, CAN, then R2S3, RS232, then PCLE, high-speed serial link, then time synchronization. This one is that for time synchronization, PPS and IRIGB you can use with 604. Power, it is also 110 and 110 to 240. Actually, it is power is based on international standards. Like in India, we can use up to 220 to 240, but in US we have for according to American standard, it is 110 volts. So that's why it has put the universal standards for all, that it can be used all over the world internationally. The housing you can see, and the compatibility, these are both are compatible with DSP interface, DSP 180 interface, and breakout board, and HIL DSP interface. This is the M series. In M series, we are talking about this now microgrid test bed. So in microgrid test bed, it is a collection of HIL devices with integrated protection relays with microgrid controllers, solar inverters, battery inverters, diesel gensets, and fuel cell. Here you can see that these are here we have used 2 boxes, that is HIL 602 plus, and other one is also HIL 602 plus, as here we can use 6 series in for this particular microgrid test bed. So one HIL 602 plus, here you can see that with the partition it is showing. So 602 plus has 2 connectors available, and other HIL 602 plus box, that is 2 connectors available. This one is battery energy storage system, that is battery energy storage inverter controller. This one is solar inverter controller that is used for PV wind application for renewable energy resources. Then this one is a relay connect designed by SEL. These are the two relays. You can see this is the relays designed by ABB, and diesel genset, that is easy gen 3000. It is the name of diesel genset. Where it is? Yeah, here. It is a diesel genset controller from Woodward, as Woodward is a pioneer in diesel genset controller development. So this is the microgrid test bed. The main purpose of this microgrid test bed is to comprehensively test and validate primary and secondary control, communication and protection under all operating conditions, including faults in both the islanded and grid tied mode, Moreover, this testbed can perform all its tests and generate its test reports in fully automatic mode, and then thus boosting the productivity and improving test coverage even further, because it has very important parameter, that is it is using multi HIL system architecture parameters. I would like to quote some of the important things regarding this, like maximum number of devices in chain you can use for 602 plus is 4, and for 604 it is 16, and for 404 it is 4. Means maximum number of devices in chain you can use for 602 plus 4, and for 604 you can use up to 16, and for 404 you can use up to 4. Maximum number of electrical variables, that is one SPC can send to and receive from SPCs in other devices, that is electrical variables between two devices are sent through device coupling elements depending upon the type of the coupling elements and the number of variables. So there are a number of variables like that SPCs are sending to each other. Like for single phase device coupling, that is one variable. Then for variable double phase device coupling, there are two variables. Then for three phase device coupling, there are three variables. And for four phase device coupling, there are four variables. So for 602 plus, we can go up to 8. Means it is possible to connect to one SPC to other devices with maximally two four phase coupling devices with 602 plus, and 8 similarly 8 for 604, and similarly 8 for 404. That is, we are able to connect, it is possible to connect one SPC to other devices with maximally two 4-phase coupling devices, and that is total number, maximum number of electrical variables that we can connect, that is 8 in 602 plus, 604 and 404. Coming towards the maximum number of electrical variables that one device can send. The previous point which I discussed, that was regarding the SPC, that is the standard processing port. So that was 8. But when we are talking about one device can send to and receive from other devices, that is two independently previous constraint. So it is means independently previous constraint. It is possible to transfer up to 16 electrical variables from a part of the model design to one HIL device to other parts of the model. This restriction is made because of transferring capacity of HIL devices. So it is 16 for 602 plus, 604 and 404. So maximum number of electrical variables, that is 16, that one device can send to and receive from other devices. Maximum number of signal processing variable per stream, that is signal processing variables, these are also 16 for number is 16 for 602 plus, 604 as well as 604 and this 404, that is 16. That is signal processing variables means these are transferred between devices using the component device transition. Means each device transition component define one stream. define one stream. So this restriction simply means that you are allowed to transfer up to 16 signal processing variables through one device transition. Then there are also we have the flexibility, that is we can have a maximum number of signal processing stream between two devices in each direction. In each direction means independently previous constraint, there is also a constraint of maximum number of device, means transition component between two devices. For example, you can connect two HIL 404 devices with maximum 4 streams, every of it with maximum number of 16 signal processing variables. And for 602 plus and 604, you can have 16 streams for this. Then simulation time synchronization is available with 602 plus also, 604 and 404 also. Means all the parallelized HIL devices are synchronized with master HIL, that is one with the device ID 0. Coming to the device ID, like I would like to say that it is, I am saying that is one with the device ID 0. Actually, here our counting starts from 0. Like if we are connected to three persons, then three devices, then we will say device ID 0, device ID 1, device ID 2. For similarly, for one device ID, we will say that is device ID is 0. If we are connected with one device, then device ID will show 0. And if we are connected with two, then device ID will show device ID 0, device ID 1. Similarly, for 3, it will show device ID 0, device ID 1, device ID 2. For 4, device ID 0, device ID 1, device ID 2, device ID 3. So this is how here we are counting the device IDs. Here the counting starts from 0, not from 1. So these were the special features of this microgrid test bed, and one of such laboratory set up at Massachusetts Institute of Technology, that is Lincoln Laboratory. Here we have here microgrid controller design and testing was done, and the link is also provided. You can see, and here we have provided. It is modeled with the diesel genset, then solar plant, battery ACs, relays, then your solar inverter controller, and 2 to 4 microseconds multi-rate simulation time step. Then HIL setup, it is 4 HIL 6 series devices, and protocol, that is Modbus, TCP and UDP for data logging. We have used. Now, these are the means for available for what we, this is the just a general portfolio overview for Typhoon Hill products, that is virtual hill 4 series, 6 series and M series. For Typhoon Hill tool chain, it is available in all, that is virtual hill 4 series, 6 series as well as in M series. Then paralleling of HIL devices, you cannot because HIL devices, that is hardware in loop devices, in virtual it's not possible, but it is possible with 4 series, that also with 404, not with 402, because in 402 we cannot cascade, but in 404 we can cascade. So in 404 4 series it is here, and then in 6 series, then in M series also. Then HIL processor, in HIL processor, like for virtual hill, you have to use PC, and for here, you have to use the devices. And then Typhoon HIL cores means up to 4 cores you can use for 4 series, up to 8 cores you can use for 6 series. Like for if you are using 602 plus, then up to 6 cores, up to 6 cores you can use. This is the maximum number written. And for 604, you can use up to 8. And for M series, it is up to 80. Then signal processing and communication processors, we are using PC for virtual hill. ARM means ARM you can use up to 2 for 4 series and 6 series, and you can use ARM up to 20 in M series. Then we have the high speed input output, that is the analog input. We are going to have in 4 series, that is 16, then in 6 series up to 64, and up to M series it is 640. Analog output, that is 16 for 4 series and up to 64 for 6 series. and up to 644 M series. Then digital input output for 4 series it is 32. Digital input output maximum number that is in 6 series up to 64 and in M series it is up to 640. These are the communication protocols, that is Ethernet, IP connectivity you can have with virtual hill and 4 series, 6 series and M series. Then Modbus is available with 4 series, 6 series and M series. Then IEC 615850, this is possible only with 6 series and M series. Then Sunspec only possible with 6 series and M series not possible with 4 series. Maximum grid size, it is up to 80 nodes for 4 series and up to 160 nodes for 6 series, and it is up to 1600 nodes for M series. M series means microgrid series. Here we are having the interfacing board, that HIL connect, that is true plug and play interface, means it gives you the feel that you are directly connected to the HIL emulator, means you directly interface your controller to the HIL emulator. And custom connectors, then input output levels and power supplies. So Typhoon Hill Connect interface system enables seamlessly interfacing of any power electronics system controller system to the Typhoon Hill family of real-time emulators. Its modular signal conditioning architecture enables our engineers to rapidly customize it to match your industrial controller and interfaces such as current sensors, voltage sensors, fiber optic transceivers, contactors, and temperature sensors. Breakout board, these are wiring by wiring. Like for simple, as we do in breadboard, for when we are designing something on breadboard, so what we do it wiring by wiring. The same thing here also we do in breakout board. That is connections we do by wiring by wiring. Then in launch pad interface board and DSP interface board, the launchpad interface board is also a kind of a controller. It is the way to those who want to accelerate the development of power electronics applications for Texas Instrument families of DSPs, DSP interface and launchpad interface. They can emulate the power stages of a P device that include power converters, electrical machinery, filters, electrical grade PV cells, passive elements with 1 microsecond overall time resolution. In this way, users can develop immediately, test their control applications without worrying about much safety measures required in the power laboratory environment. So here the DSP interface which we use, that is TIDIM 100, that is DSP card. And here you can, it is available with DIM 180 available with the converter card, means it can interface up to 1 card. DSP interface can interface up to 1 card. When we talk for microgrid DSP interface, the DSP interfacing is similar. That is, you can emulate power stages of the devices. But here in microgrid DSP interface, you can use DIM 100 socket for TI control cards, and it answers to the increasing demand of microgrid development tools using the Texas families of DSP, and here you can interface up to 3 cards. This is the difference between microgrid DSP interface and DSP. Here you can interface up to 1 card, here you can interface up to 3 cards. Here it is simulation, then it is the automation property of the Typhoon Hill. We are using FPGA as the main processor, and in Typhoon Hill, like you have done your schematic part in your while simulation and model, and then you have compiled. You can compile and directly load model to the Hill SCADA, that compilation time is less than 1 minute, because we are using FPGAs as our main processor, so it saves time, and number of steps are reduced, because this code generation, like in other simulation, you have to do the code generation manually, but here with automatic code generation is possible in Typhoon Hill process. Means automatic code compilation, it will compile one by one, and you can get the messages in message console also in compilation, that electrical part or C code part. Here in compilation part, it shows all the things. So the code generation is automatic, that is handled by the Typhoon Hill process. And the language which is embedded, that is Python language is embedded with Typhoon Hill. We will see later. And you can directly, here you need not to go for the calculation, long calculations for the code generation. So directly it is compiled, and you can directly go for the real time simulation, directly connect your real time simulation. There is no difference. Our virtual hill device gives you the feel that you are connected with real time. So there is no need of worrying of the that you will be facing any problem while connecting with the real time or for the code generation. So here it has simple the things, reduce step. We have built-in blocks available, that you need not to model or model the block for each small components, like inverter and rectifier. These are built-in, and code compilation is done by this Typhoon Hill process itself. This is the controller hardware in loop example, that this is the plant is digital, you can see, and we have used the actual controller, and this is the hardware box, how we connect it. Digital plant you can see. So this digital plant is giving you the feel in virtual mode, that is it is real. You can directly connect to without any hesitation to the HIL box, and it is compatible with actual controller also. So this is an example of controller hardware in loop, where plant is digital and controller is actual. This is a case study for where we have this is inner drive testing distribution and transformer. So these are the comments from the user, that is Typhoon Hill emulator with OEM controller makes an ideal development environment which combines real control signals in real time with real hardware, which is easy to operate as a software simulation package. So HIL must have for every power electronics engineer. These are the comments from Andreas Dietrich, Anadrive CEO. So in this, you can see that is, I cannot enlarge much, but if you can see this is a laboratory setup. And these are the results which we have obtained from this laboratory setup. Here it is control cabinet, then converter cabinet, then filter cabinet, and here we are using 700 kVA transformer, and these are the results which they got from this laboratory setup, that is full power test. These are the results. When they used our HIL 400 base setup, we replaced all these parts. These parts means converter cabinet and filter cabinet with our HIL box. Only we kept controller part, that is controller cabinet, as actual, and they are getting these results. Means this is the full power test, and this is only we have used, that is controller as actual and keeping the plant other things as digital. The results are same. There is no difference in result. So this is very cost efficient, and fidelity is also same. The fidelity which we are getting here in laboratory setup, the same fidelity we are able to get in by using our HIL box. So it is one example for the case, one example of the case study which we have done. where they have used 700 kV VSI used for transformer testing. This is the laboratory setup, and this one is HIL using the HIL box. The results are same. So here they have reduced their cost. Their cost was very high. So these are the appreciation comments which we got from Andes Dietrich in a drive. That these it is and it must. This is the comparative comparison. I'm not here to preach that which one is better. I'm not here to preach that which one is better, but still to to show our technology much more fruitful, we have to take some points which we need to compare with other platforms like software and hardware integration. We have vertically integrated because we are providing software and hardware from both from Typhoon Hill. You need not to go for the third party software, and that's why it is said to be one stop shop. Means here you are going to get hardware also, software also, as well as full technical support. Even if you're working, if you're using virtual simulation in Typhoon Hell environment, or either you are using hardware, even after the sales, we are providing you the full technical support. You need not to go to the different vendors. You are compatible with us at one stop, one shop. Everything is available here. So here it is full compatibility you are getting. It is complete compatibility with the versions that you have. Different versions, all the versions available, like oldest versions also and latest version. You can use according to your the system requirements and other things. And but in other platforms, the compatibility with selected versions are not available. Here the model compilation time is less than 1 minute, but here the model compilation time is more than 15 minutes. Reason that we are using the FPGA as main processor and CPUs as secondary processor for slow dynamics. And the other platforms, they are using CPU as main processor and FPGA as a secondary processor. So our processor utilization is maximum, dedicated and compiler, model libraries and firmware configuration. Regarding the firmware configuration, I would like to tell you that in our Typhoon Hill, as you will get the software update, along with that you will get the firmware updates too. Means your firmware configurations will be also updated. It will not take much or less time. Like in other platforms, your software is updated first and firmware is updated. It is taking months to get updated. But with our Typhoon Hill, you will get instant firmware updates. Here your simulation time step is 500 nanoseconds, and here in other platforms your simulation time step is 10 plus microseconds. Here we are using with the PWM sampling, it is digital sampling, that is 20 nanoseconds. In other platforms it is 100 plus nanoseconds. And here you are getting a ease of use due to the embedded HIL with Python. But here there are multiple vendors and multiple tool chains, and there are different support teams for every tool. But here you are going to get it one stop, one shop. Even if you're for your query, you can book a ticket. There is option available, that is hill.support@fox.com. You can book a ticket for your any query. Means you need not to fetch or talk to anybody. You can just book a ticket regarding a query, and your query will be resolved through that ticket system. So that's why we said that it is vertically integrated and one stop, one shop. Here you have these vertically integrated solution we have already seen, and the graphic modeling and custom test interfaces, automation with Python pre-certification. For this beautiful features, we need to explore some of the Typhoon. We need to explore the Typhoon Hill Control Center, which is gives you the very beautiful environment for the testing. Here the pre-certification, it is pre-certification means regarding to means like you, if you have designed some plant and you need to get certified from means so here it is pre-certified with some international standard systems of testing, and from with you can pre-certify it. So this is the meaning of pre-certification. Here we can go through ahead. This is the Typhoon Hill Control Center. This green icon shows when you have the software update. So when you have the software update, it will show like this, that software update is available, and when you will click this, then you will get the information that this is software update. So here you can have lifetime free updates for unlimited users, lifetime free firmware update, and lifetime free firmware update, lifetime free support for unlimited users, lifetime free update for unlimited users. So this green icon shows when there is any software update. This help icon, it is you can use this help icon when you are connected online. Documentation hub, in documentation hub you will get lots of things, lots of theoretical material, even you can get the technical notes if you are using those things for your thesis or dissertation. You can use them for that purpose also. So documentation hub is given so that for each and every component you can explore it in the documentation hub. Okay, so this is a schematic editor. In schematic editor we will, in schematic editor what we do, we design the model, means this Typhoon Hill schematic editor. It is designed to support a number of components that can be used as building blocks to model car electronics and car system. This section describes the general properties of the component library. Library in schematic editor, and provides a list of main types of components available in it. Like for example, I'll quote some library components like passive elements, then sources, measurements, and here you can for the go for inbuilt blocks of converters and test suite, then machines, transformer. Test suite we will discuss differently also, as it is a special feature of Typhoon Hill, and it is also responsible for pre-certification. So in a schematic editor, you can go for the test suite, converters, machines, transformers, transmission lines, then contactors, circuit breakers, circuit partitioning elements. You will all see in schematic editor in our second session. So signal processing components and microgrid. Here I am just giving you the brief picture of the schematic editor of the Typhoon Hill. Then you have also component additional information regarding signal in schematic editor itself, that is signal streaming, C function, advanced C function, then PWM modulator, Modbus device, then Ethernet variable exchange, then Sunspec Modbus device, IEC61850 Goose Code protocol, CAN Open protocol, OPC UA server, then IEC61850 sample value, then DTB detection, serial time synchronization, providing all the absolute machine encoded position for over a standardized protocol, importing power losses data. So this is one of the essential tool. Schematic editor is one of the essential tool within the Typhoon Hill software tool chain, designed to help you program your test equipment graphically. Simply you can draw your power circuits and distribution networks together with the control logic, and deploy them in less than 1 minute with a state-of-the-art embedded compiler from single converter application. Even from single converter applications and basic controller prototypes to multi-layer distribution networks, schematic editor will help virtualize your power system with ease. So it is designed to a single windowed environment for modeling tasks. All selected toolboxes and user-specific libraries are seamlessly integrated across the tool chain, leaving user experience. So it all just works. This is how it just works. Now this is Hill SCADA. In Hill SCADA, it is used to initially control the means here you can control and monitor your things, which is initially control and reconfigure your HIL test bed on the fly. Means you can visualize the results, you can build test procedures while Python programmable action buttons in a script editor. It is available, and simply drag and drop a wide range of UI interface elements to create your own interface for all the interface interactions with HIL test bed. You can freely arrange every UI element in HIL SCADA, resize it and program it. You can enjoy a complete, means here you are having a complete freedom that how you can monitor your simulation without stopping the simulation. This is the plus point. While running simulation, you can enjoy the complete freedom of monitoring and controlling. So there are several widgets are also available for SCADA, like action widgets, macro widgets, button, text box. These are the widgets which you will find in the HIL library when you will be open. If when you will open, then you will get these of the widgets in HIL-SCADA, and visual also, like group, sub-panel, text node. Then you have the monitoring. In monitoring, you have gaze, digital display, trace graph, XY graph. Means you can have TV monitor connection. Means everything you can do on this. When you have designed this panel to panel, you will get the feel that you are sitting in front of the actual panels. You are sitting in a physical laboratory, and you can control each and every parameters of the uh, of your design model. Similarly, you can also customize all the monitoring while using the different widgets, like for action, like for example, I would just that you can configure your HIL test bed on the fly with action widgets. You can turn loads on or off, change voltages, insert harmonics, trigger various islanding conditions, observe and record the response of the device under test in real time. You can means in short you can have you can throw a light of lifetime of standard and emergency situations at your device in just couple of clicks on HIL SCADA buttons. So you can enjoy full test automation because every action widget is fully programmable via Typhoon Hill API, and you can use both global and macro specific variables. So these are the features. Now coming, these waveform generator is the additional feature of this Typhoon Hill Control Center. So coming to the waveform generator, in waveform generator you can import IV data format in .csv, and you can generate IV and PV curve in waveform generator. And what else you can do in waveform generator? Waveform generator consists of two parts, that is PV file generator. In PV file generator, you can import IV data and generate IV and PV curve. And in source file generator, you can generate voltage and current source waveforms. I will show that in source file. Yeah, this is source file generator. In source file generator, it is used for generating various types of signals which the user can change at the point level. Means you can custom these signals. These are also the options for importing signal data from MATLAB or .mat or .csv files and exporting current plotted signals to the same data. You can include spikes and other things, spikes, swells, harmonics, and multiple events in your source. You can change time step by using the command toolbar. The command toolbars are given. From here you can insert the changes and command toolbar, and you can plot area. So here the user can directly manipulate signal data on the point level by selecting points, moving one or multiplying selected points. And it also contains commands for different um, on an appropriate plot mode. Means user can activate zoom on the selection modes. If you want to see, you can have the flexibility of zoom this and you can see this. So, so this is the source file generator that you can do in source file generator. Then in PV file generator, you can generate and import. Coming to previous slide, yeah, this is PV file generator. Here, this is the PV file generator. Like if you have some parameters, these are the PV file generator parameters. Like if you have some parameters, like if you have purchased this PV panel and if you have the specifications available from the manufacturer, then you can just fill these details here and you can go. Here it is the flexibility to change the temperature with the standard temperature, that is 25 degrees centigrade, and irradiance, that is 1000, up to 1000 you can have. You can generate the PV curve for this. And here you are having the temperature radiance where it is on cursor. Yeah. So here it is for open circuit, then for this is FFU, then CV, then CR. These are some of the data which you can insert. And here, if you are not having this data from the manufacturer, from here you can change and you can use the EN compatible that 550 code, and from there these are the standard data where you can code this. From here you can change this if you are not having the data. If you are not having the data, you can directly change this. Okay. So this is how you can do in PV file generator. Like for VOC, if you want to change, you can change it. Then you can select your model, and for selecting the model, here you can browse, and here you can EN50530 compatible. You can select this, and then you will get the automatic things. If you are not provided with the technology settings from the manufacturer, then here you can change that. And you can get the preview from here. From here you can get the preview of the graph, that what you are getting. The important thing to note that it is when you are changing FFU, FFU, that is this, FFU, that is maximum power point to open circuit voltage ratio, and FFI, that is maximum power point to short circuit ratio parameters yourself. You have to change the technology depending on the correction factors. These are the correction factors. This is CV, CER, then CG. These are the correction factors, as well as in order to get the adequate results. So these values are experimentally found for each technology and are ready to get for CSI and thin film waveform generator. So this is the most important point that to be kept in mind, that what you have to do the changes. Rest you will, when you will be exploring the software, you will get to know very well, much more better. And if you find any problem, you can contact us individually also. Now coming to the script editor part. In script editor, there are 3 window panes. 3 window panes means this one is the main window where we write the program. Here it is a simple program of Bode plot. So here we have used the Python language. It is written, it is embedded Python 3. And then when you have finished the program, then you have to click on the run. This is the run button. You can click, and then a separate window will pop up to show you the graph for Bode plot. This is the script editor main window. In script editor main window, a minimalistic text editor for writing, and you can edit with using the Python scripts. And this one is the console window. Second is the console pane, you can see. Here, sample means it is a simple console pane that will display the output from the user Python script. When you have to run the program, then the result will be displayed here. Here, the graph has to be plotted, so there it is separate window has pop up. So this is the separate window pop up, and here you will get the results. I'll show you. Like this is a simple area of program of area of circle I have written here. So when I have means I have run the program, you can also try. So you can put the value when I have put the value of R as 5, then I have got the result, the 78.5. This is you will get in console pane. This is a simple example to explain you easily, and when you will model, then there you will get. This is the API wizard, API window pane. In API wizard pane, this pane allows the user to easily and quickly insert appropriate HIL API functions. The API wizard pane interface is dynamically generated based on the loaded model. So if this window does not appear, you can just click on the view button and you can just enable the API wizard window pane, and here you can get this. So in API wizard window pane, like for this, like if I want to put the condition for this software control, like this is switches, bottom and top switches. So from here I can directly insert, and the code is directly inserted here. For putting the harmonics, we can insert the codes for harmonics with the help of the API wizard. For loading the model, it is inserted. So this is how we work for the API wizard. These things are very helpful when you will be working with the modeling with the model, and this is a part of the Hill SCADA where you have to control the actions through model control and sources. Then you can control the actions through widgets also. So these are available in HIL SCADA panel where you can have, and this is a script editor. In a script editor, with the help of the script editor in API wizard pane, you can do all this. Scripting of codes can be done, inserting of codes can be done. This is how you can insert the code. And if you will be getting any error, so there in console there will be showing the message that what is the error you are going to get. Similarly, in a schematic editor also in console, there it is warning and error it will be shown in the console pane. So this is how it is used. This is Typhoon Hill is embedded with Python 3. Actually, in very short, as time is running, so in very short, I would like to tell that why we have used Python. So it is simulation engine, from simulation engine to web server, and it can directly get reached to the user actions. And then in schematic editor, these sheets can be plotted as spreadsheets in the form of .csv files. If you are plotting for waveform plots, then you can get directly to matplotlib.png files, and in control files, this Python files. Why we have used the Python file? Because it is extremely good all-purpose programming language like HDLs, and do one specific thing like synthesize to hardware. It is so one should also know this Python language with C and C++. Actually, we have used Python for the purpose that like there are several tasks like testing, data collection, and automation, which constitute a large chunk of engineers' time. So in my experience, design only takes about 5 to 10% of engineers time. The other 90% or so is consumed by things like researching, testing prototypes, or debugging, or creating test jigs or programs or production tests, quality control, and of course the documentation part. So a lot of things comes before the design, like researching part. So here you can have so this part can be lots of hard tasks can be still needs to be handled once the design is implemented. So there is a lot of hard tasks that needs to be handled. So you can, so with the help of this embedded Python 3, we can use, we can we can have the more I just take an example of file processing. Like when you have a file is in one in .xml format and customer requires it in another that .csv format. So this is a common situation that would be normally be a huge headache, that if not a showstopper for means, so you have to fetch a few libraries and some simple Python codes, and it is possible to change text files between simple formats. Also, the automatic testing equipment as an electrical engineer, as one, so one of the big advantage of using Python is controlling and automating test equipment. It becomes very important, more and more common, and that is low cost test equipment fitted with USB outputs and can collect the data and store them in .csv format, in formats such as CSV. So it was here again I take example, like for if you want to get the data from oscilloscope, then you have to hand oscilloscope, and that is expensive. Then you will get the waveforms, and then you can then you have to export it. So it is why not use the Python to get it inexpensive and can output waveforms as raw data in the form of .csv. So here, this means you can actually capture the data from some waveform, and it processes and plot the output. So this is live physical data that you can now play with inside your computer and see how it behaves with your digital filters. So this is the plus point of using the Python 3, and the Typhoon Hill is embedded with Python 3. Also, you can format it to feed to an arbitrary waveform generator and recreate the exact waveform for testing on a circuit. You can also set a closed loop like simulating device under test, like waveform generator or collected data. Also, so as a professional engineer, we are likely to be involved in manufacturing at some point, and the ability to automate testing for production is extremely useful. So that's why it is better for the company's bottom that those savings come from few field failures and less reputation damage from bad quality control. So it's better to get customized to these types of to overcome these type of damages and bad quality control. So we have here Python 3 is embedded here to frame us in a class to get protection from all these. Even SQL database management you can also do here in Typhoon Hill with the, because it is embedded with Python. So this allows you to interface to many of the popular relational databases like SQLite or MySQL without having to change your code. So this is the plus point of using Typhoon Hill embedded with Python 3. Test suite, when you will in a schematic editor, when you will go for test suite, so this is the test suite for MPPT it is. So it is the code it is given. We are using test suite for this high standards, like test suite, it is the tool available only written only with the Typhoon will use for pre-certification. In this tool, certain test scenarios is based on international standards are available, like for microgrid DDEW, FGW, TR3, REV, it is written REV23. So under this condition, you can test with LVRT, HVRT, LFRT, and HFRT. That is LVRT, low voltage right through, HVRT, high voltage right through, LFRT, low frequency right through, and HFRT, that is high frequency right through. And similarly for MPPT, that is multiple dynamic efficiency test and static efficiency test. Then coming towards this. In control center, it is one more slide was there, that is Typhoon test ID. You must have seen in this.
Yeah, Typhoon Test IDE, it is the platform where you can test your model with test, and it is the advanced version of this test suite. So this is the purpose of pre-certification is that to escape you from the damage, from the physical damage, and you are physical damage and time loss. It is here pre-certified, so it saves the time after this pre-certification. 99% it will be accepted. Your model cannot be rejected. Your work cannot be rejected. So this is the plus point of um, the hardware you can license will be used for even for Typhoon Test IDE. Additional license is required as well as for test calibration. Till now, for test calibration, we have not observed any issues from wherever we have delivered the product. So we have not received any such type of issue till now, that we have not received any issue regarding this test calibration, that somebody have any problem. If they have got problem, so they can it can the problems can be checked for the entire device interface, analog and digital input outputs, including the externally available supply levels. So both test and calibration procedures are fully automatic, but a valid license is required in order to run the tool. This signal analyzer, this in signal analyzer, it is a tool used for visualization and analysis of signal data exported with Typhoon Hill software and or dynamically imported from HIL SCADA. It shares the same visualization and signal analysis functionality with the capture and scope Hill SCADA widget, so, which is available in Hill SCADA widget, that is capture and scope. So for HIL firmware manager, so this is HIL firmware manager. Its application allows the user to automatically upgrade firmware on multiple HIL 402 or 6 series devices. All devices firmware files are packed together with Typhoon Hill controls center installation, and additional firmware download is not required. The user can start the upgrade process on the desired device. Firmware is up to date, the firmware configuration can be changed, and multiple connected devices of the same type is also available, and firmware manager will update them sequentially one by one. But remember, do not turn off or plug the HIL device during the firmware update procedure. It may result in HIL device being unusable. So during the firmware update, there are several procedures. All other Typhoon Hill applications should be closed. So this is the important point which you have to keep in mind while when your firmware is updating. And with the script editor, you can use several library components, that is converter toolbox, microgrid toolbox, machines toolbox, power system toolbox, signal processing. All these things can be done. So coming to our next test suite, this is the pre-certification process we discussed just now. So this is the complete package of Typhoon Hill which we are using, that is, so in Typhoon Hill tools, that is offers a unique user experience free of third-party software hardware complexities. As a result, Typhoon Hill Control Center with all the libraries installs with a single click, models compiled in second, digital inputs are sampled with a 20 nanosecond resolution, and real-time simulation runs with the time step as low as 500 nanoseconds on all Typhoon Hill products. We deeply believe that that less is more when it comes to test equipment that our users love. and we stand behind seamlessly integrated technology stack from Typhoon Hill's application-specific processors and ultra-robust numerical solver all the way to the schematic editor and SCADA. This complete technology stack that empowers our users continuously exceed their controllers, soft quality, performance, and time-to-time market goals. This is how you can install our Typhoon Hill virtual hill device software from directly. It is open source. You can directly go to the Typhoon Hill homepage, click on the get your virtual hill device hill license. Then this is products, then devices, then virtual hill, then register yourself, then you will get the activation key in your mail. You can download the Typhoon Hill Control, download the software from the Typhoon Hill Control Center. Then again come back to the My Typhoon Hill option, sign up with the activation key which you have got in your mail, and you can log in to this download license file and Typhoon Hill software. There is also a quick start guide for installation documentation is available. You can run, means you can run your first simulation, and by using the examples, opening the example models, you can run it. And this will help you. This quick start, you can go through the quick start. This will help you that how to explore all the things. The system requirement, it is Windows 7, Windows 8, 8.1, Windows 10. You have minimum requirement is 2 GB RAM, and minimum screen resolution is this 32-bit and 64-bit processor as well. It is open source, user-friendly, permanent license, unlimited users, and free upgrades. This is the software installation configuration. When you have to install a software, you need a PC running with the system configuration. You can log in. This is how you can start the installation. By default, this will be installed on your C drive. Here, don't forget to browse the destination where you want to select, where you want to store your Typhoon Hill. Also, don't forget to create a shortcut on the desktop, then finish it. Compilation, such type of a window will come, then it will show important license warning. For important license warning, from that same page, you have downloaded the license. For licensing step, you can start the Typhoon Hill Control Center, you can open the license, you can the downloaded license can be placed in the license folder, and you can restart the Typhoon Hill Control Center to apply the new license. So you can click on the license info. In the previous window, it is where it is showing. Here you can click and you can import the license from where you have stored the license file, and you can restart. After when your everything is done, then this type of a control Typhoon Hill Control Center will open, and you can click on the different icons, that is the different control centers for your modeling and other things. Not but less, this is a very good platform, Hill Academy. I would suggest for the every participant to please log into the HIL Academy, because it is a place where everyone can find courses from the domains of car electronics and power systems. Moreover, HIL Academy is open for external contributions, so they can upload and create their own materials and use the platform for sharing the knowledge. So here in Hill Academy, what you will get, some of the tutorials are created by the Typhoon, that is Hill Specialist course, that is Hill Essential, aimed at undergraduate modeling and interacting with the running model, then automatic testing, then this is your interactive with running model. Then ECT is the number of the European standard timing according to that. So ECTS you can go, this is made for international level, the standards, that is for getting you. These are the lectures, number of video lectures and other things. You can go for hands-on work with virtual hill device. It will give you an idea to explore. There are a number of tutorials available for modeling of ticket or chipboard or modeling test automation. Here are some of the creations by the members of the Typhoon Hill Academic Program, where you can go through digital control of grid tight converter testing, created by a group. All these groups for here again you will get the online learning platform. Here, this is the link where you can register. Also, you can become a Hill specialist by giving the online exam after you have gone through all the videos and tutorials. Still, if you have anything, you can find us at kp@quartz.com, hill.support@quartz.com. You can post your queries either through book ticket or your personal queries regarding if you're working in Typhoon Hill environment, and hill.info@quartz.com if you're querying for some materials. You can follow us on LinkedIn. You can get us on WhatsApp on the given contact numbers. This is the contact number of the HR team for the query of the products and commercial things. For technical queries, you can contact us on this or on this hill.support@quartz.com. So here I finish my presentation. If anybody has something to ask, they can ask. Hello.
Hello, thank you, madam. It was a wonderful session. If participants, if you have any queries, you can unmute and directly ask to the resource person. We will wait for 2-3 minutes, madam. Or if you would like to post it on the chat box also, you can post your queries. Madam, I think they don't have any queries at now. Most probably after going through the simulation, they may ask some related questions.
Okay.
Okay. Uh, I would like to
Yes.
thank you.
Now our session is very hands-on.
Yeah, hands-on. That is what. That we will start at 12 o'clock,
Yes.
12 noon.
Okay.
Okay, 15
Okay,
minutes
sir.
break we will give them. Uh,
Okay. Sorry, 15 minutes delay.
yeah. And there is one question from Karthik Yam. What is the approximate cost of Hill device?
So it is approximately it is for our basic HIL device 402 cost around 18 lakhs 50,000 plus GST at the rate 18%. It is tentative. It may decrease and it may increase.
Okay. Hope Karthik you got it.
This is I'm telling about 4 core dedicated FPGA.
Yeah.
And also you can mail your queries to hil.info@quartz.com
Cops.
regarding the cost analysis and commercial details.
Yes. Okay, madam. Thank you. I would like to just summarize what you have covered today. That is the Typhoon hardware in loop incorporation. You introduced to that introduced the founders. You also introduced to the QAPs. You explained the different system architectures, the Typhoon Hill technology, the uses and application. Hope the participants have got why FPGA have been used over the CPU, and what is the features of FPGA solver. Also, you explained about the Hill simulators and compared the 4 series, 6 series, and M series. Also, we could know the microgrid test bed and its salient features. We also learnt about the product portfolio overview with the interfacing boards, the automation, and ultra high fidelity. And you also showed us the Typhoon Hill Control Center 2019.4 version, and what are the features on the desktop of the Typhoon Hill Control Center. and also you given the information regarding how to download and install this open source software with the system requirements. Hope all the participants have understood this and gained a lot of information about the Typhoon Hill, and they make use of it for their research or the courses. With this, I thank the Khushbu Purwar madam as well as the Shashank Kumar for the wonderful session. Uh, we will meet at 12 noon or okay, 12 noon, and we will break for the for 15 minutes. Okay. Thank you, madam, once again, and we will meet again at 12 noon.
Okay, sir.
Yes,
Sir, for
yes,
yes, sir.
madam.
Thank you, sir, to you especially that you provide us the opportunity to share.
No,
Thank you.
madam. It's a privilege having you for I mean, in this platform where most of our faculty members have got benefited from this. I should thank the Shashank Kumar sir also. With the short notice, he agreed for the sessions, and he was very happy that we have asked him, and he's. We are also happy that with a short notice, he agreed and arranged for this session. Thank you very much, Shashank sir, and you also, madam.
Okay, sir. Thank you, sir. And for any queries, sir, you all can contact us individually. We can, if you're working, if you're having any technical problem, we can connect individually also, either through the desktop or any of the things. Okay, sir. Thank you.
I am working as a marketing and support engineer at Forbes Tech. So the concept of this webinar is all about simulation, programming, softwares, the tools involved in it. So basically, we are based in that technology as our tool choice. So in this webinar, we've discussed about some terminologies which are already been discussed, but still to enhance that part also, like what is HIL and what are the types involving in it, and what is real-time simulation, as well as the simulations which we all are doing in our engineering part, and also in top of that, what is the need? What is the need of that? Why should we switch from simulation to real-time and hardware simulation? What is basically the need for that? And why typing? Because there are lots of softwares, lots of real-time simulators available in the market. So, on top of that, why typing? We'll discuss that part. And also, we are going to discuss regarding our software and also working hardware, how it is user-friendly and how it is easier to configure to the software for hardware simulation, and also how it is easier to dump your simulation model real-time simulation. You can see while we are going to the answers. So we'll start from the beginning. So basically, if you want to download our software, if you go first to the web browser and then you search like this type of already the link has been shared, but still I'll share the steps involving in it. And you need to go to this products and then devices. Over there, it is virtual device, because as it is a software, so we have aimed this our hardware as virtual hardware. So you need to click over here. After clicking on it, you can see it appear as supercharger, virtual everything. So you need to scroll down and get your virtual license. So just click it, and you can see it's the form for filling up your details like your applications as well. And then after you submit, we get an email from that regarding link to activate your account in Typhoon, and also a key license key over there. So I think you can see my browser page on this type of thing. Okay, so after you fill up this form over here, this shall transform your email level with PHL. After you fill up this form, you will get an email from type.com or with a license key on it. And after you get the details, just log in over here. This my type section. And you need to provide your email as well as a password. You need to sign up over here. This is activity provided on your email. And after you sign up, just click to log in. Just if I log in over here, you can see my account is created. Similarly, a similar account will be created for you. And in download section, go to this download section. Here, download your software. And it's 64-bit based software. If you want to install the 32-bit versions with the 2-bit on this page, we get the software version compatible with 32-bit. So in every quarter, you will get upgrade for the software that is your cost. So is my voice clear now, or still there is some issues in that? Well, just a moment. Okay, so I'll just start. Can you see my type wheel control center screen over here? Is it visible? You can see that. So basically, you will start with this first the technologies involved and why we are this. Yes. So as we are, it has been discussed already still. So previously. Previously, when engineers used to develop a system or design, they first write equations and then they used to solve the equation. And after solving the equation, they conclude to the results, and after getting results, they try to develop their hardware model. So, like this, they used to do the experiments, they used to develop any kind of hardware technology on base of that. But as previous, the system was simple, so it is easy to write the equations behind that, and it is easier to solve. But with the increasing advancement of technology, the introduction of computers, the introduction of softwares also. So what engineers did, they replaced the hardware equations, the equations in background of the hardware, they replaced that with block sets involving in the software. And using that block set, we just drag and drop the block set from our library components and connect it, and it will do some kind of equation. And you need to solve it with some kind of solvers. And after solving it, you get time constant, you get the results. And these whole steps we are going to perform in our computer itself. So in computer, you know that there is some kind of processor, either it is in the core IP or Wi-Fi. So similar kind of processor is available in our computer. It's CPU based. So those equations are solved by our solver, by our processor itself in the computer, using some solvers, and they give results. But the results for smaller time still looks accurate. But when we increase the time, when we increase the time limit, it's going to hang, depending upon the complexity of the model you are simulating in your simulation software. So, and there is also no relation to your time constant, because whatever time for the simulation we have provided, like 5 seconds or 2 seconds, it either may be more than 5 seconds or less than that. So there are lots of time complexities involved in simulation. So what we do the next step forward. So where we get the flexibility of the simulation, because in hardware there is no flexibility. You cannot connect with anything, with anyone with anything, because there are some rating issues. Hello, is it still not clear? I was in real-time simulation part. So basically, when we are connecting with hardware, there is no limited fixed flexibility actually. But accuracy we are getting 100% because we are testing with actual hardware. We are getting accurate results. But in simulation, we can connect anything with any components. We can connect. There is a flexibility. There is no issue of devices. So we can get flexibility of simulation. So what engineers do, they need flexibility of the simulation as well as the accuracy part. So for accuracy, what they have changed is they use a specific type of device like say calculator for calculating or higher complex models. So they use a different type of device called as simulator, in which there are certain application-based specific processor needed, either it is FPGA or CPU. So they have used that processor that was simulator, and also there is some analog input based as well as it's for interchanging the signals. So they developed this kind of simulator, and whatever the model designed to simulation software, that to be done on that processor, and that processor process that simulation model to the specific time they have provided for simulation model. So that's why it's named as real-time simulation, because whatever simulation we are doing, the simulator, it's occurring on the real-time clock. Okay. So all these steps we are going to see our hands-on session when we are discussing about our simulator part and developing models also. What is the difference between this real-time and what the errors is? We are using sketch, we are using real-time simulation. And after that, what we have done, we have separated, because in electrical part there are electrical plant, there is two parts, one is plant and another one is control. So on that next step, what we have done, we have dumped the controller part into some kind of PSP interface based parts. It is done that sequence developing of the controller into that part, and we connect it to the simulator. So now our plant is running on simulator, and our controller is running on this, and we are exchanging this. So it is up to forming within our computer, within our simulator, and within this controller part. So a loop is forming, and there is an actual hardware. It's our controller is our actual hardware. So it's termed as hardware in any or controller hardware. So we are testing actual controllers over this. So now the next step of this HL, we are to attach this CHL, which we have discussed as controller hardware, and the next step is PHL or power hardware. So the similar thing happens in power hardware. What we do, we exchange this controller inside the simulator and the plant part like converter, like chips, and our source like this source becomes actual in the real world, and we interface the controller signals down inside the simulator with the actual plant. Okay. So this is known as power hardware. That the power part is actual and the control part is digital. So these are the two types for this power hardware and controller hardware. And after that, when we are done testing with controller hardware to power hardware, then we go for activate and build hardware testing. So these are the steps called to avoid the risk, because with the increasing complexity with the advancement of power electronics, all these steps. So now I just do my software side. So if you download the software and you double click on the icon on the desktop, diagonal control center will open like this, and here like this, and here you will see hardware information. So if you click on this hardware information, it will show you the details if you are connected with any hardware to simulator device. But if you are not connected with any hardware to simulator device, it will show like this, unable to detect any device. So whenever you are using virtual ring, whenever you are using the software simulation board, it will show like this. And whenever we are going to connect with our real-time simulator, so it will show the hardware details, that what is the device we're using, what is the configuration, and also the firmware available in it. all the details which displayed over here. Next, this is for online help, and this is for offline. If you click on it, HTML page will open for the help purpose, and this is the documentation hub. In the documentation hub, we get all the details regarding how to use software, some steps for the software, and also the library components involved in the library for the library components. What are the equations behind the components available over there? You can get details in this systematic library, and also the various details for the hardware systems, like we have discussed already in the first session, like the 2 series systems, everything regarding the input documents. So over here you can see this hardware is a guide as the details for this IoT output, like this. For the 402 device and citizens. Also the user number of analog and for the connectivity options, like this. We get all the details over here for the hardware system user. And then this is for the extension of the system guide. It's for installation and access for the part, and for users multiple in device. This is guide for hill parameter, and it's for accurate list interface. We have discussed the hardware sequence for the interface part. Similarly, these are all the interface output. That also some technical books like analog output calibration, battery molding application. Someone is interested for battery molding, someone is developing their model for electric vehicle purpose, they can use this software. All this molding part is available. Usage of its part also, and yes, for monitors, integrated modeling. Also, power modeling of power electronic devices are also available in the documentation. And there are also some examples of documentation regarding some examples available in our library. Is already available in this documentation part. And these are for this API documentation part, like automatic programming interface. So let's see there, if you double click on it, get all the details regarding the programs that use the software and to interface with various parts, like to programming based on database, programming based on SCADA, and etc. So these are all the documentation, and this is a section for the license. You can see you get the details of the license. If your license is not active, or if you have not provided your license, this shows red color. And these are all the tools. So basically, in simulation software, I have used security. You can see the place where you can model and you can see your data. You see the results like this. A platform will be there, and a platform for programming interface will be there. Like today, we have a platform for programming and platform for simulation. Basically, most of the simulation software market has these two options, but you are getting these all features like this SCADA. As a name, SCADA appears like supervisory control and data acquisition. So whatever the model you have developed in the schematic editor, after compiling, it opens directly in Hill SCADA. And over in Hill SCADA, you can control the actions of the simulation, like you can provide timer, you can insert conditions, you can insert some faults while running simulation, and you can acquire the data, you can record data in MAT format, in CSV format, and you can also share the data from one place to another. So that's why it has been given the name as this data. And then this typing-based ID, it is a platform where you can write your codes in Python, and you can do the whole simulation, not using the schematic editor, just writing the codes. You can do the entire simulation, you can see the results, you can insert some conditions in the simulation, and you can get results. So it will generate some retest codes also. So it's Python based, and our software is basically based on Python. And this is case two demo. So as it is written in demo purpose, it is used for this industrial application basically. Also, let's take an example. If you are designing some solar converter manufacturer is designing a new type of controller for testing purpose for selling it in the market. And after they develop their product, they want to test their product with some certain standard conditions, and they want to get certified for that product. Okay. So what they will do, they will go to some certification agency. They will talk with them, and they will go for this certification part of the controller they have designed, and they need to pay some certain amount for that purpose. Okay. So after paying that certain amount, they will give them certificate of this product is meeting some standard conditions for country or abroad. So certain conditions they are meeting, and they will give a certificate. Now you are ready to go to sell that product in the market. Okay. So let's take an example that certain controller doesn't comply the standards available for the certification agency. So what they will do? So after they get built, they need to get back again, make the changes according to the standards, and then they have to get back again to the certifying agency, and they need to test that controller. So one time, two time, it's okay, but if your product fails at many times, you need to pay for that also, pay a huge amount. Also, the certification agency will not allow you. There are certain limits that after this you cannot get allowance for testing that particular product. So there are some certain limits for that. So what we have provided a test suite, which is developed by Austrian Institute of Technology using some certain grid conditions like EDW, UL 174.1, and if we need to grab this LVRT, low voltage diagram, high voltage diagram, like HVRT, LFRT, low frequency diagram, HFRT, high frequency diagram, based on certain conditions, like a test your controller constant in the converter sections, and also for solar part, we have the same PD, dynamics efficiency test, static efficiency test, and PI ISEP. So these are certain test conditions. You can pre-certify your controller, and after pre-certifying the controller, you get a test report for that. It may be 800, 900 pages on it. You follow the conditions. Will give you standard test reports for that, and now you can go to the certifying agency. You can be rest assured that your controller will pass all the standards. So next is waveform generator, as discussed already. Basically, the waveform generator is used to generate waveform, as the name suggests. So we can generate your file, PIV data, as well as your own source file, and you can use it in the simulation. Is whatever the file you generate from here, you can directly use it in the simulation. So if you have any data like UCISC data and the type of material, you have this data, you just need to provide the irradiation and temperature condition, and then you can. So after you complete this data will appear over here. So like this, you do not have much data, just select this get 5 to 5 compatible. So you need to give only small amount of data on this technology that is part and provide the irradiation and temperature conditions. So like this way, if you have any data you have brought from outside the market, just need to provide the data over here, and you can get your PPI. So you do not need to buy any simulator for that purpose. So the next option is over here. To click on source file generator, you can create your own source file, you can insert certain conditions that spikes over here in the source, and you can save that file and you can use it in the simulation. So just add a source. There are multiple options like sinus value, AC constant, stock square, and just need to provide the values. And remember one thing: whenever you enter some values, it just like I have rules, and you need to press enter. Until unless you press enter, it will be read in the. So you need to press enter over here. If you want to use harmonics, so you will provide the harmonic value and hybrid hardware science like this. And if you want to do kind of thing, like this, you can insert this, insert spikes inside it, and you can save it. Or save. You can save it for ISO format already. Some files are saved over here, so you can use this directly to the simulation. So I'll just back to this part. And this is signal analyzer. So this tool is used for whatever the results we have get from startup, whatever the data we have captured still in startup. We open over here in signal analyzer is an advanced tool of this, and over here you can analyze the waveform we have captured, and you can do FFT analysis. And this part we have already discussed that scriptator is used to write the Python programs. We have embedded Python 3.6 version available over here. Someone mic has been turned on, please.
Sudipto, your voice is not clear, Sudipto. Lots of disturbance, I mean breaking in the voice.
Just give me a moment.
And then get next repair
Just give me a moment.
Yes, yes.
Hello, Sudipto. Hello. 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 Sudipto. Hello. Hello.
हाँ सजा तुम्हारा वॉइस नहीं आ रहा। हेलो
Sudipto,
तुम फोन से कनेक्ट करके करो ना, वॉइस नहीं आ रहा तुम्हारा।
हेलो
सुनाई नहीं दे रहा क्या बैकग्राउंड में कोई कुछ बोल रहा है तो?
हेलो सुदीप्तो।
हाँ
हेलो।
हाँ तो देखो देखो और कनेक्ट करो फोन से और बोलो।
हेलो।
Hello sir, can you hear me? Am I audible?
yes, very clear now.
Okay, I think now it's clear. So I shall continue. I was in the script editor. So as discussed, script editor is used for writing your Python programs. As basically Typhoon Hill is based on Python. So we have embedded Python 3.6 available in it. Also, you can interface your own Python, which is already installed in your system. Like if you want to use 2.7, which is readily being used everywhere, so you can use that version also. So whatever the Python version installed in your system, you can interface with scriptator just by changing embedded Python 3.6 to your system one. So you can use it. And then next is firmware manager. So with every software upgrade, there comes with a new firmware embedded in the software. So whenever you just update your software, you need to upgrade your firmware for the device you are going to connect with it. So you will get the firmware with the upgrade software as discussed. And then next is test calibration. So this tool is used to test and calibrate your analog input-output signals for pins for the simulators. So you need to calibrate once in 2 years, but it's not required. So next is the logo, Day4 wheel. So if you click on it, the website will appear directly. And this is the current version, which is 2020.1 SP2, the latest one. So now I'll just move to the schematic editor and we'll discuss that part. So let it be open. Okay, I just explained once about SCADA. So basically in every simulation software, what you get a platform for modeling, like we have schematic editor, and a platform for programming. Okay, so in every simulation software it's common. Okay, so what you are getting all these features extra, like waveform generator, Hill SCADA, Typhoon test ID, and test suite demo. Okay. So in Hill SCADA, as the name suggests, supervisory control and data acquisition. So whatever the models you have developed in schematic editor, after compiling, it opens directly over Hill SCADA. Okay. So in Hill SCADA, we can control the action part of our simulation, like when we can insert, we can change our voltages, we can change sources like PV, we can change the irradiation and temperature condition. Also, we can insert some faults using the widgets available in Hill SCADA. So we can also time it, like in 5 seconds, 10 seconds, this certain faults will be inserted, okay, and it will get back to the normal condition. So all these actions we can perform using Hill SCADA, and also there are some monitoring widgets by which we can see the data, see the outputs of certain measurements, toolbox which we use in the schematic editor. We can measure the voltage, we can measure the currents. Also, some graphs will be there available if we discuss on this SCADA part. You can see, and also there are some data logging options, like there are streaming data logger and signal data logger. So in signal data logger, you can save your data continuously in CSV format, .mat format, HDF5 format, etc. You can save your data, and in streaming data logger, you can send this data from one place to another. Okay, using some kind of communication like Ethernet communication. You can send this data. Okay. So as the name suggests, so we have given the name for this platform as Hill SCADA, so we can control our simulation as well as do the monitoring part, as well as we can do the data acquisition, and also we can send this data from one place to another. So that's why we have given here the SCADA. It's different from that SCADA we use generally, but the actions are similar from that. So we have named that this as an application as Hill SCADA. So first we'll go to our schematic editor. So we have just click on schematic editor. It has opened like this. I'll just open it. You can see after you click on the schematic editor, it will open like this. Here are some options available over here, like file, edit, view, model, Windows help, etc. So if you click on file, you get an option to import PCM files into Typhoon directly. So if you have used PCM simulation earlier, you can directly import that PCM file into the Typhoon part, and you can use it. Okay. And also you can export this whatever the files you develop over in the schematic, whatever the model you develop over the schematic, you can export to PDF. Also, you can export to image. And here is a new option. In new option, there are two options. One is for new model and one is for new library. So if you want to develop your new model, so you have to click on this new model option or Control N, And if you want to go for this new library, just take an example, you want to add your own library in Type-O-Hill, that option is also available in Type-O-Hill software. You can insert your own library inside this Type-O-Hill software. By clicking on this new library, you can select the components you want to include, and then you can save it. It will be automatically available. Okay, you need to first reload it, export, and then reload the path, and you can this library will be available over there. And there, if you have developed already a model, you can open it, and also an option for open example model. So if you click on it, so more than 50 plus examples are already available in build for different domains and different applications. Like for communication, if you click, there are different examples like for CAN bus, DNP3, distributed network protocol, Ethernet, IEC-61850, MMS based, sample values based. Also, those who are doing in the power system area for PMU studies, we have this IEEE C37118. Also, a virtual PMU model is also available in the example section. Modbus for communicating with actual SCADA, you have this OPC protocol, and serial communication is also available, and this Sunstick Modbus also. Okay, so these are the various example models available in the communication folder. There are some examples for the hardware in use, some example for how to examples like the device partitioning, etc. Those will be required in the later part. And those who are interested in the field of microgrid, various examples starting from back-to-back converter to wind turbine and wind farm. And also some examples for protective relays are available already in build. So also in power transition, starting from single phase rectifier to this welding inverter, already available. You can see already in built example models. You can open it directly, and if you want to make any changes, you can change and save it in a new name. And for power system, there are various examples like IEEE 4-node test feeder to transmission line section version model available. So we don't require right now this part. I'll just close it. And also you can access whatever the option available over here is shortcutly available, like creating a new file, creating a new schematic is already available over here. Open, save, save as, like this, print. And there are some 3 sections over here which is most important. You already know about zoom in, zoom out part and flip it, rotate it part. So these are the 3 buttons which we require mostly. One is this model initialization script. If you click on it, a blank page will open whenever we develop our model. So whatever the parameters you want to define, you can define over here. Okay. Also, you can do certain calculations over here. Okay. So, and next is compile schematic, and next is compile and open model in new SCADA. We mostly require this button because whenever we develop our model, we need to see the signals, and as I told that SCADA used for the action and monitoring purpose basically. So you need to click over here. So after you click on it, the model will compile over in the schematic and it will open in Hill SCADA. Over there, we need to create a panel, SCADA panel, for this actions and controlling part, and we can see the signals. So basically, we mostly use this button, open model in Hill SCADA. So I just take a new schematic. So I just open it. So whenever I click on this new schematic part, so it will open like this. It will ask me for hardware settings and simulation settings. So as we have discussed that, if you know that our software is named as virtual HIL or virtual hardware loop. So whatever the model we developed in the simulation without connecting our hardware, whatever the model we are developing, it is based on the hardware topology like 4026 series, 404, 602 plus and 604. So we are developing our model based on these hardware topologies. Okay, but it is independent of the hardware. We do not require hardware to connect while developing the model or compiling the model or simulating. Okay, we are not right now, as you have seen. Just click on cancel. As you have seen over here, we are not connected with any simulator device. So for simulating your model, you do not require any hardware loop. But whatever the model you are developing over here, it's based on that simulator. So whenever you go for the real-time simulation, you just connect USB with your laptop and whatever the model you have developed in your PC is directly dumped into the simulator. Okay. So there's a type of device you need to select. You can go to the complex simulation. If you have complex model, you can change your model from 402 to 604 because it is having 8 core of FPGA and this is having 4 core of FPGA. And also there's hardware configuration ID like 1, 2, 3, 4, 5, 6. So regarding that, you need to go to this device setting. Here you can see different configuration based on that hardware. Like we have selected just a moment. As we have selected 402, so you can see number of cores in it. Like in configuration 1, we can get 3 cores. In configuration 2, we can utilize maximum 4 cores. Okay. So as we know that 402 is based on 4 core of FPGA, so in configuration 2, you can utilize 4 cores of this simulator. But in configuration 1, you can use 3 cores, and there is one machine solver. Means you can utilize one machine over here because there is one machine solver. And there is 8 lookup tables. 8 lookup tables means lookup tables is used for battery and PD part. So if you use any battery or PD in the simulation, so for that 8 number of battery and PD, you can interface in the simulation for configuration 1. Okay. Similarly, those who are working on thermal power loss for power electronic device, thermal loss for power device, you need to select on this configuration 4 because it is active over here. Okay. So I think this part is clear. So how to select the hardware configuration ID and how to select product if you go for the multiple configuration, then this is required, but we'll go for the initial 402 with the configuration ID 1, simple. And in the simulation method, you can see the types of solver like exact, trapezoidal, Euler, and bilinear methods. So I'll go for the exact, and in simulation step, you can see they're starting from 500 nanosecond. As we have discussed that as we are FPGA based, so we have the lowest time step of 500 nanosecond for planned simulation, which can go to 20 microsecond. For if you're working with power system, you require higher time step. So for that purpose, we can go to this 20 microsecond, but it starts from 500 nanoseconds. So we'll click on auto. If you click on auto, then it will start from the lower time step, and if the model is too complex, it will go to the higher automatically. So we'll click on next, and then it will ask for review, and then we'll click on finish. So it will take some time to load the library, load the components available, like, as well as a blank page will appear where we can drag and drop our components and connect it, and we can compile the model and run simulation in this part. So okay, so like this, it will open a blank page which is written as over here, new schematic with the current date and time. And here is our library explorer. If you want to search any component, you can just directly type over here. If I want to search for register, you can directly type over here. You can find over here. And if you want to go to section, I'll just describe every section over here. Like starting from circuit breakers to production line. So if you open circuit breaker, there are 2 options. One is motor operated and one other one is master packed. So if you double click on this motor operated circuit breaker, so if you see over here, it is based on a model of ABB's stored energy motor operated circuit breaker series. Okay. And it has 2 options for control. You can see first signal is switch close and second signal is switch off. So all the details regarding this circuit breaker is already provided here. If you need further details for this, you need to click on this help, and a HTML page will open like this, and we'll get the details for this motor operated circuit breakers. Okay. Similarly, regarding every component based in our library, you can see all this part, all that help details. You will see the documentation or see the equations or see how these models have been, two blocks have been designed. So if you click on this master pack circuit breaker, you can see it is based on the model of Schneider Electric master pack circuit breakers. So whatever the components available over here in our library is directly based on real-time applications. So whatever hardwares or whatever the real-time devices we use widely. So based on that, our toolbox have been designed. So I'll just delete this part. There are various types like double pole, single pole, triple pole, MOE and MP based circuit breakers available over here. I just do not go in details because we have less time. So whenever you install the software, you just go through these library components. Okay, and this library is entirely developed on electrical engineering domain. Okay, and next we have this communication protocols like C37 INAP 118 for PMU studies. If you click on this, you will see PMU receive, PMU send, CAN bus, CAN open, and distributed network protocol, DNP3, Ethernet variable exchange, ISEP-2020 boost based, MMS based, and sample values based, and some Modbus device along with OPC for communicating with actual PLC, and we require ISEP-61850 conventional protocol for connecting with relays. Okay. Because relay understand this ISEP-61850 communication and serial communication also we're getting. Okay, in communication. Next, we have contactors. We have idle series and non-idle series. If you just drag and drop a single pole contactor, double throw contactor, if you double click on it, there are three ways to control this contactor. One, you can see this digital input for digital input, and the second one is model. So if you click on this digital input, you can see SA as 1. So I'll just go back once to some part. I'll just minimize it. I'll show you something. Just give me a moment. Okay, so I'll just share once. Okay, so can you see my screen now? Is it visible?
Yes, yes.
Oh,
So
okay. So here you can see the image of the simulator. This is the image I have captured from my phone for this L402 device. It's look like this. It is compact in size, and it is having this analog I/O. You see A, B, C analog input output ports, and this is digital input output ports. And this is the indicator. If you turn on the simulator, it will glow up. Indicator LEDs over there. It is the DSP interface card. We have interface our text instrument F2837 card over here. And if you see, this is the backside image of the simulator. This is the turn on and turn off switch for the simulator, and these are two fans. This is for power port, and this cable, USB cable, is for connecting with our laptop. Okay, and this is the Ethernet cable port. And this is the zoom in picture of this L402 analog input output section. Over here you can see there is written 1 to 32 and A, B, C. So I do not have any knowledge regarding these pins, what is A, B, C means and 1 to 32 means. So for that I need to go to this diagonal control center. I'll just open, it's already open over here. I'll just scroll down on this L402 IO pin output. So over here you can see row A, row B and row C. That means if you go back to the image, this is row A, row B and row C. And this is pin number 1 to 32. Okay. So I need to see what are the analog output pins. So over here you can see that pin number 1 to 16 is analog output pin. Okay. And after 25 we are getting analog input pins up to from 25 to 32. Analog 8 pins are there, and this row C is ground section. Okay, row C is ground section. So if you go back to the image, This means from 1 to 16 is analog output pins. So this is analog output pin 1, 2, 3, 4 like this up to 16, and from here 32 to 25, these are all analog input pins. These are analog output pins and these are analog input pins. Okay, and similarly over here on the row C, all are ground pins. So you can manually configure that which pin is for analog output and which pin is for analog input by seeing this figure and by seeing this table input output. Similarly, if you want to see for this digital input part, so this is the digital input IO section. Over here, similarly, 1 to 32 is available over here, and A, B, C. So in digital side, we can see row A, pin number 1 to up till pin number 32 is totally digital inputs, and from row B, pin number 1 to 32 is totally digital output, and we are getting digital ground pins on row C. So that means if we go back to this block, so row A is totally digital inputs and row B is digital outputs like this, digital inputs, and row B digital outputs and row C ground. Okay, so I think you get the point that if you want to interface any digital signal, you want to give any digital input inside the simulation, so you need to select these pins from row A from 1 to 32. So similarly, whenever we are talking about this control option for this contactor, if you double click on it, control source as digital input, you are getting this pin number 1 to 32. As we have selected 402, so there are 32 pins available over here. So you need to select the pins in which you want to give an external signal to control this contactor. So at that time you are doing hardware in loop simulation, you are controlling this contactor from outside, you are developing an actual control for this controlling of this contactor, and you are interfacing, giving that signal to the digital input pins of the simulator. Okay, so by this way, this is the first method to control this contactor. If you do not have if you do not want to choose this control option, you can go to this signal input from the signal processing part of the model. Means if you select this digital input pin and let it be 1 as it is, and if you compile your model, you will, in this card option, you will get an option to just manually turn on and off this contactor. Okay, so by this way you can also control this contactor over here. And the third option is, if you click on the model and click on OK, you are getting an port over here. So you can develop the control logic for this contactor and connect it with this port, and you can control this contactor. So as we have discussed that our simulation software, as our software is not basically based on simulation, it is based on real-time application as well as hardware loop application. So now you can get the idea that how you can interface an actual signal inside the schematic by using the control options available inside the contactor blocks. Similarly, for converters also, we have this different controller technology. First, we can discuss about the type of converters we are having. Next, as we have this NMC part. There is from boost, buck already inbuilt, flyback converters, ERIC converters, NPC lake, TNR rectifier already inbuilt over here. So if I click on single phase inverter, if I drag and drop, so in single phase inverter we know actually there are 4 switches. So SA top means leg A top switch, leg A bottom switch, leg B top switch, and leg B bottom switch. So like this, there are 4 switches, and if you want to control it individually per switch, you need to select same digital input pins, and you can give the controller signal from outside using this digital input output pins, digital input pins of the simulator. So these options you are getting when you are selecting this option as digital input per switch. Similarly, you have an option for digital input per leg. In this, you can see there are only 2 options. One is for top leg and another one for for leg A and leg B. Okay. So, and the third option is internal modulator. If you select on internal modulator, you can see the carrier is already inbuilt. But previously, what we do, we used to use a reference signal, and we used to compare the reference signal with some carrier signal, and we used to provide some carrier frequency over there, and we provide it to our switches, okay, using some NOT gate also. So already this carrier frequency is inbuilt in our converter. You only need to provide over here the reference signal, okay. So after you select the fixed carrier frequency, you can provide the carrier frequency over here. As we have provided over here 10 kilohertz, you can provide it, and dead time period over here also, carrier phase offset, okay. And if you click on OK, you will get this 3 pins where you can give this reference signal for leg A and reference signal for leg B, and this EN pin is for enabling this converter. So like this, as we have discussed that our software is based on this hardware loop, so you can either control the switches of this inverter from the outside, or you can control the switches of the inverter from SCADA. It's the second option, and the third option is you can develop your controller inside the simulation and you can connect it over here. So these are all the options available for controlling part, and similarly I'll just close it. In machine sections, we have this 6-phase, 9-phase DC machine with separate or parallel excitation, and doubly fed induction machines. So I just take one doubly fed induction machine. Here you need to provide your electrical parameters, mechanical parameters, load. In load, you have this option as SCADA or external, means you can provide the load value from SCADA or external, and in external you have this type of load as torque and speed. So if you select on torque, and then you need to provide the analog input pin. Okay, so in this analog input pin, you need to select the pins in which you are getting giving the load from outside inside the simulation. You need to select the pins and then click OK. Either you can provide the values from SCADA, or you can externally provide the torque source from outside. Click on OK. There is no pin available over here, but if you select on load and change the load source as model and then click on OK, then you are getting an option to provide the load inside this doubly fed induction machine. Okay, so these are all the controlling options available in our software. Also in feedback, you are getting this encoder protocol like EINDAT, ISS and SSI. All these are available. Also, if you want to get some details regarding what is behind the equation behind this doubly fed induction machine, you can click on help and you can get all the details. And if you want to take output from these machines, you need to click on true, provide execution rate, and then click on OK. You are getting the 2 ports, one for torque and one for speed. Okay, so I just delete this one, and this is all for the machines part. And in measurements, we are getting current measurement, current RMS, voltage measurement, and voltage RMS block already available. And also we have a special toolbox library for microgrid. Those who are working on microgrid, we have this distributed energy sources like back-to-back converter, diesel genset, energy storage, battery energy storage, average model based as well as switching model based, and a PV power plant, NPC PV inverter, and twin power plant. All these are already inbuilt. If you drag and drop, just take your back-to-back converter, switching model, just drag and drop and place this inside the schematic. Okay, so you can see it's already inbuilt. So you just need to click over here. You need to provide this nominal power, DC link voltage, all over here. You need to provide the values, filter parameters, controller parameters, okay, APKI values you need to provide, and then click on OK. You're ready to go. Okay. Or if you want to make any changes inside this back-to-back converter, you need to first right click over here, go to this unlink component section, click on yes. If you do not unlink this component and you wish to make any changes on it, the software will get corrupted. So whenever you are wishing to make any changes on this microgrid section inside any library, so you need to first unlink it, okay, and then you can make changes. So now I again go to this mask, look on the mask and see the details. So here you can see 3-phase inverter. 3-phase inverter is used some sources, and here's controller, rectifier control, and inverter control. Okay. So various controllers are already inbuilt over here. If you want to make any changes, you can do it, because first of all you need to unlink and then you can make the changes. So this is some examples. I just delete this part. Similarly, we have got all these components like diesel, genset, etc., and power plant, etc. In grid, you have grid user interface, and some loads also like constant impedance load, variable GPR, variable load, and also some meter like 3-phase meter. And in production, you are getting some under voltage, directional power, low forward, external tip, and feeder protection relay already inbuilt. So I'll just close it. And a model partitioning is required when you are using multiple number of cores. So for that purpose, you need, if you want to separate your cores, you can go for this core partitioning. And if you are using multiple device in cascaded form, you need to use this device partitioning. And in passive components, we have this capacitor, co-coupled inductors, etc., resistors, and also variable capacitor, variable inductor, and variable resistor. You can show it is now disabled. If you want to enable this, you need to go to this model, schematic settings, change this configuration ID for this particular variable sections, and then click on OK. Then it will be enabled. And similarly, ports used for similarly electrical port if you are doing any subsystem part. For that it is required. And we'll go to the scale process section. So in you have already know about this library like accumulator, delay, differentiator, discrete space, disk transformation. And one thing I would let you know that real-time simulation is basically based on discrete domain, not in continuous domain. So whenever we're talking about real-time simulation, so we need to use this discrete part. Okay. So if you're doing, if you are planning for developing a model for real-time simulation in MATLAB also, you need to change the mode from continuous to discrete part. Then after you can go for this real-time simulation. Similarly, whatever the software available for real-time simulation, it is all are discrete based. So similarly, in extras, we have this counter, JK flip-flop, PID controller. I'll just click PID controller. Pedal modulator, AC terminal reference generator, single phase PLL, 3-phase PLL, ABC to alpha beta to T. All these are already available. What is the significance of PID controller we are having? If you double click on it, you can provide the values over here, KP, KI, and KD. Also, there is an option for external. You click on external. And just click on KP only, make it all internal first. Then you can see an option to provide the KP values from outside. So if I use a SCADA input over here, if I go to this signal processing sources, if I take a SCADA input over here, I connect it with this. So now I can change this KP values while running simulation from the SCADA. So whenever I develop a model like this and I use the SCADA input for this purpose, I can change the values while running simulation in the SCADA part. So you can change these KP values from this SCADA while running simulation, and you can change the parameters. Okay. Similarly, if I go for this external part, then our port will be available for PI. So if I take another SCADA input and connect it to PI, so I can change this KP PI values while running simulation. And you can do the hit and trial method. So this is a special feature, and next we'll go to this method. Logical operations, we have comparator, logical operator, relational operator, etc. And in function tables, you have 1D lookup table, 2D lookup table, 3D lookup table, advanced C function, and C function. In C function block, you need to just provide input-output parameters, write the functions, okay. And then you can check syntax. This is based on C part, C programming actually, but you do not need to write that syntaxes like header files. You do not need to define like hash include studio.h, hash uno.h. You don't need to define. Only you need to define this input and output functions, and you can check syntax and then click on OK. You're ready to go. So this for C function, and if you have developed any controller in Simulink and you have generated code from any software, not such Simulink, if you have generated a C code from for the controller part and you want to interface it in the Typhoon software, you can use this advanced C function. Double click on it, go to the additional sources. You can select that folder in which you have generated the C code files, and you can click on OK. After that, you can interface the controller directly inside the Typhoon. Also, if you have some DLL files, you can use that also. Just give me a moment. Just a moment. Let it open. Okay, again I will follow the same step, open the schematic editor and then open a new schematic. Similar, and then finish. We'll again open the blank page over there. Okay, so I was in the same processing side. So we have already discussed this function table, logical operators, math operators. You have absolute gain limit already, you know about that. And in power measurement, you have this harmonic analyzer, phase difference measurement, positive, negative, zero power meter, single phase phasor, three phase phasor, as well as TSU measurement block already available in power measurement section. And in power system, you have this diesel governor from Woodward, exciter model, steam governor model, steam turbine model already inbuilt. And in sinks, you have this termination probe, digital probe, you already know. And in sources, there is some difference, like analog input. If you want to insert any analog signal inside the simulation, you need to use this analog input part. Similarly, you need to select analog pin 1 to 16. We have got in pin 402, and you need to click on OK. So this is the use of this analog input. Similarly, we have digital input over here, and there is another option is SCADA input. So whatever, if you take SCADA input, okay, so you can vary the value in the SCADA part while running simulation. Okay. So whenever we develop a model for the single phase inverter, we'll show you that what is the difference between SCADA input over there. So for interfacing analog signals to the scale simulation, you can use analog input, and this for digital input. Similarly, we are getting this 1 to 32 pins for the digital part. And sinusoidal source, square wave source, tape, triangular wave source are already here, which are mostly required. I'll just close it. And in system, we have this bus joint, like we use mux and demux in MATLAB. We have this bus joint and bus split over here. Okay. And if you want to use multiple simulation steps for the controller part, you can use rate transition, where you can use this, and also signal switch are already available there. And if you go to this actual sources, we have this battery, this drag and drop battery, current control current source, current control voltage source, externally controlled current source. I'll just drag it because it's different. External control voltage source, fuel cell, generator average model 3-phase, ground, photovoltaic panel, and voltage source, voltage control current source, voltage control voltage source, 3-phase, 2-phase voltage source are already available over here. Also single phase constant power load, three phase constant power load. So I will just take one three phase constant power load. So if you double click on this photovoltaic panel, you cannot see over here the option for selecting the manufacturer type of PV panel. Also, there is no option for selecting this irradiation and temperature. So these all options will be available in Hill SCADA. Whenever we compile the model and we open the model in SCADA, all these options will be available over here. So we can change that values while running simulation. So this is the difference. And now you close it. Similarly for battery, there are different types of battery like lithium ion, nickel cadmium, nickel metal hydride, and user defined section. So if you click on user defined section, you get this option for inserting the values, normal voltage, capacity, initial SOC, full charge volume, everything. And after you provide all these parameters, you click on this preview SOC curve. It will open like this. Okay. And if you want SOC output from this battery, you need to go to the signal processing, enable this state of charge output, and you need to click on OK. So output will be available over here. Now, if you want to use an externally controlled current source, means if you want to use an actual current source from outside, so you need to use this externally controlled current source. Over here, you need again similarly need to select this pin and also offset values and gain values. Let's take an example. If you are getting, let's say for the voltages, if you are getting 230 volt out from the outside, you are getting 230 volt outside. But as you know that the Hill simulator pins accept only the signals up to the range of plus minus 15 volt. Okay. So we need to step down that 230 volt into that limit. Let's take an example. We are getting 9.8 volt after stepping down that signal, and we are interfacing it to the pin number 1 or pin number 16 intake. Then it will, if you use a probe over here, the signal will show as 9.8 volt as discussed. So if you want to make it as 230 volt like the outside signal, so you need to insert some gain values by calculating it with the difference, and then if you click on OK, then it will give you 230 volt approximately. So like this, these are the two options over here. I'll just delete. It's already discussed. Now there is a fuel cell. Double click on it. It's based on EMFC, proton exchange membrane fuel cell based. Yeah, someone has query. You can ask. You can also unmute yourself. You can ask. I think maybe it is by mistake. So you need to provide these parameters like electrochemical parameters, fluidic coefficients, fuel cell geometry, operating conditions, polarization curve, stack, and thermal coefficients. And you can use this fuel cell in your model. Now, in constant power load, you have an option for this voltage and frequency true. So if you click on enable, you need to provide this lookup table parameters, and if you click on preview, you can see this voltage true curve. Similarly, if we click on this enable frequency to click on preview, you can see this frequency to curve. You can also change the values for this lookup table over here. So this is it. You can use this as cost power source also by giving negative values over here. So I'll just also group facility is also available. So I'll just close this one. And in system, you have this subsystem part. If you want to create as a system, you can use this. And in test suite, you have this anti-islanding DC meter, dynamic grid fault, and grid fault also grid simulator. So if you select grid fault, you have this, you need to select this fault type, A ground, B ground, C ground like this, also provide fault resistance, and then can use this. But you cannot change this fault type while running simulation. If you use this dynamic grid fault, in that, in this control method, you can select the type of fault in SCADA input. If you provide 5, then it will be phase A to neutral, similarly ABC neutral by providing 11 in SCADA. So I'll just click on close. So this is the difference between dynamic grid fault and grid fault. And also there is a library for transformer like ideal transformer for single phase, 3 phase, etc. And transmission line, we have two sections like Bergeron model and pi section. So we have this RL section, transmission line, and underground cables. So I'll just close this one, and now I'll develop a simple model for a single phase converter with IGBT leg, and then I'll develop the same model using inbuilt single phase converter. So first of all, I'll require some sources. So I'll take a voltage source. Also, I'll take a contactor. So I can turn on and off this source to going into my converter. So I take a single pole, double, single pole contactor for that purpose. And also I'll take in converter section, I'll take IGBT leg 1 and 2. So by this I can click single phase converter, and now I'll need some passive component like resistor and capacitor for filtering. So I'll take a capacitor over here, and also inductor and resistor for load, also a DC capacitor. So all this being done, quite now I'll require some measurement elements to measure the voltage and current everywhere. So I'll take current measurement for the output part, voltage measurement. Already I have get a voltage source over here. Also I'll take a voltage measurement to measure the output before the built-in part. So all this are already there. Now I need to connect all this component which I have drag and drop using the Library Explorer. So if you want to rotate it, so first click on it, and then you can use this option, rotate schematic for 90 degree. Like this you can rotate, or you can just select and press Ctrl plus R. So using that you can also rotate. Now what is the steps for connecting the component is this, like this way. If you see here, there is a green options for the port. So you need to first click over here. Only a single click on this port. Now you can see a plus arrow appears like this. No need to drag. If you like MATLAB, you need to drag the signals. Just click over here, and after clicking it will appear like this. It will move as per you move this cursor. Now go to the section when to which you want to connect. And on this green port, you need to click again for connect. So like this, you need to connect. Similarly, you need to click on this green port, go to the section up to this part, then click. No need to drag. If you drag, it will appear like this. If I click over here, and if you drag, it will appear like this. So no need to drag, just need to click and then go to the section in which you want to connect, and then click onto that. So like this, you can do the connection part. Similarly, I will connect the rest of the components, and after that I will change the name for my ease of use, and then I will provide the values for this filter purpose as well as my load. Okay, so I'll just place it, do some capillaries over here, just connect it to this part. Similarly, I'll do the connection with this identity leg. Done. And now I'll rotate this voltage measurement block, and I'll connect this one and this one with this part. Just move it a little bit. Similarly, I'll rotate the capacitor over here. Place the current measurement block. Similarly, I'll rotate the resistor and rotate this voltage measurement. So I'll just do the connections over here like this. No need to drag. I'll just repeat once again. Only click onto this green port, go to this section, and then click. Simple. No need to drag and drop. Okay. So like this, I have done the connection for this part. So our IGBT leg for a single phase converter is connected, and now I'll change the name for here as ES as input. Input voltage. Click on OK, and let it be S1 or S, and change the value of capacitor. For changing the value of capacitor, if I click on this, you can change it over here. If you want to write the values in the model initialization, you can do that part. So I just rename it as C2. So I provide the values over here as C2, and then I'll change it as name as V inverter, and this one I'll provide the values as L1. Similarly, I'll provide the values over here as C1 and change the name as I out. So whatever the name you provided here will appear in the SCADA in the same name, and also the resistance value as R, and over here I change the name as V out. So all the names have been changed. Now I'll define over here whatever the values I have taken inside this C1, C2. So I'll just type over here C1 equal to, and I need to define C2 for this block. So C2 equal to, and over here I have defined L1 equal to, and over here I have defined R. So I'll just provide R. So now I'll provide values R as, let's take an example 100. L1, I'll just taking random values. 10 E minus 3 and 800 E minus 6. The 800 E minus 6. Okay, so I have done defining all the values, and now something is missing in this model, which is I have not given any control option for this IGBT. Okay. So first I'll do for the first option, which is just input for switch, means I'm not providing, I'm also not connecting any simulator. So I'll go with this option, digital input for switch. So I'll just then now click on compile. So if you click on compile, it will ask you to save the model. So I just select on desktop, give it as a name as DSU. So and it's compiled. So when compiling, it will show you the results, that what are the components you have connected, and if there is any error in the connection or defining any values, it will provide over, give you the report that there is something missing or some kind of issues over there. And over here you can see this, just a moment. So I'll just click on this load model to virtual device, because we are not connected to any simulators right now. So we need to select this option, load model to virtual device. So after you click on this device, it will take some time to load the model. And now you can see here SCADA option is available. We are on this Will SCADA section. So we are first on Will schematic window over here. Schematic editor. After we click on compile by clicking on this button, we have to redirect it to this SCADA section. Okay. So now it's taking time to load the model in virtual device. So let it get compiled. So after it gets compiled, it's open like this SCADA window. Show you open like this, as we have not defined any panel for this model. So we need to select on this create new panel. A blank page will appear like this, and we need to select these widgets. So as I have discussed, there are combo box, text box, macro, button, slider, knob, or as a name says action, you can implement this action widgets to implement any action inside your simulation, just like for controlling. Just an example, I'll just save this model also in image format, so it will be useful for me. So I just import it on image JPG format, save it, and over here in the SCADA, I'll just use this visual section. In the visual section, I'll take an image, double click on it, select the image which I have saved in desktop as DSU. So now this image is inserted in our SCADA panel. So now we can see our circuit from the starter panel, and it will be easier for us to monitor all of this. So now we'll take a slider to vary our input voltage. So we'll take a slider to vary our input voltage, and we'll do the configuration later. First, we'll select the widget. Like as the name says, as action widget, we are taking a slider for changing this, varying this input voltage. Similarly, we are taking a combo box for changing this type connected or disconnected for this contactor. And similarly, we'll take a gauge for this output voltage measurement. Just noise for output voltage measurement, and we'll take a digital display for measuring the current over here, and also I'll take a gauge also for measuring this. So all these components we have selected, and now there is an inbuilt DSO mode available over here named as capture scope. You need to just double click on it, select the signals. So I'll just click on signals, click on plus. Now we need to select the signals. First, we require this input voltage. So if you scroll it down a little bit, you can see already input voltage. Whatever the name I have provided in the schematic is already available over here. I'll select input voltage. Now I'll require this V inverter, and then I'll require this V output, and also I. Okay, so I'll just select the viewport. So now as I have taken two viewports, 1 and 2, this 2 viewport is created. If I take another viewport, so now 3 viewport is created, 1, 2, 3, and if I take another 4 viewport, so now 4 viewport is created for this 4 signals. This for viewport 1, this for viewport 2, this for viewport 3, and this for viewport 4. If you want all the signals in the one viewport, you can also check on these boxes, and all these signals would be come on a single viewport. Okay. So now all this is done. We have configured this caption scope. There is an option also, signal data logger and streaming data logger as discussed. If you want to send the data from one place to another, so it can stream the data. So I'll take a signal data logger, and I'll select a signal. Let's take an example. I'll select output voltage out, and I'll log the format file as CSV. I'll save it in desktop. Okay, so this is done. File name as signals data. I'll click on OK. Now I'll do the configuration for the slider, combo box, and also this gauge and digital displays over there. Similarly, for monitoring, we have this gauge, digital display, text display, LED. Okay, trace graph, XY graph, phasor graph for phasor monitor, also PV monitor for monitoring this PV, IP, and MPPT, and bar graph as well as caption scope as we have already inserted. Similarly, for data logging, we have this signal data logger, streaming data logger, and this is for connection serial communication between the DSP interface card we are using. And for visuals, we have this group, subpanel, text node, and image, as we have inserted an image over here for my simulation model. So either you can provide your source value from here, okay, or you can provide the source value using these widgets. So as I use the widget slider, so I'll just double click on it. Now I'll configure the slider. I'll first change its name as input voltage, and select the maximum properties and minimum properties. Let's take, I want to change it from 0 to 200 my voltage, and with a step of 10. So if I take a minimum step, that will be of 10, and then I need to go to edit code editor, because you have given the name okay, but you have not just selected the signals which you need to control. So for that, you need to go to this edit code editor. Now you want to control your source, so you need to go to this source settings, and over here you can see option as constant, arbitrary, and sine. So as for inverter, we require this constant voltage, to select constant. But if you want sine, you need to click on sine. You need to provide this RMS value, frequency, phase, and you can use harmonics, and then you need to click on insert. Similarly, if you have any different waveform you want to insert, so you need to click on arbitrary option, and in arbitrary you have the option to all that files. So as in waveform generator, we have discussed that it will save in .isg format. So these are all the files we have discussed in waveform generator, source file generator. So whatever the source you generated from there, you can directly call it like this way. Okay. So I think you get this idea. So now we'll go to this constant section. We do not require to put values over here because we are going to give the values by changing the slider. So we just select option constant, place the cursor over here in the line number 3, and then click on insert. So over here you can see it's already inserted and code for hill.set underscore source constant value input voltage value equal to 0.0. So we do not require 0.0. We need to change this value. So I need to make a small change over here. I just need to delete the 0.0 to INP. If I write INP, then it will appear like input value. So if I click on input value, it means whatever I change the slider over here will be inserted directly. So I'll just click on save and I'll close this widget. So this slider is now ready. If I make any changes over here, it will insert the voltages. Okay, so we'll see that. Now we'll configure this gauge. We'll select the signal. We are taking this gauge for V inverter, and we'll select the signal as V invert and okay. And similarly, this for our current. So I'll just change its name as I out and select the signal as I out. And similarly for this, change its name as voltage output. And over here, V out, and then click on this. So all these are configured. Now I'll configure this combo box for turning on and off this contactor. So either I can use these widgets or I can also use it from here. So I just disable it from this part. Now I'll just start my simulation and let's see what happens. So you can see there is no value, no input value, no inverter value, no nothing, and it's running in virtual wheel mode. You can see the time it's too slow because it's running in simulation mode. So I'll just provide the values over here. So you are getting input values inside. So I'm making the changes without stopping the simulation. Okay. Now I just turn on this contactor. So I'll just go to this contactor, take on software control and make it close. Okay. So now I need to provide this gate configuration for this IGBT leg. So you go to the switching blocks and I'll take the software control for this IGBT leg 1 bottom switch top switch, and similarly for leg 2 bottom switch top switch, and I just enable turn on this bottom switch for leg A and this top switch for leg B. And okay. So bottom I need to enable and top of this. Okay. So now we are getting the values because I have manually turned on the switches by getting 0 and 1. So by this way you can check the feasibility if you are going to develop a new kind of converter topology. So you can check the feasibility of that converter topology by also you can create your own truth tables using this by turning on and off by 0 1. So similarly I'll change the configuration, make it 0 again and also 0 again. So I'll turn on this top switch of leg A and bottom switch of leg B. So you can see the changes. Some kind of output is coming, but it's not accurate. So by this way you can change the feasibility. Okay. So I just remove the software control. Now I will develop a simple controller, simple logic for this one. So it's done. Now we'll stop the simulation. We'll go back again to this model. We'll change this control setting from digital input for switch. Now, one thing I was left discussing over here, start simulating, and in switching blocks, let's take an example. I'll take software control, and over here also similar software control. If I turn on three switches, like I turn on this 1, 2, and 3 switches over here, there is no error showing over here. But when you are going to simulate this on real-time simulation mode, this will definitely show error over here. So DTV error or dead time violation error for that purpose. So I just making you show the difference, that what is the difference you will get on real-time mode and what is the difference you will get on virtual hill or simulation mode. So you can see the time difference, it's very slow going on. So I just stop the simulation and develop a simple controller for that purpose. So I just change the control mode to model and click on OK. Similarly, I will select the control mode to model and then click on OK. So now I'll select a sinusoidal source. I'll take a sinusoidal source and a triangular source. So I'll take sinusoidal and triangular source and a comparator. I'll compare the signal and I'll take a logical operator for NOT and I'll take a bus joint. Like we use mux and demux, so simple. So now I do the connections similarly. Now you have seen these all are blue in color and this part is black in color. So whatever the plant part we are having will be in black color and whatever the signal processing part we are having will be in blue color. So this is the difference. So now I do the connection, change it to NOT and this is done for our two switches, one for leg, a top switch and bottom switch. The signal for top switch, the signal for bottom switch. So I'll take sinusoidal, okay, excitation rate 100t minus 6 and similarly duty cycle as 0.9 and frequency as 10 kilohertz. I'll take 10 kilohertz and now I'll again select this one. I'll copy it and paste it on the bottom sides. So I'll just paste it over here and connect it onto this. And now I'll just change the phase difference for sinusoidal. So I'll change the phase to 180 and done. So I've just done a basic configuration for this inverter leg. And now I will compile it. So now there is no need required of this turning on and off the switches because we have already provided the switching signal logics over here. So let it get compiled. Okay. It's building the model for virtual hill purpose. Okay, so model is compiled, built, and already we have designed the SCADA for this part. So I'll just start the simulation. We have provided the input value. Also, we have turned on this contactor from here. If you open it, you can see. So I'll just close it, and you can see all this output voltage come to waveforms. Okay, so this is the difference. Now I'll just stop the simulation. I'll save this panel file. I'll save the panel file as DSU SCADA. Okay, done. And now I'll close it. And now I'll run the same model in real-time simulation mode. And let's see. So if I keep on close. So okay, I'll just turn on my simulator. So I'll just turn it on. Let's check it's connected or not. So now it's showing that my hardware is connected with 402 with configuration ID 1 and with firmware ready state this. So now I'm running this model for real-time mode. So I just again compile the model over here and let's see. So I'm just compiling. This model is running on 500 nanosecond. If you see this compilation report, you will get all the details. Now it's done, and we have already saved its SCADA file. So just open it and we'll start the simulation. So over here you can see it is written as real-time mode, and you can see the time. It's neither fast nor slow. It's running on real-time mode. Okay. So the data we have saved in signal data logger. If you come to this part, just a moment. So over here, as I have saved the signals, so you can see signal data is already saved. So here you can see in the time duration, I have saved the data first. First, if there was no output, then the output was coming. As I change the switching configuration, so you can see the data. We have saved up 48 seconds. So like this, you can save the data for more than 7 days. And I'll get back again to this SCADA part. Just a moment. So now you can see, as we are not getting any output data because we have enabled this moment. Just need to close this contactor. So now we are getting the output. Okay, so it's running on real-time mode. So this is the difference between simulation and real-time simulation. Now, if you want to capture this data, okay, so you need to change this mode from scope to capture. You need to import the settings from here by clicking on this gearbox. You need to click on yes, and then you need to select the time interval up to which you need to capture. Just I want to capture it for 2 seconds. And with sample rate varying from 100 SPS to 2 MSPS, 2 million samples per second, 200 samples per second. So I select 2 MSPS. And if I click on this force trigger option, it will start capturing from 2 minute 30 seconds to the next 2 seconds. Okay. So if you want to capture it, just capture it, it will start capturing from this 2 minute 37 seconds when I click on this force trigger, and it will give you the capture results, capture data. And if you want to capture it from the initial, what you need to do, you need to first stop the simulation. Yeah, I've stopped the simulation first, and now I'll click on force trigger again, and then I start the simulation. So when I click on the start simulation after 0.0, after 2 seconds from the 0.0, it will capture and plot the data. So whenever it comes to transferring data, you can see plotting data. So this is our initial values. Okay. So like this way, you can capture the data and you can save the data in CSV format, HDF5 format, MAT format, lab, and TDMS format. You can save this data. Also, you can save this as image file. You can open this capture data in signal analyzer tool, which we have discussed earlier. Also, you can change this legend type of color, or you can change from here. Also, you can do FFT analysis. So this is the FFT analysis toolbox. Check the user base frequency, and then you can plot it. So like this, if you want to capture from the starting, you need to follow the steps. Okay. And if you want to see it in running mode, then you need to go back to the scope. So you can see it is running mode. Okay. So like this, you can do, and I'll show you one difference over here in the real-time mode. So in the switching blocks, if you click on software control, I'll just take something control for all the switches. Now you can see my controller part is disabled. I am not getting any output because my control logic has been disabled because I have taken software control over here. But if I take again this one bottom switch and top switch as one, so you are getting some kind of out. But let's see an example. If I turn on 3 switches in real time mode, what happens? So you can see dead time violation output. So this is the error or warning it will show when you are working with real time mode. Because if in real environment, if you turn on 3 switches in an inverter, it will blow up. So this is the warning we get. I just reset the flag. So now we have seen the difference working in real time mode and working in simulation mode. Now I'll change one mode for this IGBT leg to from module to internal module. Okay. So here carrier frequency is already inbuilt. I'll change the dead time period as 1 T-6. Already DTV detection is there and click on OK. So you can see there is 2 ports over here, one for enable and one for input. Similarly, I'll change the configuration over here also. As internal modulators, similar settings I'll do and then I will click on. Now the carrier is already inbuilt inside in this mode for internal modulator because carrier is inbuilt, so I do not require over here the triangular wave source or my carrier. So I'll just remove this part and I record only the reference signal. So I'll take this sinusoidal. Similarly, for my reference, similarly I'll just remove this part and record only the reference signal. And I'll connect it with the input pin of this and similarly I'll take the input pin. And now I'll change this control source of this contactor as model and I click on put. And now I'll take a SCADA input. So now you can see the benefits of using SCADA input inside our model. So I'll just connect it with this for turning on this contactor. Also I'll connect this enable port to this and also connect the input to this. So using the SCADA input, I will turning on this contactor switch. Similarly, I will turn on this IGBT leg to one switch and enable this IGBT leg. So I have provided the reference signal sinusoidal with phase 0 and this one with phase 180 degree. So I'll just compile this model again and you will see the difference. So let it get compiled. This model is running on 5-7. You see this mode. All details is already available. You can see it's written 5-7. Okay. So let it get compiled. So the model is built. Now I just again turn on my simulation. So as I have not given the SCADA input for turning on this port, so there is no output, but input is coming because we have used slider over here. So I'll click on SCADA input. Over here you can see the option where I can provide the values. Now to enable it, I need to provide 1, and whenever you enter the values, you need to press enter after providing the values. So if I provide the values, you can see the difference. Okay. So if you use SCADA input inside the modeling part, you can change the values online while running simulation. If I again want to turn it off, so I make 0, so you can see. So while running simulation, I am making all the changes. You can run on real-time mode when connecting to the simulator. You can run on virtual hill mode when you are not connected to it. So I think this part is clear. If you have any doubts, any queries, you can ask. Or if you want to repeat any part of sections, you can also ask. So you can unmute yourself and you can ask your queries. Hello.
Sudipto, there is one question in the chat box.
Yeah.
What is the difference between normal input and the SCADA input?
Yeah, that's what I've told. If you use SCADA input, then you can make the changes over here while running simulation. But if you use our normal input, like just like if I take over here a constant for my input. If I take a constant, I can't change its values while running simulation. It will be 1, okay, or 0. So I can't change this value from SCADA while running simulation. So if I take a SCADA input, I can change these values while running simulation, as you can see. If I provide the values, you can see. Also, you can use action widget to control this SCADA.
Okay.
So any further query?
No other queries, I think.
So
There is one more
thank you
query.
very much.
You can
Yeah.
see the chat box, no?
Just a moment. I'll just open the chat box.
Can I read it out for you?
Just a moment. Just a moment.
Yes.
Okay, I can access the chat box now. Okay, this software can be connected to any other SCADA such as Wonderware. Yes, you can connect with other SCADA by using the communication protocols which I have discussed, like OPC. You can use, or whatever the communication platform supported by the SCADA. You can use. Now our project is being going on from Honeywell Industries, Bangalore. They are connecting the actual SCADA of them there with Type-1 simulator using this OPC platform. You have seen what is the comparison between Hill and MATLAB modeling, because our Type-1 is developed only for electrical engineering domain, and if you have seen our library, all library is based on real-time and hardware-in-loop application. If someone have worked on DSpace or any other platform for real-time and hardware-in-loop simulation, you can face a difficulty while configuring this analog input and digital input channels, like this DAC cards. Okay. So here you can see how it is easier to configure the signal inside the Type-1 Hill by using the analog input pins or using the external controlled current source, external controlled voltage source. And also here from this output controls, you can take out this analog signal. You need to select the signals over here. I take invert, and in analog output port, if you connect a DSO on this analog output port, you can get this signal directly. So this is the difference between MATLAB modeling. MATLAB is used only for simulation purpose, but Type-1 Hill software has been developed for simulation, real-time simulation, as well as hardware input purpose. Okay. So I think this is clear. So in terms of real-time simulation, I'll just explain one thing again. In MATLAB, what you need to do, you need to first develop your model in simulation environment. Then let's take an example. If your target for real-time environment is CPU based, you need to generate that codes of that model in C. But if your target is FPGA based, you need to generate the codes in DSDL or Verilog. So C is quite easier still, but for Verilog and DSDL generating, if there is some issue in data compiling and data loading into the real-time environment, so there will be some issue in results also. Okay, so there are various issues while transferring your simulation model into real-time environment. So that's why what Type-1 Hill has done, he had offered his own software as well as his own real-time simulator. So whatever the complexity or problems you face from transferring your simulation model into real-time environment, that all complexity has been solved just using the platform of same vendor. And also, if you use MATLAB, you need to purchase every year this update license, as well as you need to purchase MATLAB. Also, you need to purchase a real-time simulator from another company, and also the software or environment of that real-time simulator you need to purchase. Also, some solvers you need to purchase. But here, software and hardware, all from Type-1 Hill, and it comes with unlimited users, perpetual license. And it is for lifetime. So this is the difference also from in terms of pricing view. Yeah, if I tell you in short how to select the Hill devices, you have seen the number of cores. If you see in short that Hill 402 have 4 cores of FPGA, we have 602 plus device in which we are getting 6 cores of FPGA, and the advanced one is Hill 604. 604 is having 8 core of FPGA. Also, we have got Hill 404, which is also having 4 core of FPGA. But instead of L402, which I have shown in the picture, all devices can be cascaded. Means, let's take an example. You are having one 602 device, which is having 6 core of FPGA. You want to cascade it to 12 core. So you can take buy another 602 plus, and you can cascade it with the 602 plus you already have. But if you want to do the same thing for 402, it is not available for 402. Rest for other devices, it's cascadable. Yeah, and also the number of converters and the number of buses you want to simulate, you can select the devices. If I think in short that one core can simulate 3-phase, 3-level inverter, okay, and 20 IEEE bus. So you can calculate according to the number of cores or device you want to select. So for 402, 4 into 20 IEEE bus means 80 IEEE bus we can simulate for 402. And as I have discussed that one core can handle means simulate a 3-phase, 3-level converter. So that means 402 can simulate 4 3-phase, 3-level converters or 12 single-phase converters. In short, yeah, selection of device varies for the size of application basically. And I think 402 is quite enough capable to split a simple microgrid, okay, with 4 3-phase, 3-level converters, enough for that. So any other queries or regarding this, Dr. Karthik M, I would suggest you that you should contact us. I'll just provide you my contact details. I'll share you my contact details, or you have got our contact details also. This is my contact details. Sorry. Yeah, so this is my contact. So for hybrid electric vehicle design, I should suggest that you should go for 602 plus. So it will be for 6 core of FPGA, and also it can be cascaded for future use. Okay. So this is my contact details, my email address, my contact number. You can contact me at any point of time for regarding this device selection or regarding your application also. You can contact, and also the pricing part. So any other queries?
If you just want to simulate only hybrid electric vehicle in simulation or real-time simulation mode, then you can choose any of the device. Any of the device is good enough to simulate your model. But if you want to make that, means if you want to connect with some smart, protocols like CAN or MOD, or also you want to develop a ECU like to communicate with other systems, then you need to go select the 404 or the higher version of the devices. Okay. So for hybrid electric vehicle or plugged-in hybrid electric vehicle, all the kind of electric vehicle examples, you can select any one of the devices. In fact, if you want to see, you just download the software. And you will find one electric vehicle example is available inbuilt. Okay. Yeah, fuel cell and battery, both the kind of sources are available in the sources toolbox. And in the battery toolbox, you will find certain options are available. Means you can use user defined also, or you can use lithium ion and lead acid, nickel metal hydride, and other kind of batteries also. Options are there. You can use. And in sources, you will find fuel cell also. Means you can use that according to your requirement, configure them and utilize them. Okay. So this is our inbuilt electric vehicle example is available with charging station, and in this example, you will once you compile this model, you will find that vehicle to grid and grid to vehicle, both the operations are both the cases are developed into this model, and also distribution type of load is also used to connect with this setup. So you will, the link is provided for you to download the software, You just download the software and the license, and after that, explore this example. You will find a lot of things inside of this example.
Yeah, a lot of papers are already available in Tycoon website. If you go to this documentation section, there are a lot of papers available according to your application. You can search and you can go through that also. So I would like to thank Dr. Prashant for inviting us to deliver this webinar session. And there is any queries, you can contact us. Already we have provided our contact details. You can connect to us on LinkedIn also. So I think Prashant sir, I think
Yes,
there is no query left.
thank you. It was a very nice hands-on session.
Yeah,
Very nicely
definitely. I think
explained with the circuit also. So it will help us, all the faculty members, to enhance the course delivery in the electrical division or electrical engineering. Okay. Uh,
so. I
you're
think there
sharing
is
something?
there is a query that claim that this experimental result will publish transition paper. Yes, definitely you can publish this in the transition papers. And right now, mostly they refer for this hardware in loop publication and real time based publications. So if you check on, you can see, and there are a lot of transition papers, journal papers already available in our TypeMail website.
Okay.
Okay, if you go to it, you can see all
All
the
these
details.
published, all these are on electric vehicle technology, and all these are published using Typhoon Wheel products.
Okay. Okay.
So you can
And there are
explore.
lots of papers from India also and
Okay.
worldwide.
Yes, yes.
Very
So
nice.
you can explore. Typhoon type. That's the first one. I'll just show you from where you can get the papers. So just go to this resources,
Resources,
download. Sorry, uh,
documents,
just
resources, documents,
yeah.
and publish papers.
And, so here you will get list of
Year-wise
papers
papers.
which are published, like year wise and date wise, and from which universities and journal, on which journals, all there. So you can get this one.
Okay. Okay. Very nice. Very nice.
Hmm.
Yes.
In this year, a lot of papers are published from India. Two papers from KNIT Sultanpur, one paper from ISC Bangalore, and means
NIT Suratkal,
NITK Suratkal is
but
also there. No?
IIT
Surat,
BHU, NIT Uttarakhand, NIT Patna is there.
Uttarakhand, Patna, a lot of Indian institutes have published their papers.
Okay. 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 Fine. Fine.
Okay, so I
Yes.
think this is good enough for
Yes.
these two sessions, and means letting you know all the things about the software is a very difficult in only 2 hours or 3 hours,
True. True.
and sometimes it will take 2 or 3 days to only discussion about the software and the tools and the things are related available into the software and the related simulator and other things.
Yeah.
So
Yeah.
I hope you all got a glimpse of this product, and hope you all are enjoyed these two sessions. And whatever the queries you are having in your mind, you can contact Prasant sir, or you can contact directly with us also,
Yes.
or you just we can means make you learn about this one on the one-to-one basis using TeamViewer, AnyDesk software, and the software is open source with general license. So with this tool, the simulation is absolutely free.
Yes.
Okay. For real-time simulation and hardware-in-loop simulation, you need to do just have a Hill device. Okay. And for hardware simulation also you need a Hill device. But the simulation is totally open source. Anyone can download, any student, any faculty, any engineer, any person can download this software with basic license. You just need to provide your personal information. And a lot of labs are also developed using this tool, and a lot of universities are also using, like in South. Amrita University is also using their NIT Surat, and a lot of institutes are using and successfully working. Not only means, and a lot of universities are using without having Hill device this product. Okay,
Okay.
so if you want to go for only simulation, then you can download this software. You can use the freedom of this software for your class teaching, and also in-depth, in-depth exploration of your technology in your research into using this tool. A lot of
Great.
things are, you just go through that and explore that, and wherever help required, we are available. So if you need any kind of help to develop labs in your institute, or if you find this tool helpful for your research and you are finding difficulty, you can connect with us and we will help you out thoroughly.
Yes.
So thank you, Answer, for
Yeah.
providing this platform.
No, it's
Introduce.
a very fantastic one. Thank you, Shashank. In future, we will try to connect to you, and we will have a full-fledged 2 or 3 days
Thank you.
sessions for all the electrical engineering background faculty members. Okay. Thank you very
Definitely,
much
definitely.
for the wonderful session, and a lot of information we have gained from this session, and hope all faculty members use this tool in delivering their courses also. Thank you very much. We'll connect again
Thank
some
you.
other time after a few days. Okay.
Definitely,
Yeah.
definitely. We will. And one more thing is, one more announcement for all the participants.
Yes.
Those who wish to attend the online training sessions. So we are continuously running online training sessions and internship programs. So for more information, they can connect us on LinkedIn, or they can explore, send a mail,
Yes.
and we will share our means online training program, so that they can explore for in explore in detail.
Yeah.
Okay,
Yes.
and
Yes.
there we are giving hands-on sessions on day basis, and minimum 5 day program is there, and maximum 4 weeks program is there. So a
Okay.
lot of options are there. You can opt anything for you, or you can ask us to arrange online training program for your institute for 5 days or 10 days. It depends, and many things are there. So thank you, sir. Thank you very much, and thank you all participants to attending this program. And it's one of a kind of program which we need to have. And during this lockdown period, whatever the technologies we are having around, we need to at least we need to have idea. So thank you, sir, and a great day. Have a
Yeah.
good day. Have a safe day.
Yeah. Thank you. Thank
Thank
you,
you.
Shashank. Thank you, Sudipto. It was a very informative session.
Yeah, thank you, sir. Thank
Yeah.
you very much.
Thank you very much. Okay. Good day. Bye.
Thanks.
All the participants, we are going to have our next session at 3:30 p.m. Uh, the introduction to Opti system, and it will be delivered by Dr. Ahmed Atis. He is the vice president of OptiWave uh, Canada. So the session will start at exactly 3:30, and it is based mainly based on the photonics and optical fiber communication. Thank you, and see you at 3:30. Yes, sir.
Perfect.
It's visible, sir.
Okay. Okay. So I just want to double check, and then we go here. Okay, perfect.
Yes.
So how is the workshop, or I'm not sure how we call it.
Sir, it's going fine. Uh, Around 300 participants have registered from
Okay.
different background.
Okay.
So almost on an average, every session we had around 75 participants
Okay.
related to specific to the branches.
Okay. Perfect.
It's good, going on good. We have another 2 more days, and most of the faculty members are looking out for your session, because
Okay.
we don't have any software which we are introducing it to the optical fiber communication. In engineering
Perfect.
course, we have optical fiber communication, and
Okay.
normally it will be a theoretical course what we deliver. But
Okay.
I think with this, they may start using this optic system
Yeah.
and give some good demo and enhance the knowledge of the students also.
Yeah. Perfect. It's actually there is something called OptiPerformer
Yeah.
software which is attached to this one, and you can use it for experimental kind of demonstration,
Okay.
virtual experimental demonstrations. You can teach as well, kind of lab,
Okay.
virtual lab using
Okay.
the OptiPerformer. Yeah.
Okay, sir.
I didn't mention it. If I knew about it, I could have added to
Yes.
the presentation, but I will mention it just briefly, maybe.
Okay, sir.
Yeah. Okay. So how is gonna start on time or?
Yeah, on time, sir. Another 9 minutes we have. Exactly at
Yeah.
3:30 we will
Perfect.
start, sir.
Okay, and then we have 2 hours for this presentation, or you are flexible? I'm not sure. So I can relax during the presentation, or I have to be precisely in 2 hours.
No, no, not necessary, sir. Not necessary.
Okay.
As per your
Okay.
convenience, you can do it and finish. No issue.
As you know, this is 6 o'clock in Ottawa right now,
Yeah, okay, sir.
so it's too early for us. It's
Yeah.
still the morning is
Yeah,
didn't
I
start.
understand, sir. I understand. And thank you for
So
accepting and making
no
yourself
problem.
free for this session, sir.
No problem. It's my pleasure. Actually, we are happy to participate, and I'm not sure this workshop is usually yearly workshop, or it is like because of the pandemic happened.
Correct.
It's because of the pandemic. It's not a yearly thing.
True, true, true. Actually,
Okay.
I had planned it for the students, but due to this pandemic, we could not have it. Actually, it was scheduled in the month of April itself, and since everybody went for the holidays, and we could not have it. And I thought, I went through a few of the experiments I could do it on this on the trial version, and
Okay.
I found it very interesting. And the people from the photonics or optical fiber communication who are handling electronics and communication faculty members, I
Okay.
felt this will be a very useful for them to get
Okay.
it done, a
Perfect.
small mini projects type of things, or they can do some final year projects also.
Yeah.
So
Plus, they can do research projects as well. Like, I mean, you know, there's lots of publication has been using OptiSystem or OptiWave software
correct, sir,
in
correct.
their, yeah. So it's a very good tool, actually. I'm gonna give some kind of introduction about the different products, and then go to OptiSystem mostly.
Okay, sir, no problem, no problem.
Yeah. Perfect. Dr. Prashant,
Yes, sir.
can I give you my cell phone number in case the connection broke or something?
Yes, sir. Please, sir.
You just send me a message. It's 613 area code 613
Okay.
981
Yes, sir.
3577.
Yes, sir.
Just send me a message so I can know that everything is fine in case something happened. So I can and
WhatsApp
let you
message
know
I'll
where I
send you,
stop.
sir.
Yeah, yes. Sorry, again?
A WhatsApp message I'll send you.
Yeah, that's perfect. That's perfect. It should be okay. One more thing is for the presentation,
हाँ, sir.
the size of it is too big, so I couldn't send it today by email. So I'm
Okay.
going to send you a link sometime today or maybe tomorrow, so you can pass it to all attendants.
Yes, sir.
Yes,
Definitely.
and the other thing, if you don't mind, like attendance emails would be nice if we can get them, so we can send them updates and all these things of
Yes,
the
sir.
products.
I'll share. I will share, sir. I will share with you.
Perfect. Thank you. Did you send a message or not yet?
No, no, not yet, sir. Not yet, sir.
Okay, just maybe you can try it just for a test.
Sir, can you just pardon me your number, sir? The 613 is the area code.
Area code. So you have to put first
61.
one. No. First is the country code,
Okay.
and then 613
Yes.
981
हाँ, sir.
3577.
Yes.
Okay, I got it. Thanks.
Good. Yes.
Perfect.
Sir, shall we start?
Yeah, I'm ready to go. Yeah.
Yeah. I'll just introduce you to the participants and then you can take over, sir.
Perfect. So screen is ready to go, right? So I don't need to share
sir.
anything.
Yes, sir.
Perfect.
Yeah.
Perfect. Thank you.
Good afternoon, one and all. Welcome to the session 3 of day 4 on International Skill Enhancement Program on Programming and Simulation Software. I'm very much privileged to introduce our today's guest speaker for the session, Dr. Ahmed Atiyah. He is a vice president at OptiWave Systems Incorporation, Canada. He received his Bachelor of Science degree in Electrical Engineering from Yarmouk University, Jordan. MSc degree in Electrical Engineering from Jordan University of Science and Technology, and a PhD degree in Electrical Engineering from University of Ottawa, Canada. He is currently working as an adjunct professor at School of Electrical Engineering and Computer Science, Sunlab Core Facility, Ottawa, Canada. He has contributed more than 100 technical papers in different refereed journals and conferences. He holds over 25 issued patents and patent pending. His current research interests are in the fields of optical fiber communication systems, including optical fiber characterization, optical amplifiers, non-linear fiber optics, and optical communication transmission systems. With this brief note, I request Dr. Ahmed sir to take over and continue with the session, sir. Thank you.
Thank you very much, Dr. Prashant, and good afternoon, everyone. Good morning in my time. But there is few people actually watching here from Ottawa and from Japan even. So hello to everyone. Today I'm going to talk about, give you an introduction about OptiSystem product software. And meanwhile, at the beginning, I'm going to give you some more information about OptiWave and about the products we offer, and then we concentrate on OptiSystem. Okay, so just like a few words about OptiWave. OptiWave established in 1994. And it's centered in Ottawa, Ontario. OptiWave offer software basically for designing, optimization, and simulation of different components, links, and systems, as well as networks, which can be done using distinctive components. This kind of software will give you an advantage of shortening the production time for the product when you do use these kind of simulation tools, as you kind of investigate the system before a component, before you kind of manufacture it. That will give you an improvement in the product quality, because you would be able to study the different effects and variation in the parameters of these components and their influences on the system design. And as well as going to basically give you some kind of cost-effective and enhancing productivity of your design and your product at the end of the day. So OptiWave software has been licensed to more than 100,000 industry-leading companies, universities, research institutions, and governmental institutions in over than 75 countries. OptiWave software can the customers of OptiWave are in different fields of component manufacturing and module suppliers. Like some examples here. Like Viavi solution, which is used to be JDS Uniphase, Oclaro, Corning, 3M, LG, Oki, and in optical telecommunication equipment provider, this is kind of example list, like Nokia, which is now Alcatel-Lucent, Huawei, Mitsubishi, NEC, Ciena, IBG Photonics. And in the telecommunication service providers, this is some examples like NTT, AT&T, Bell Canada. In the national defense contractors, we have customers like Lockheed Martin, like Raytheon, Boeing, BAE Systems, Fells. And in a non-profit organization, we have, this is a sample of the customers using OptiWave's product, like Sandina, National Laboratories, National Research Council, and Communications Research Center. Universities, we have many universities over all the world, such as like Harvard, MIT, Stanford, Ottawa, Toronto, Shanghai, and many other universities. In this slide here, I'm going to start talking about the product line of OptiWave. So we have the product lines are categorized into levels. System level, where we have two products offering, which is one of them is OptiSystem, and mainly we're going to concentrate on it today. But the other product, which is called OptiSpice, and can do optoelectronics circuit designs. And then we have component level software, which is like OptiBBM. You can do waveguide design, and in OptiFDDT, this is the finite difference time domain designs. And for mode solvers as well inside it, we have OptiFiber. You can design fibers in it, and OptiGrating, you can design different types of gratings software. Recently, we have a new product which is going to be going to the market in a couple of weeks, and this is called OptiInstrument. This software is capable of communicating with instruments physically or remotely, and you would be able to set up parameters of the equipments with it. You can automate testing and characterization. You can look and view the signals generated. You can extract this data, save it, and for post-processing, and then you can integrate these instruments with photonic and system simulation tools. Okay. In here, we're going to talk about some of capabilities of the new software here, which we are excited to introduce to the market. The OptiInstrument, it can execute single or sequence of SCIVI commands. So this is the way of communication with the equipment. Now, whatever the communication port, which the instrument has, USB, you have GPIP, you have Ethernet, whatever the communication port, we can communicate with this equipment through the SCIVI commands. And these copy commands can be saved in XML files, and you can load them, you can save them, you can manipulate these files. The commands can be flexibly placed in the certain bins and in the GUI, and you can arrange them in a proper way. The software can generate Python scripting and for the commands, and then you can execute them within the GUI or externally in the command prompt, let's say, or PowerShell of separately. It has this single signal viewer, so you can view the signal generated by the equipment using this GUI, as well as you can save this data in a CSV file. And as we said, we have also a built-in Python script editor within the GUI. Okay. Now, the purpose of this software, again, is we can communicate with this equipment and control it either physically close by or remotely. Okay. Here, we're going to talk about the simulation capabilities of OptiWave software. The first thing is, in the terms of optoelectronic circuits, is like OptiSpice, which is mainly the software used for that. You can design ring resonators, you can design laser drivers, optical interconnects. In the optical networks, OptiSystem is OptiSystem is the optical network can be used for designing optical networks. Dr. Prashant, is the voice, everything is fine?
Yes, sir. Sir, it is fine, sir. Fine.
If you could please mute other participants. So
yeah, I have done it, sir.
Distracting.
Yeah, I have done
thank
it.
you. Okay, so for optical networks, OptiSystem works perfectly there. We can design projects for optical time division multiplexing for symmetry rings, SDH, CWM system, DWM system, passive optical network, optical code division multiple access, You can design using OptiSystem as well different types of amplifiers using EDFAs or different rare dope material. All the types of rare dope material is available in OptiSystem. You can use it for designing the amplifiers. We can design SOAs. We can support Raman amplifiers. And you can have hybrid amplifiers as well. You can optimize the gain flattening filter for the amplifiers, support parametric amplifiers, fiber lasers. You can do all of that in OptiSystem. Modulation formats, OptiSystem can support all these types of formats, from return to zero to carrier suppressed return to zero, dual binary, dual phase shift keying, differential phase shift keying, quadrature phase shift keying, dual polarization, QBSKs, all types of QAM, all types of PAM modulation formats. In wireless communication, we support Li-Fi channels. We have components which supports designing and characterization of the channel. We support satellite communication, free space optics, visible light communication. We have projects to support 5G backbone in the physical optical layer. We have in OptiSystem as well capabilities to design FPGs for sensor applications. We support OTDR, PHY OTDR. And in the component level, we, as we said, is the finite difference time domain FDDT, OptiDT software mainly used for the electric metallic grating photonic crystal nanoparticle design. And for beam propagation methods, we can design couplers, splitters, multi-mode interference couplers, modulators, multiplexers, arrayed wave guides. In optic grating software, we can design filters, different types of fiber grating reflectors, gain flattening elements, dispersion components, compensators. Optical fibers, you can do the fiber design, fiber characterization, for single mode, for multi-mode, for fiber sensors applications. Mode solvers, we have different types of mode solvers for polarization splitting with holy fiber. We did a few presentations recently on photonic crystal fiber for sensor application and super continuum generation using the mode solvers, OptiMode. And then you can design lots of stuff in OptiWave software. Something which is also we did recently with OptiSpice, we managed to integrate OptiSpice with Tanner, Mentor graphic software for photonic integrated circuit design. And the simulation, we can, like users can allow the photonic simulation from mask level to the final simulation and simulation of the circuit. You can use L-Edit, S-Edit, at T-Spice and OptiSpice software engine with the whole stuff. This will allow rapid prototyping of photonic integrated circuits and the OptiSpice modules libraries. The drivers and symbols are added to T-Spice in Tanner right now. OptiSpice integration with Tanner, the advantage of it and the differentiation from other vendors is we can do optics and electronics simulation in the same platform. You don't need to migrate from one platform, from let's say electronics to optics or optics to electronics. You can do it in the one platform. Okay, so here we're going to talk more about OptiSystem applications. I gave you some kind of brief of it previously in the previous couple of slides, but here we're going to talk more about the OptiSystem applications in the wireless communication. As we mentioned, you can do these different types of support. In microwave photonics, we have large libraries from lasers, modulators, filters, detectors, amplifiers, signal processing, which enables the microwave photonics. And we have also something which is very useful in OptiSystem is the visualization library, which is basically instruments capable to view the signal in the time domain, in the frequency domain, as well as spatially and in binary or memory levels. We're going to talk about it today during this presentation. OptiSystem as well supports LiDAR systems, and we have different versions of projects we can use to support that, from the time flight measurements to phase shift measurement arrangements, and from frequency modulation continuous wave schemes. So all of these schemes are implemented in example library on OptiSystem. Usually we give this on request basis, okay? So it's not in the example library currently, which I'm going to talk about it later on. Okay, now in terms of sensor support in OptiSystem, we have different fiber Bragg gratings sensors where users can use the component as temperature sensor or stress or strain sensor. We also have a PHY-OTDR component which can be used for simulating a system to sense vibration at different location in a fiber. So you can sense many vibration at different locations. We have the gyroscope examples in OptiSystem, and also we offer a component which does the OTDR simulation, where you can concatenate different types of fibers with different numerical aperture, different attenuation, different connection between them, and then all of that you can get the design of the system, how it goes. We have a digital signal processing component which enables users to do electronics compensation as well as controlling the compensating for phase, carrier drifts, and all of these things in OptiSystem examples. In terms of coherent modulation systems, OptiSystem supports all types of QAM, all types of PAM, MPSK, and etc. So OFDM and other schemes. We have lots of examples I'm going to show you later on about these kind of where you locate these examples and then how can you use them. Okay. So OptiSystem software, when you go to OptiWave website and go to register on the account, you register in your account on OptiWave's website. Once you register, you can go inside your account, and then there you can download a 30 days free license of OptiSystem software. Currently, we have OptiSystem 17 available, and in about 3 to 4 weeks, we're gonna release 17.1 version, and 17.1 has more components and more solutions in it. Now, once you download the software, you're gonna have the software installed under this library here, program files, OptiWave software, and OptiSystem. And there you're gonna find different subdirectories, bin, components, documentation, and libraries. In the bin here, you can see executable files and help files. In component library, you're gonna see OptiSystem component parameters, and then the documentation, you're gonna see support documents where user manuals, component data sheets, and all of these things, and libraries, which are OptiSystem libraries. So I'm going to show you here the location of this software. So as you can see here, this is the C drive and program files, OptiWave software and systems, and this is the library. So if you click on it here, you're going to see the executable file. Usually we include OptiSpice into the OptiSystem software, because there's you can load OptiSpice netlist or projects into OptiSystem, and then you can run them. If you go to the components here, you're going to see data files. We're going to talk about this later on. This is data file which you can this is from different vendors in the fibers, have specifications for the either attenuation or for dispersion or nonlinear refractive effective area as function of wavelength and so on. So this is like some data can be used there. You have also different types of fibers here with specification from different vendors already ready to go from different types of fiber from different vendors. You can load them into the fiber component and use them. If you go to the documentation here, you're going to see these are the files, which is PDF format. If you double click on any one of them, you can see the component library, getting started, global parameters, setting, release notes. So here you need to read the release notes usually because it describes what is new in the release version. Like for example, at this time it's 17. You can see what is there. You have some tutorial on the C++ component, on Python components, and the tutorial examples, different tutorial examples on the Opti system, just to give you a heads up start to how to use the software. And then if you go to the libraries here, you're going to get the drivers of the different components. Okay. So to move on, now the example library. This is the key thing which we can use as a guidance for your projects and to build your projects is the example library. And the example library here, it's located usually when you do the download of the software, it goes directly into the documents and then the directory for this sample example library. You can control where you want to save the files. However, it's recommended to be there. Now, if you look at the example library here, this is the directories for example libraries under documents. And then the examples in Opti system, we always create new examples, which are based on either experimental setups or published work, simulated papers or experimental papers. So if you double click on each one of these category of these directories, you're going to see subdirectories here about the different topics. For example, we are talking about advanced modulation. You have here QAM, PSK, OFDM, PAM, and so on. So if you double click on each one of those, you're going to see either few example or whatever the number of examples. Here, for example, a QAM, you have 8 QAM, 16 QAM, up to 256 QAM, and so on. So every directory here, you have different types of examples. For example, sensors library here, you can see FPG sensor ladder, OTDR, FI OTDR, and so on. So you double click and so on. So this is very good resource for Opti system users. To sometimes, if you wanted to build something, you can look at the example and get some kind of guidance how to use the components, the parameter setting, and so on. So we're going to talk about this in more details later on also, how to set the parameters and so on. Okay, so to move on. Now we're going to talk about the documentation. As we said here, we have the PDF files which we showed you. There is also CHML files. These CHML files enables users to access the documentation from the Internet Explorer. So you can get these files as well from the same files, which is a PDF file from the Internet Explorer. And as we show you here, the locations of these files and so on. Okay. Now we're going to talk about Opti system software. Once you download the software, you're going to go to the GUI, which you're going to see it here, and you're going to see the icon for Opti system here. You click on it, you access the GUI right away, and usually the Opti system has the GUI. As you see here, we have a main layout here, which is the main canvas where you put your project and design your project here. And this is different Dockers we have here. The Dockers here, we have one of them, you can access them from the view or from these icons here. One of them is the component Docker here, which is mainly, as you can show here. Let's go to the example. We can go into here. So if you go, this is the component Docker here, which has all the components categorized in different categories based on the application. This is visualizer libraries where you have all the instruments in the optical domain, electrical domain, binary, memory. If you click on it, you're going to have a component like optic spectrum analyzer, power meter, polarization analyzer. And we offer also dual port components. So you have dual port spectrum analyzer, optical spectrum analyzer, and so on. So this is applies for the different types of signals as we see here. Now, if you go to the other Docker here, which is, you can expand it here, it's called project browser. And all the components in the project which you have here, it's listed here. You can expand, and then you can see different setting parameters here. The tree can show the parameters of every component. So for example, this is a global parameter, which you can access it for the from this here. We're going to talk about it later in more details, but if you go into the other components here, this is CW laser 1, CWD laser 2, and so on. So every one component here is right away into the project browser. There is another two Dockers here. You can access them here. It's called description Docker, which is give you here the layout of parameters, the parameter which is set in this project, and then the other one which is called progress Docker, which is when you execute the project, you can see the progress coming in here. So you can disable them and enable them from here, as you can see. Okay, so before I go, it's actually the canvas, as you see, or the main layout here. You can have 3 tabs in here, which are the layout, the report page, and script page. We're going to talk about each one of those in details later on. Okay, and we talk about these visualizers components. Now, one important thing in OptiSystem is the release notes, which you can get them typically from the toolbar here at the top of the GUI and under help. So you go help, about OptiSystem, and then you're gonna get this pop-up window here. In this window, we have this information about OptiSystem version, about the build number here, and about the contact information and so on. So as you can see here, you can access it again from help and then about. Now, if you can see here, you can access the getting started guide. If you click on it, you can access the manuals right away for getting started and user reference guide. About OptiSystem, this is version 17, the build number is 1730, and so on, okay? Okay, so now in OptiSystem, we have, as we said kind of briefly, the different types of signals supported, which we support optical signals, electrical signals, binary signals, emitter signals, and the color coding of each, like we have color coding for each connection, as you see here, between the components. So this component is a pseudo random bit sequence generator, so it generates bits. Binary signal, the color code is dark red, as you see here, red here, and dark red for emitter signal. A green signal would be optical signals, and the connection for any type of signal, because some components like this one here is called fork, can be connected to either electrical, optical, or emitter, but doesn't matter the type of signal. Usually, if you want to connect optical signal to electrical signal or binary signal, doesn't work. So we try to connect between this component and this component, it's not gonna work. So if you can see here, so if you can take, let's say, for example, a component, just I'm going to start from scratch. This is a new layout, and then you take transmitter library, optical sources. This is a laser. Now, laser output is, if you double click here, you get something called component properties, where you set parameters here. If you go help here, it gives you the data sheet of the component. Now, as you can see here, the component description about the ports tells you the port, it is type, output port for laser, doesn't have input port, and the type of it is optic. So now if you connect it, you try to connect to this component, let's say a visualizer here, you take optical visualizer, optical spectrum analyzer, we have a capability to have something called connect on fly. So you have direct connection, but let's say if you wanted to bring an electrical visualizer, let's say you have an oscilloscope. Oscilloscope here, it doesn't connect. Why? Because this is optical, this is electrical. And then you can try to connect here, you can get here no connection possibility, because this kind of sign to tell you that you have no compatible port between input and output. So this is something, it helps you when you do the connections. Okay, so I'm gonna close this one. Okay, so different types of signal as we mentioned here, and the coding of each type of signals. Okay, now in terms of also signal handling in OptiSystem, beside the types of optical and electrical and so on, the signals we categorize them into also sampled signals, where the signal can be sampled into many samples. This applies for all optical signals, electrical signals, spatial signals. We have something called parameterized signal, so where we don't have samples representation of the signal, only we have one sample representing the signal, and this is for some applications. What's happened is all these samples of the signal will be represented by a single sample in the time domain or a single sample in the frequency domain. This is mainly used for some application, like for example, quick characterization of amplifiers, gain, and so on. So you can use this parameterized signal. I'm going to show you how to use it. And then there is something called noise bins. And noise bins, they mainly used to represent the noise in the signal. If you look at, for example, ASE noise or something like that, you can represent it through the noise bins. And usually noise bins are characterized by power spectral density. So there is a parameter which is the bin bandwidth or bin width, and then the power spectral density, and then basically you take, if you want to find the average power, you need to multiply the power spectral density in that bin, and then integrate over the whole bandwidth. Okay. Now, sample signal, as we said, we use sample signal for all optical signals, for all electrical signals. Now, when we represent the optical signal in samples, it's usually represented as a complex signal, optical field, and in two polarization. So you can have single polarization of the signal or dual polarization of the signal. You can control it, and you can launch any polarization of the signal into the simulation. So this is something which can be represented in the signal field for optical signal, but this is done in the all optical signal, or most, like 99% of the simulation of optical signals is done in the frequency domain. There is some components, they do it in the time and frequency domain. Electrical signals, same thing, samples, electrical sample signals, they are represented as a complex sample signal, and it's always done in the time domain. And sample signals also for spatial representation, mainly used for multimode components. Now, when two or more sample signals are combined, okay, when two signals are combined, their individual samples will join into a new sampled signal. If the bandwidth are overlap, if the bandwidth don't overlap, each one they can be kept separate. Okay. For parameterized signal, as we said, it's a single sampled averaging of all these samples representing the signal in the time domain or frequency domain. For optical signal, it's for in the frequency domain, electrical signal in the time domain. And when you simulate parameterized signal, this enables very quick, as we said, representation for calculation, mainly in EDFAs and in some power budgeting of the WDM systems. The noise bins here, just to show you the noise bins here. So for example, if you have a signal, this is the signal representation, and this is the green color signal here is the noise bins. The noise bins basically is having, as I mentioned, has certain width here, and then the power spectral density in here. If you want to get the average noise power, you need to multiply power spectral density by the width, and then integrate over the whole bandwidth to be able to get it. Okay, so there is something called noise floor in the signal, and the noise floor, for example, in a CW slide here, as you see, the channel center is represented in here, and then the noise floor is somewhere in here. You can control where you wanted to measure the noise floor, and there is a parameter in the global parameter setting where you can control where the control of the noise floor. Sometimes if you want it, let's say, within certain width, and you can set it up through the global parameter under signal tracing tab. Okay. Okay, so in terms of lasers, we can generate, as you saw a few minutes ago, the laser has a certain noise floor, and you can generate this random noise and select the types of random noise. There is many seeds in the random seeds in the OptiSystem software, which can generate the noise in OptiSystem. And there is an index in that I can show you here. If you go, you double click on the component and you go noise. Here you can control the noise bandwidth and all these things. And this is the random number. So there is generate random seeds. You can have it true or false. And then if you have it false, you can choose what number of random seed you wanted to choose. So there is different, each one depends on different types of seeds programmed into OptiSystem software. So this is something which you can generate. Now, if you choose the random seed off, and then you choose certain number here, every time you generate this noise signal, let's do it here right now, as actually I have an example in here. So this example in here, these two lasers here, they are, as you see, we have generate random seed selected true. And this is one, both of them is the same wavelength, same thing here. Seeds is the same. But however, these two lasers, the selection is off, okay? And what's happened is, whenever you calculate this kind of lasers, when the random seed is off, it means you're gonna generate exactly the same noise every time. Not in a random fashion, but it's always the same. So if you run the calculation here and you look at these two spectra, this is the same, the first one. Okay. So the first one here, you can see the two lasers have different. So if you repeat the calculation again, as you can see here, you're going to get different, every time you're going to get different lasers, different seeds of the noise here at the background. So every time it's different. However, if you do the calculation on the other one here, as you can see, it's exactly match. There is, every time you repeat it 100 times, it doesn't matter. It's always, you're going to generate exactly the same signal. There is no variation in the signal because you disabled the randomness generation. It's always generating this kind of random seed at 0 level, and so on. So you can put 1, 2, whatever the numbers you have. Again, you can read it from the data sheet about the range of these seeds. Okay. So this is talking about the random seeds and about these levels. We talked about it and the setting. Okay. So now in terms of components, some components, they generate noise in them, and some components, they don't generate noise at all. So all pulse generators produce clean electrical signal. There is no noise added to these signals. Photo detectors, for example, you can control the noise generated in them. And there is different types of noises there. There's shot noise, thermal noise, beat noise, and different types of beat noise, signal ASE, speed noise, and so on. So you can set these parameters in the component, as we're going to show you later on, but it's something which you need to have in mind when you do your simulation, to include what type of noises you wanted to include. Okay. going to start now on something called the global parameter setting, which when you double click anywhere in the project here, you're going to open this window, which can resize it as you see here. And the tabs here, you have simulation tab, signal tab, spatial effects, noise, signal tracing. Okay, and then in each one of these tabs, you can control the parameter settings. So for example, in this tab here, we have simulation window. You can control the simulation window to be set by the bitrate. So this is the bitrate. So you change the bitrate. Let's say here it's 10 gigabit per second. If you put it 20, you can look at the time window here in the gray color. It's changing because it's the simulation window is set by this bitrate. However, you can set it by time window. So you can have access to the time window here. You can have changed the time window. So if you change my time window, then other parameters has to change to make sure that within this bitrate, the time window calculation is proper. So this is something is done internally, but you have the control to control the time window simulation using the parameter here, or you can control it using the sample rate. So sample rate here, as you can see, this field sample rate right now is 640 gigahertz. I can set it, let's say 320, and then eventually parameters here also changes to adapt to the set bit rate and time window plus the sample rate. So the user can choose which parameter affects the setting of the time window. Now, the time window determines the resolution first, plus like other parameters. Like for example, here we have sequence length. Sequence length here defines how many bits is going to be generated within this time window here, and is how many samples per bit here. So let's say in this setting right now we have 2048 bits. Each bit has 16 samples. So total number of samples here, you have 32,768 samples. Now, based on the time window, you can have the delta T, which is the total time window divided by number of samples. And the frequency window is, as you see, it's equals to the sample rate. So sample rate here represents the frequency window. So the resolution or the delta F in this frequency window would be the sample rate divided by the number of samples. These parameters are interacted with each other to make sure that this whole calculation make correct and make sense. One thing which you need to make sure when you do the calculation is sometimes the sample rate had always to be more than the bandwidth of the signal to verify the sampling theorem. This is something which you put in mind. Usually when you choose the bits area, for example, if I go to let's say 256 bits, you can see here the time window changes. If I change the samples per bit here, let's say 32, as you see the sample rate it changes, and so on. So all of these parameters are interactive. Another parameter is very important, and usually with advanced modulation is called symbol rate. Symbol rate here, if it's very like most what we find out that most of the projects being designed, users forget about this parameter. When you have symbols transmitted in the system instead of bits, you have to make sure that the symbol rate is correctly set. So for example, if you have a QAM, which means 2 bits per symbol, you need to divide the bit rate here by 2. So if this is 20, this is 10 gigabit per second, and so on. Now, if you have dual polarization, there is another issue. So if you have dual polarization, then the bit rate has to be divided by 2, and then you look at how many bits per symbol. So this is, if I have dual polarization QAM, this should be 5 gigabit symbol or gigabaud. Okay. Now this is another parameter. There is a parameter here called reference wavelength, and this reference wavelength, typically, most of the components are specified at certain wavelength, and the wavelength setting is inside the component. However, if there is no set parameter in the wavelength for that component, this parameter will be used. So If the component has its own reference wavelength, then it will override this parameter. If it doesn't, then this parameter will be used, which means the parameters are specified at this wavelength. Okay, and here we have something called export results to file. Now, if you check it out here, this is version 17. We did in 17.1 more modification where we give access to save the results of the components as well as parameters into a CSV file. And the CSV file, you can choose it in certain location, and then once you place the CSV file, do the calculation. In 17.1, you will save the selected parameters of the component. So if you see, for example, here in the laser, you can select any parameter you want to save. And in some components, let's say, for example, if you click here called component result, you can select it, and this would be saved in the file. So if you press OK, then as you see here, it will be displayed. And this component, when you check this field and you save it in certain position, you're gonna save the result of that component as well, which you select. Now, in OptiSystem 17.0, as you saw here, it's limited because only you can save the results of the components. In OptiSystem 17.1, we allow saving both results and parameters of the components. Another difference is in 17.1 also, we save the results in every sweep. So when you do, for example, sweeping of a parameter here, we allow the result to be saved in every sweep. In 17.0, only the results are saved after the last calculation. So this is a difference between the two versions. 17.1 allow to save after every sweep and after the end of the calculation, while 17.0 allows only saving after the end of the calculation. There is advantages for that. We're going to talk about it later on. Okay, so if we go back again here to the definitions which we talked about it, this is the time window here, or frequency window here, and the time window here. We have, these are the samples of the signals, and if the delta F here, it's the sample rate divided by number of samples, and delta T here will be the time window divided by number of samples, as you can see here, and then the calculation has to be preserved, as we saw the relationship between the sequence length and the bit number of samples per bit, and so on. Okay. So in here we're going to talk about something called adding parameters. So in the global parameter, here, as we said, it's used. All these parameters are used in all components when it's called in these components. So for example, this time window is for all components. This sample rate is for all components. This bit rate for all components. However, you can control it locally. So you can, let's say, for example, let's say I want the sample rate on this component to be 5 the sample rates. I can something called do script. I'm going to talk about this later on. So I can script that and make the sample rate for this component 5 times the sample rate, which is in the global parameter. Okay, but the thing which I want to talk about here is something called add parameter. So if you click here on add parameter, you can have this kind of window where you can add up in the global parameter here any parameter you want. Say, for example, I want to add a parameter called wavelength. So I write wavelength here. Okay, and then I define the type of this parameter. Is it a floating point? It is integer, boolean, string, to be loaded from a file, or so on. Okay, so choice and so on. So once I choose that, I choose also the location. So it is in the simulation tab, in the signal tab, in the spatial field effects tab, and so on. And then I choose for this parameter the minimum wavelength. For example, I wanted this parameter to run, let's say, from 1000 nanometer to maximum value, let's say 2000 nanometer. Okay, and then I choose the current value, which is, let's say, 1550. Then I define the parameter here globally. It's called wavelength. And then I come here to unit conversion, because this unit and the wavelength is now, I put it here in nanometers. So I have to choose here a unit which is called frequency. There is difference between frequency, between bandwidth, time, distance, and so on. So you have to choose if you don't want to choose unit, you can keep none. But here it's a frequency unit. Then you have displayed here the possible units you can choose from. So in this wavelength, I'm choosing here nanometer. So I put here nanometer. Okay, once I do add here, a parameter is created, as you see here. Small letter, you have to be careful to that. And I created in small letter. And you can see the current value is 1550. If I press OK, then this parameter would be saved, okay, in the calculation. So if I click here again, this parameter is already here. Now I can go to this, let's say, laser, and I can change the frequency of it. Right now in terahertz, I can choose the unit which I want, let's say in nanometer. Okay, so this is the nanometer wavelength. And then I can go here, I can do something called script. So I script it, and I can use the wavelength here, parameter. I have to write the wavelength in the same way. If it's capital, small letter, it's better to copy it and paste it here. I can do check on it, say evaluate. It means the value of it is 1550. So it means that this laser is going to take the value of 1550 at this moment. And then I press OK. Then I press OK again. Then this means the wavelength has been saved. As you see here, frequency, it says wavelength. And wavelength is read from here. Now, why we do that? This is very good feature, because if you have many components are affected by the same parameter, you can script them. So you don't need to go to every component and change the parameter there. What you need to do is just only, let's say this laser, again, I want to script it. So I do script and go here, say wavelength, and say evaluate just to check, and then OK, and then OK. Now, I don't need to go here to change the wavelength of this laser and this laser. I can go here in the global and say this is 1570 nanometers. So directly, these two lasers are coming at 1570 nanometers. So when I run here, I can see that these lasers are right now at 1570 nanometers, as you can see. So again, this is the advantage of using adding parameters. You can add up any parameter you want in here. You can add it up, and you can as well as remove it. So if you highlight this parameter, you can remove it. So once you say here remove parameter, yes, it's done. Okay, and then it means here this one I have to go to normal, and this is the last wavelength has been saved there. So I press OK, or I can change it. Same scenario here, has to go to normal. And this is the wavelength. I can, don't forget here, the unit has to be the same unit, and so on. Okay, so has to be fixed in there. Okay, so move on. So this is the process of adding parameters in OptiSystem. Okay, and scripting. Now, one thing which is also advantageous in the process of adding parameters in the global parameters, so something called sweep. As we said, we can do sweeping of parameters. Any parameters, you can sweep it. So if you go in the project again here, if you go to the parameter, you can sweep the parameter from here. There is something called mode. And in the mode here, you have, as we saw, normal, script, and then sweep. If you do sweep, then you can sweep this wavelength, let's say, between any parameters. So here, if you click on this icon, you can set up the number of iterations you wanted to do. So if I say OK, it says to me here number of iteration is 1. Now I can do the control of iterations from here, or I can control it from an icon which is somewhere in here. I have to see it. Parameter sweep. That's not active here right now for me, but it's anyway, I can do it in here if I do sweep. Okay, and then I can go from here, and then let's say about 10 sweeps. Now it gives me this pop-up window here where I give me the frequency range which I can control. I can highlight here and gonna choose the spread tool. So I can go linear, where I can add up the difference here is constant, or I can have exponential, logarithmic, formula. I can put my own formula, Gaussian. So different types of of spreading I can cause in this range. So if I say linear, for example, I can choose the beginning, let's say from 1530, and maximum, let's say 1570, and then I press OK. So here will be the range will be divided equally into 9 steps, as you see here, between 1530 and 1570. If I press OK, then the action be taken in control, and then press OK. Now, doing that, it will make sweeping of this wavelength between the range which we set here, between 1530 and 1570. So if I run here, as you can see here, you can see that this is the iteration is sweeping, 10 of them, and then I can look at the sweeps. Okay, so I can look at sweeps here from these icons here. So I can go, this is iteration number 10, 1, 2, 3, 10. I can select anyone here and I can see the lasers, or I can go downward or upward from here for all these lasers. Okay. Now, to move on. Okay. So we are going to talk about something called finding component in OptiSystem. So this is a very good feature where if you wanted to, OptiSystem has over 500 components, okay? So if you wanted to look for any components in mind, what you need to do is you go to the component library Docker here, just place the mouse and click in here, as we're going to show you in this here presentation. So double click in here. Okay, I'm going to move this into the presentation here. Okay, I'm using 2 screens. For some reason, seeing this is happening. So find component here, okay? Find component here, you enter the component name. So for example, I need laser, CW. You can do CW any word or all words, search. So you search here, all the words which has, all the components which has the word CW is listed here, okay? So when I do, let's say for example, I have here optical fiber, and then exact say all words here, it means search only the words which has the words optical fiber, not any component which has the words optical fiber. And then what you need to do is, let's say you go to this component, highlight it, double click on it, it takes you directly to the location in the component library. So what you do is just drag it here and then use it. So this is a very, very useful feature in OptiSystem in case when what you need to do is you have right click here in the component, find component, and then you can have this window in here. Okay, so now connecting components. Components can be connected in OptiSystem in as we showed you previously, something called on drop, which means when you take the component directly here, you just drop it into the layout canvas here, and then it will be connected automatically, or it's on the move. So if you move the component from here to here, it's going to be. How to choose it? You can choose it from a view in the toolbar here, and there auto connect. You have 2 options: auto connect on drop, auto connect on move, and then you can also use them on the icons on the right side here of the GUI, and you can see this is the 2 icons used for auto connect and on drop or move. Now there is other way to connect manually the ports of the components using the control. So you press on control on the computer, as we're going to show you here. So let's say if you take 2 components, let's say this is optical fiber and this is another optical fiber. I don't want to connect them right now because this is on the drop, but I want to connect them manually. So what I do, I press on control, I take the mouse. As you see here, the icon on the mouse has been changed to as a connection icon, and then you put the drag or drag the mouse into both ports which you wanted to connect, and then release the mouse and release the mouse. You should be getting the connection as you see here. Okay, then you do the connection manually, or you can do the connection on the automatically using a drop move on the drop on the move. Okay, next we're going to talk about the ports of the component. As you can see here, the component port, if you double click on the component port, you're going to have this pop-up window where you can, as you can see here, you take any component port. If you double click on it, as you can see here, this is the window comes up. If you click on location, you can change the location from top, bottom, right side, and then you can scan it here. So if you have sometimes, for example, big components, let's say I have a multiplexer. Let's say take a component here, which is maybe this here, optical sources. So filters, optical, let's say this filter here. This is the filter. I need to move it up. I double click on it. I double click on the port. I press location, and this is on the right side. I can move it a bit higher, and I press OK, and then you can go higher and lower, and you can control the placement of the port. Now you can highlight the component, let's say, and then you do something called the flip. Okay, so what you do here is to, if you highlight the component and you do edit, flip, the component connection is flipped. So this is sometimes to organize your layout and make it visible and organized. So you can see here, as we described, the control of the ports, positions, and placement. Okay. And the flip feature. Okay, now component parameters. We're going to talk about component parameters. Now, if you go to any component in OptiSystem and you double click on the component, you have this pop-up window, which we call it component properties window. You can again size it. And in each parameter, as we saw, you have the parameter description, the value, default value. We usually use default values which are taken from published paper or from commercial product, and we put the default values here, and usually in a normal mode. Unless it is an example, we can put it in either sweep mode or script mode. Now each parameter, if you see here in the data sheet, if you double click on it, the description of the component, the parameter, which tab, the units, and default units, possible units, and the range. This is very important because if you use some parameter out of the range, you're gonna get error, and all of these parameters are described in here. Then under it, you're gonna see technical background where it describes the theory of the component in the component. So it describes how the functionality of the component. If you wanted to change any parameter, you just change it. Let's say, for example, the power, I need 10 dBm here. I put 10 dBm. Once you put OK, then the parameter will be active, so it's in the component. You can change again the parameter in sweep mode or script mode, as we show. Now, some parameters, as you can see here, they will be loaded from a file. So let's say, for example, if you look at the optical fiber component in here. Optical fiber component in here, let's make it larger. So you have user-defined reference wavelength. If you select it again, it means this is the reference wavelength, which means all the parameters in this component are specified at this wavelength, unless you have these parameters, specific parameter, let's say here attenuation, it's called from data type. Constant, it means this component has an attenuation of 0.2 dB per kilometer specified at 1550 for all wavelengths used at this fiber component. So if I have 1310, 1610, whatever, this is the attenuation. Attenuation would be 0.2 dB. Unless you load it from file, and if you load it from file, then would be this file, for example, has a wavelength dependent attenuation. And then this file, as we showed you earlier, You can have it stored in the libraries, and you can have different types of attenuation from different vendors, as we showed you in the beginning of the presentation. Okay. Now, if you go to dispersion parameter here, you have group velocity dispersion. You can enable it or disable it. If you enable it, you would be able to control the dispersion as a constant, which means, again, at 1550 nanometer, which is the wavelength, you have it in reference here, or you can have it from file. So you have dispersion dependence. So you have to load your file, and this is the dispersion versus wavelength and dispersion file. You have group delay. You can enter group delay versus wavelength. So you have the different options in this field. You can choose the field, the type of file you're gonna load. If you have, again, going back just for simplicity, constant, you have dispersion in picosecond per kilometer nanometer, and you have dispersion slope. You have, if you take the calculation in the frequency domain, you have access to the group velocity dispersion, which is beta 2, and then the beta 3, you can enter it here instead of the dispersion D and the slope here. Now, any component has a gray field, as you see here. It means this parameter is not used in the calculation. It's very important. So let's say, for example, I change this parameter to -30. This parameter is not 16.75. It will be calculated internally in the code relative to this number which you enter -30. The same scenario, if let's say, for example, I have here 10 picosecond, or let's say I want dispersion compensation fiber, let's say -50 picosecond per kilometer nanometer, it means the beta 2 group velocity dispersion is not -30. It's based on this number is going to be calculated. Once you press OK, all these parameters you enter is going to be basically saved in the component and used in the calculation. You have in this component polarization, PMD, polarization mode dispersion parameter. You can have deterministic or stochastic. You can set up the parameters. You have nonlinearity. Nonlinearity, all types of nonlinearity in optical fiber is considered in OptiSystem. So from cell phase modulation, cross phase modulation, Raman scattering, Brillouin scattering, Rayleigh scattering effect. Beside the nonlinearity, you have self-steepening. You have what else? Four-wave mixing. So all of these nonlinear effects is already implemented. Now, some components doesn't have all these parameters, and the most comprehensive component is the component in here, which is the bidirectional component. If you can see the bidirectional component here, if you click it, now it's connecting automatically. It's fine. You can just highlight it and delete the connection if you want, or you make it manually, whatever you wanted to do. But this component here, in terms of nonlinearity, it has all types of nonlinearity. Okay, so from cell phase modulation, cross phase modulation, Raman scattering, you have Brillouin, Rayleigh scattering, Brillouin scattering, self-steepening. Okay, so all of these nonlinear effects is already implemented in this component. Now, quickly, I just want to tell you for this component, any component which is called bidirectional, it means it allows the signal to transmit from west to east and from east to west. So this direction. Now, something which you need to put in mind, if this component, you don't use anything on this input port here, you must put a null onto it. So if you search here for the null, find component null, you're going to see optical null, electrical null, binary null, and memory null. So for all these types of components, you're going to have these components. You need to connect this port if you are not using signal from east to west. And output port, you can keep it empty. You don't need to use it if you don't want to. It doesn't affect the calculation. But if you don't have the null at an input port which is not used, then the calculation will not take place for that component, and then you might not have any output in your system. Okay, so in this kind of calculation, we're going to talk about it also later on. We're going to consider different cases in the simulation, because another thing which you need to understand is with bidirectional simulation is the signal, if you use it from west to east and then you're going to use the same signal from east to west, you have to do some kind of delay of that signal to allow the calculation in the component. Okay, but if you are using different signals from west to east and east to west, then you don't need a delay element in the bidirectional components. This is also something which usually users forget to implement in the project, and then they don't have outputs. Okay, move on. So we talked about the component properties, of how to set the component properties. And we can double click on the component, or we can go to the edit. You highlight the component as you see here. You highlight the component first, you go edit component properties, and then you can take a look at it. Or you double click on it. Another thing in the components, if you notice here, this here, let me talk about it quickly. Any component, if you right click on it, you're going to see the component property, which is this window, which you set up parameters, or you can see component results. So the component results, some components doesn't have results, and some components have results. So as we saw here, this component has results, which is laser full width at half maximum. So this is going to calculate inside the code and will be as an output for that component. Okay. Now some component, as we saw, doesn't have it. Now, there is something called component script, where you can have script the component and it adjust something in it, maybe done some calculation automatically. Then also component view. So you can look at the component view, where you have a viewing window here. You can look at the results in 2D graphs, 3D graphs. You can talk about it later on. Okay. And then the component help, which is the file, as we saw, and layout properties, bill of material, which is some fields inside the components. Okay. Now visualizers here, as we see, there is more features, something called disable and enable. We're going to talk about it also later on. Okay, move on. Let me get a sip of coffee. Now, how to access, as we described here, the component pop-up window. We talked about all of these levels, sweeping, scripting, data file loading, and units. So all of that, we talk about it. And we're going to move on. Now, yeah, loading of the component parameters, okay? So initially, if you remember, we said about these files, which we call them O.ofs file, which is optical fiber system files. And this are stored in the under C drive, program files, OptiSystem libraries, okay? And then these files are mainly for components like fibers, which is commercially available with parameters already plugged into the component. These files, you can load them into the component, optical fiber component, let's say, or you can create them. How to create them? After you set up the component, let's say you take any component in OptiSystem, you set up all these parameters, and then what you do here, you press on Save As. If you press on Save As of that component property, okay, then you're going to create a file, you're going to name it, and then it will be under OFS. Now this is file, you can save it anywhere. And then you can, if you want to use this component with the same parameters without any changing, you just go and load this file. Okay, so we can load this file into the component. So you first open the component property, then you do load, and then the load gonna take you into this position where you put the file in, you load it, and then you run, you press OK, then the component parameters which you saved would be loaded into the component here. You don't need to set it up again. Now, another way to save parameters of the components instead of going that route is what you can go to the component property here, and you change the name. You change the name here. The component in the OptiSystem is defined as optical fiber. You change the name here, give it let's say sub1, or we'll give it another name. It's your choice, but has to be different from this component. So OptiSystem wouldn't get confused with this component naming. So you can give a component name here, and then what you do after that, I'm going to show you here. What you go to that, it's say I take this component here, I rename it here laser, let's say laser 1 or whatever I want to call it, and say press OK. Once I press OK, I can go into the component library Docker here, and there is something called custom library. In this custom library, what you can do, if you drag this component in here, it's going to be saved. And whatever parameter you saved in this component will be saved in this component standard component. So you don't, if you want to use these parameters in this component in the future, what you go, you just build up your project, and then you go to the custom library, drag it, and use it. Then it means in that scenario, all the parameters you saved, you don't need to change them again. So this is two ways to keep the parameters which you saved for future usage. You can do it either through the save, as we say here, the save as under OFS format, optical fiber system format, or you can rename it and save it in the custom folder in there. Okay, so this is the two options. Now, in OptiSystem, as I mentioned to you, in the program files, OptiSoftware component, optical fiber, you can have all these fiber data files saved in there. Okay. Move on. So this is the custom library, as we saw. You must rename it, as we said, and then drag the component into the custom library, and then you are done. Okay, now building a basic project, we did, this is kind of process during the talk so far, but what you need to build a project, what you need to do, you need to set the first step is the global parameters, as we saw, the time window, the data rate, the symbol rate, if there is symbol rate, the number of bits per symbol, the number of samples per bit. This is crucial for any setup. Now, you have to pay attention into the number of bits per bits in the sequence, because in some applications, lower number of bits does not provide you the proper results. But for example, if you have, let's say, 64 QAM, if you use, let's say, 64 bits in the system, this 64 bits, if you use a QAM, which means you have 32 symbols, they are not going to be enough to display them into, let's say, 16 QAM on 16 positions. So you might have problems. So you need to increase the number. And also sometimes when you run a simulation for bit error rate calculation, all these things, you're going to see that with changing the number of bits in the sequence, will give you different results, and that's possible because as you know, the bits has to be on the average number of zeros are equal to number of one, first of all, and then this is your simulation has to have certain number of bits to be able to give you a reasonable result. So what you do sometimes is you need to increase the number of bits per sequence length until you get stable results. And the stable results means the variation will be minor, but you're going to see variation because of the randomness of the signal. Okay, so this is another thing which you need to pay attention to it. Okay, now once you choose the parameters in the global layout, then you choose the component, you select the component and the visualizers in the system, then you select the parameters of the components, and then you connect the components and visualizers. It depends on the way you connect them, automatically or manually, and then you do the calculation. Okay, and then after that you do the analysis and look at the results and the graphs and view them. Okay, so here's an example, simple example, where we have a light source modulator, a pseudo-random bit sequence generator, a pulse generator. So what we do, we carry the binary bits on the pulses, format not return to zero, and we modulate the light coming from the CW laser and then transmit it on through the optical fiber. We view the results here using optical spectrum analyzer, using an optical time domain visualizer. So you look at the pulses in the time domain, we look at the spectra of the light in the frequency domain. Then we detect the light using a pen detector. You have pen detector, you have APD detector in OptiSystem, and then you have a filter, different types of filter, all types of filters, and then you look at the bit error rate, and you characterize it. Now, this is an example taken in lesson 4, and then this example is actually, I did modify it a bit here. So if you look at this example, okay, I did modify it here just to show you the sweeping. I add up some components. This is lesson 5. Here, if you look at these two icons and the tab here, there is something called layout. So the layout, we have two layouts here in this project, this layout and this layout. You can have as many layouts as you want. You can delete layouts, you can duplicate layouts, and you can add a blank layout. So this is just flexibility to during the process of designing the project can be used. Now in this project here, I have did some sweeping as you saw, and I swept here in the EDFA again from 2 dB to 20 dB, and then look at the bit error rate. In this layout here, in this layout here, I swept the laser power from -10 dBm to 10 dBm. As you see here, if I have in the layout, if I have to sweep, if I want to sweep a parameter in the same number of iterations, then that's fine. I can do them per layout. But if I want to sweep different parameters, I can use something called nested loop. As you see here, this is called nested loop. So this is nested loop. It can allow me to sweep different parameters in different steps. So I can, for example, fix the power -10 and then sweep the, let's say, the fiber length between 10 kilometer to, let's say, 100 kilometer. And then I go 10 dBm and then so on. So I can do some kind of nesting. So this is called nesting loops. So I can have this kind of nesting feature. This is another addition in OptiSystem you can use. Now in this parameter here, as I did the calculation, if you look at the visualizer of the bit error rate here, it's too much, okay. Okay, so here bit error rate, as every sweep here, you see the Q factor in here displayed, the bit error rate. You can look at this is different, as we said, different power levels. If I look at the I, it's gonna close if I put power level lower and so on. Okay, so this is the effect. I can study the effect of power launched into this kind of fiber, 100 kilometers, and so on. Now, the detector, as you see here, the detector, I control the responsivity to be constant. Now in here, it can specify at wavelength, which is defined in the reference wavelength in the global parameter, or I can take it from a file. I have choose different type of detector, silicon, germanium, indium gas. So different types. I'm going to control the responsivity. I control the noise types here, dark current, AS beat noise, shot noise, and so on. I have many parameters to control. If I don't need something, I uncheck it and so on. Control the frequency responses of the detector. It's ideal, it's RC, and so on. So anything you need about this component, again, you can read about it in the data sheet. So all the information is there. If you want to load a file into the component, you have to follow the structure of the component, and you have to follow the units in the component. So if you want to load, for example, here the responsivity, you have to put in the first column the wavelength, as you see, in micrometer, and then you have to put the responsivity in ampere per watt. Okay, and then you load the file into the responsivity here. You load the file, say user defined, and then you load the file, and the file is going to go load it from there, but has to have certain format and so on. Okay. Now in visualizer, if you see a component, if we double click on any component, you get the property window right away. However, in visualizer, if you double click on it, you're going to get the view of it. Okay, so the view of it, and then how you can access the component property of the visualizer, you right-click on it. Right-click on it and go to component properties. And then here you can set up parameters, and you can control where you want to do the decision and so on. So different parameters, you can set them up in the component. Now, if you look at the component results in here, if you go component results, like for example, this component has lots of results in calculated, and then you can choose, let's say I need to choose the total power or signal power, noise power. I need to choose minimum bit error rate, log bit error rate. So whenever I click it, what's happened is going to be displayed under the component. Okay, so the results in green and the parameters in black, as you see here. If I want to see other parameters, I can just click them, and it's going to appear under the component. So this is some visualization. Now, in the system, you can monitor the signal anywhere in the system. Now, you can put a monitor there. Once you put a monitor there, if you see here, there is a rectangular box here, which is called a buffer. And this buffer it allows the data to be saved when it's calculated. Usually when you calculate components, you start with the components from the left to the right, and then there is an order. It's something called scheduler. And this scheduler works in any components have the at its input port data available, it's going to be calculated. Like this component doesn't have input port, so it will be calculated right away. This component will be calculated right away. However, this component can't be calculated until this component is calculated and generate results at this buffer. Now, at this buffer here, once the data is transferred or information or signal it's transferred to this next component, if the buffer here is not rectangular, as you see here, then it will be cleared. The data will no more be available. Like for example, fiber here, the data here is not available. So if I put a visualizer here right away after the calculation, I wouldn't see anything. I need to read the calculation. However, if I have a buffer here, I can put any visualizer at any time after calculation, and still I can see the type of signal which is generated there. So because the data is stored in the buffer. Now, is the fiber here, components, as you can see, I can put as many visualizer as I want. However, every time I put visualizer, I'm going to have a buffer, which means stored data in the memory. So more data in the memory, then it means the memory consumption would be higher, and then my calculation would be slower, and it might ends up, if you have lots of visualizers, you might have to crash the system because you don't have enough memory. So you have to be careful on that. In that scenario, what you can do, you can minimize disable the visualizer. When you disable the visualizer, as you see here, it will not be calculated, first of all. Now, the calculation here, disabling the visualizer will speed up the calculation, because once the calculation is finished and data is saved in the buffers, the last step is to calculate the visualizers. Each visualizer will be calculated separately from the data saved in the buffers. So if you disable it, then the calculation will be faster, because this step will be cancelled. You don't do the calculation there. However, the data is available. So what you do, if you like, after the calculation, you can go and enable the visualizer. Then the visualizer will be calculated, and then at that time you will have update the visualizer, and then you have the results available at the visualizer. Now, during the calculation, also you have something called disable monitors. So you disable monitors, it means all the monitors here will not save the data. So it will be clear, and that will also save the memory sometimes if you have a huge number of visualizer and calculation. Now, any tab here, any port here, I can look at the icon in here. This icon is called monitor tab. If I drag it in here and place it on this, it creates a buffer. So I can store the results in here. So, and if I wanted that to tab 2, I can delete it as well, and so on. Okay, so I can click here and I can eliminate the buffer. I can eliminate the buffer by clicking on it. Okay, so this is the way how to use the buffer concept and the data manipulation. And let's move on here. So we chose the basic components. We create this. Now we're going to talk about something called creation subsystem. Subsystems. It's a tool. Subsystems in OptiSystem. A tool where you can connect components together in a single component, just to save space and simplify. So the purpose of it is saving places, creating new components. You can have something called compound components. You can create it and you can save it in the custom library for future usage. I'm going to show you some examples already built in OptiSystem based on that. And okay, so let's see here. Take an example quickly. So what you do, for example, if I want to make system of these components together. What I need to do, I highlight these components together here. So these components are now selected, and go right-click here and say create subsystem. When say create subsystem, as you see, now all of these components becomes a single unit. You have an output port here for it. Okay, and now if you double-click on it, now I have this subsystem already there. Okay, so I can go layout property. I can name this subsystem, say, for example, transmitter here. Okay. Now I can put information on it, and then now I can go right-click here, say close subsystem. So close subsystem takes me here. Now if you look at this here layout here, so if I double-click again, the subsystem is open in here. This is main layout. I can go toggle between them. I can go to the main or to the subsystem. If I close subsystem, it's going to be disappearing from here, okay, and stays there. Now this subsystem, I can drag it and put it in the custom library if I wanted. Okay, so once you are in here, you can drag it and put it here. Then you have it ready. If you look in OptiSystem, in this subsystem library here, in the Docker, in the component library Docker, you have many components which we call the components we create for different applications. Here, let's say, for example, BSK transmitter, DBSK transmitter. So if you take this component in here and put it, you can see there is component is created many components. This is simplification for the user. Instead of every time he wants to use BSK, instead of building this block, what you need to do is just only you drag it and drop it in here. This is the advantage of using these subsystems when you create one of them. Okay, and then you can go here and do component properties, and then you can create something called the look of the icon. Here it's called default icon. You can go metafile, glassbox image as a bitmap or as EMF file, and that if you do it bitmap, the size of the box, as you see here, it's now clear, and the size of the box is will affect the memory at the end of the day. So if you do the property as an icon default, will takes less size of memory, and this is if your system complicated, you have to take care of that. Another thing is, you see here, you can with the glass configuration here, you can see that the connection of the components is clear, and this is sometimes useful because you need to know where this port is connected and to which component, if you like. If you have complicated systems, sometimes it's difficult to see it, but you can control the size of this system here and so on. Okay, so you can control it. It's the size of it. Okay, so move on here. Okay, so we look at these features of. Now we're going to talk about input ports, output ports to the subsystem. So input ports and output ports here. If you look at the icon in this side here, you're going to see this icon here to include the input port or output port. So this is called input port, and this is called output port here. So you can place them, and you can select them as well from the edit field of the toolbar, edit layout tool, draw input port, output port. You can see them, and then you create them in the subsystem. So you open the subsystem, and then you drag this here, and you click it, and then you can place it wherever you want in the layout. Okay. Okay. So to move on. Okay. So we are very far. Okay. Now we talked about the look of the box and the path. We can specify back. Okay. Okay, now looking into the fields, as we mentioned here, the gray, and it's the value of any field is gray, is relevant in the calculation. We talked about now. Okay, so we are going to talk about the project layout. So what's happened is you can save the project layout in a memory and in OptiSystem temp directory, and this directory is located under username, application data, local temp, OptiSystem. If you go to this location, you can look at copies of your project layout. So you can control that, and this is in case of, for example, how to access it. You go to tools, and then take options, and then you're gonna get this options pop-up window, and then you can say here, select whatever you want. Save workbook mode, save report page data, backup files, save files before. So you can choose whatever, and you can say here number of backup files. You can save up to 20, for example, consecutive files. So every time you run this project, you're going to have a backup file, another project, a backup file up to 20, and then they're going to be cleared. And then, but the maximum number of copies you're going to have of this project is about, it's 20 copies. Okay, so now we talked about the saving. This is the saving feature, and as I mentioned to you in 17.1, this is how it looks like right now. It's different from 17.0. You can check save the file, and then you can have the file location, and then you can save after each sweep, as I mentioned, or save after the sweep iteration. So after all this iteration, at the end of the calculation is being done. Okay, so you can choose which one of them, and then you can save parameters as well as you can save results. So in the 17.1 version, it's more flexible in the saving, and you can save it as a CSV file. Okay. Okay, so we talked about buffers and clear the buffers and the monitor tool. Okay, so we talked about this. We talked about the memory effect of the monitors and the visualizer enable disable, and disabling the monitor enable monitors. Okay. Now, the visualizers, we talked about visualizer tabs. We talked about optical, electrical, binary, and compare types. You can find them under default visualizer library, and then you can select the category, one of these categories, and then we have also the way to look at the visualizer component property. You don't double click on it, you just take right click and then component properties. Some components, as we said, we have component view, which we look at it as well. Now, in terms of visualization, you can have a visualizer here, and sometimes components have graphs in them. And the graphs, you can access them from project browser. So if you go to the project browser in here, so if you take an example here, so if you take the project browser, some components, like for example, have results. So you say here graphs, and if you see the graphs here, some graphs when there is no data, and then this kind of presentation, but this is sample signal. You can also expand this field, and you can have, let's say here we are talking about sample signal spectrum. So if you double click on it, you're gonna see the whole traces here, all sweeps. Now you can go to report page, and then you can drag this into the report page here, and it's gonna be saved in here. You can click on the figure here, and then you can have access export the data, export, control the access here, definitions, and so on. So you have lots of variety of control of the graph, which is generated here. You can create your own graph. So you can create your own graph as we see here. So I'm going to delete this, is just to, okay, so I have delay issues of the responses. But what's happened is I can go to this, as you see here under the report page, different visualization processes. You have 3D graph, grid. So if I press the grid, I can put here the grid. Then I have like a Excel sheet. I can drag results in here and put it in the Excel, so you can have it in columns, as you see here. I can take a graph, I can create a graph here, and then select the data on the x-axis, select the data on the y-axis from these things here. For example, I go to the parameters, I look at the power, it's swept here, so I take the power, let's say, on the x-axis here, I put the power, and then let's say I take, let's say, power, let's say, what we have here, let's say this spectrum, you have to say, for example, certain parameter, you can put it on here. You can drag it and put it on the y-axis. Then you can create an XY graph or 3D graph. Okay, so if I'm looking at, let's say, let me see the projects here, what we have. There's lots of changes I did. But you look at some parameters and you wanted to sketch it, for example. Let's say you wanted to have the laser, the resultless laser. You can drag it and put it in here. So this is the full width at half maximus constant all across all the power levels, which is correct basically. But this is the way how you do it. Okay, you can put the results on the y-axis or the x-axis and you create the graphs which you wanted to see. Okay, let's move on. Okay. So again, we can see graphs through the visualizer. We can see graphs in the project browser. You can create graphs in the report page. Okay, and then and you can look at the results which you wanted. Okay, we talked about this graphing and in the project browser. And now component view, as you see here, component view. Let's say if I take this project in here, and let's say I take on this fiber, and I look at component view, and then go to 2D. Now, if you expand here and then expand the lefts here, this is the things which you can sketch. And you can sketch them on the x-axis, left axis, or the left axis or right axis. You can choose, for example, attenuation. So this is attenuation versus wavelength for that type of fiber on the values on the left axis. But if, let's say, I want to sketch the dispersion on the right axis, I can here on the right axis dispersion versus wavelength. So this is the values which are stored in this component as we see as wavelength dependence variables, let's say. So this is how you can access it. Now, there is some components you cannot connect visualizers to them, and especially if you go to the here, or let me go back again. And if I go to some of these components, let's say in the sensors library, you have OTDR components. Now, the OTDR here don't have ports here, so you have to use the component view to look at the results, okay? So it can give you the results. But you can still set up all these parameters and design your setup. There is examples on it. Examples, you can go here, File. By the way, I forgot to tell you, File, Examples, and it takes you directly to the location of the example library. And then you'd say, for example, let's say I'm gonna go Sensors, and this is OTDR. This is the example here. I have 6 fiber pieces with 2 splices, 3 connectors, example. If you double click on it, it opens the example, you run it, and then you look at the, I'm not sure how long it's gonna take. Okay, so if you look here, component view, and then you look at the 2D component, and then you sketch, and this is what is happening in the OTDR. Okay, so the different links, and this is connection, and so on. Okay, so you have some components doesn't have ports to connect visualizers, but you have to use the component view to be able to see the results. Okay. Okay, so we are 15 minutes left, or I can go further as we discussed, Dr. Rashad, right? Okay.
Sir.
Can I still can go further with the presentation, right? Because I need maybe another 15 to 20 minutes.
Yes, sir. As per this thing, you can go, sir. Another 10-15 minutes.
Perfect. Thank you. Okay. So now continuing here on the report page, as we show the report page here, you can have all the different types of graphing and definitions. You can set up parameters in the report page and so on. Okay, you have lots of information in the user reference PDF file about how to use the setups here and change them. Okay, we look at these graphs, different types of graphs. I'm going to talk here fast about signal modulation of the system. We have different types of modulators. Some components can be like some lasers can be, or some components like VCSELs, lasers can be directly modulated, or some of them can be externally modulated using different types of modulators. Amplitude modulator, phase modulator, frequency modulator, electro-absorption modulator, Mach-Zehnder modulators with single ports, dual drivers, and all these things. There's different varieties. You find them, all these components, under the transmitter library, modulators, and optical. This is an example of directly modulated laser. So you have a pseudo-random bit sequence here, now returned to 0, and laser. And directly here we have a pulse generator. You can look at the pulses generated in time domain at 10 gigabit per second and 2.5 gigabit per second. Now you have external modulation, where you can use different types of modulators. We have, as I mentioned, different types of modulator. We can set up where is the modulation you wanted. Some modulators have analytical formulas. Some modulators have to have certain transfer function, which you can load your own transfer function, and then basically control where is the modulation you wanted on the max or minimum modulation, or in a negative quadrature, negative slope or positive slope of the modulation. Okay, so you can control where you want it, and also you can control, especially with, let's say, for example, a radio over fiber, a transmission. You can control a single sideband, double sideband, carrier suppress. All of that you can control it with the settings of the modulator and the driving circuitry. Okay, so this is the list of the modulators we have: analytical form, single drive. And so you have here, this is an optical port, this is optical port, and this is electrical port. And then you have dual drive, and you have absorption modulator, and so on. So analytical formula, this is the simplest form. You have single drive, as you see here, and so on. I just wanted quickly to list these things. And if you need more information, just maybe contact me, and then I'll give you more information on these different modulations. If you need information, you just double click on the component, and all this information is available for you to read. So you can set up the bias voltages, modulation voltages, and the modulating signal, and so on. This is another component which again can control based on the biasing, where is the modulation, and based on that again you can suppress the carrier, or have double sideband or single sideband, and so on, using filters with the addition of the filters. Okay. This is the absorption phase measured data. So which is stored in the component. This is the default file. You can load your own file in the component and create your transfer function of modulation. Okay. The format of the data, how to load it, is very important. So you need to know what is the fields, the columns, the units, as a kind of very important to emphasize on it when you load the data, and it shows the type of the data. And this here, quickly, I'm going to go through the optical fibers in OptiSystem. As we mentioned, different types of fibers. We have unidirectional or bidirectional. We have some fiber designed just only to study the nonlinearity in the fiber. So we eliminate the dispersion losses in fiber, just only nonlinearity. And this is, each type of fibers can support all nonlinear effects or some nonlinear effects. And there is another feature in optical fibers, is something called total field model or separated channel model. Okay, and this is something which can be explained in this graph here, where in the total field model, not all the component supports that, the fiber component supports that, but let's say, for example, optical fiber WDM component here supports that. So you can choose the components to be, as you see here, separated. So it's not a single kind of field signal, as you see here. So this is a kind of all field model, and all the signals will be considered as one single field, and here is separated field. You can set it up in this example I create for you. It's called total field example. Let's close this one here. And this example here, if you double click on the component and go use simulation field, and this is called CWM fiber component. You can find them again. Let's close this one first, and find them here in the fiber library. optical fiber library, and you have here optical fiber, CWM fiber, bidirectional fiber, lossy fiber, nonlinear fiber. This is other types of fiber use design. But if you double click on the fiber here, CWDM, and you go simulation field, you can see here mode, merge sample bands. Okay, now in here we select merge sample bands. Here we select also, I think, merge sample bands, and here we don't select merge sample bands, just to show you the effect. And if you calculate, as you see here, the fields are at the output of the fiber are separate. I did the calculation earlier, and here, as you can see, the fields are connected together. Here in this example, just to compare the effect of the combiner, power combiner, where you combine the different lasers, or you can use the max component. You can see the fields are limited here, different fields compared to each other. So this is something which is also, again, component design parameters will affect the results at the end of the day. So you have to be careful when you set up the parameter. But this is just to show you when you have all the samples are merged in a single band or separate bands if you select a separate mode of operation. Okay, so this is called total field variation. Now, okay, in terms of project calculation, we did calculation briefly to you guys, and just show you the way to project calculation. We have an option to calculate the whole project, which means if you have different layouts, and in each layout, let's say different iteration. So if you do calculate the whole project, it means it's going to calculate all layouts, all sweeps. Here you can calculate all sweeps in an active layout. So if you have, as I said, multi-layouts, you can, and you are open single layout, you can calculate the sweeps in that layout, active layout. Or you can calculate a single sweep in the active layout. Okay, and then this feature here is called calculate multi-thread all sweeps iteration in active layout. Okay, and this feature is very useful when you have large number of sweeps and also complicated systems. So in this kind of multi-threading, and if your computer supports multi-core, then the projects will be distributed in the multi-core, and then the process is going to be, every sweep is going to be created in a single layout, and these layouts will be distributed on the multi-core, and then this process will be faster in the calculation. So this is one way to calculate faster the project when you have a complicated project and multi-sweeps using the multi-thread feature if you have a multi-core computer. Now, another feature of calculation, which is also speed the calculation, is under the scheduler here. And the scheduler here, you can see, let me open the project. So here's the calculate multi-thread all sweeps. You can select it, and then it means this active layer will be into multi-core on your computer. Okay, and here the other ones. Now, if you go to scheduler here, you can have a single thread or multi-thread scheduler, which means this feature, if you select it here, okay, and then say okay, then the calculation would be multi-thread, which means the process of calculation is not going to be sequential. Okay, so it means this component, then this component, then this component, sorry, not visualizer, last thing is visualizer, then this component, and so on. When you calculate in the scheduler multi-thread, it means any component in the layout has input at its port ready to go. It can be calculated right away. Okay, and this is the same thing for multi-sweeps in the calculation. So this is kind of sweeping, make the calculation is faster as well. Okay, so this is the process of calculation, the multi-thread, the calculation. Now, okay, single indexing, okay, in the visualizer. So if you look at any visualizer in here, you double click on the visualizer, you have something called index, signal index. So signal index here is 0. Now, if you have, let's say, for example, delay element in the design, and you put a visualizer after it, then you need to put the signal index to 1. Here it doesn't change because we don't have delay element. But if you have a delay element, then would be, you have to click here to see the output after the delay element. In fiber lasers, when you design fiber lasers, because in fiber lasers, what you do is you run the simulation many times, let's say 100 times or so, to allow the build up of noise into locking of the laser. And then this is the way how to see the progress of the output is to go to the index here, and then it change the index in here, and then you can see all the progress of the results. Now, another thing here, as you can see in signal settings, you can see iteration here. It's one iteration, which means once you run the project, you're going to run it one time. If you put this, let's say 3, it means the project is going to be run 3 times. Now, if you want to look at the every time results, you're going to go through the index, signal indexing. So this is the purpose of signal indexing in here in the visualizers, depending on the loop number. So, for example, if you have circulating loop in the design, so if you want to look at every step of the loop and you put a visualizer in it, then you have to look at this the indexing to look at the loop every time. Depends on the number of loops in here. As you can see here, the visualizer inside the loop, and then you have to change the index to be able to see the progress every time the signal goes through the loop, because the signal comes here, it's going to go here, and then if the loop is, let's say, not equal 1, let's say you put it 10, means you run this is 10 times before the signal get out. So if you want to look at the output every time, then you use the signal indexing. When you use delay element, as I mentioned, when you use iteration in the global parameter, again, as I mentioned here. Fiber laser is very important, as I said again, is to use the signal indexing to be able to see the outputs. In this section here, quickly, I'm going to go through the optimization process in OptiSystem. OptiSystem allows the users to optimize using single optimization process or multi-optimization process. You can optimize gain flattening filter, you can optimize Monte Carlo optimization implementation. Okay, so this is different implementation. You can access them through the calculate here. So you go through optimization here, and then you start to set up. You choose the type of optimization, single parameter or whatever. If you do single parameter, you double click on it again here. What you need to do here, I'm gonna choose gain flattening filter optimization. Then I set parameters here, and then I go to the component, select parameters, and then I look at the visualizers and select the parameter which I need to set, and so on. So just show you quickly. Once I set up all these parameters, I do use the calculate. I have to check here run optimization, and then do calculation, and then I go to this tab here, optimization, so I can monitor the optimization process. So I'm going to show you example quickly, which is not this one. Okay, so I didn't open it. It looked like to me. Okay, let's take it in the display here. So this is the different situation. So you can have different types of optimization, as I mentioned. You can set up the parameters in the different windows, and in once you optimize a certain parameter, let's say, for example, I want to optimize the length of the fiber, of erbium doped fiber, or a bump wavelength, or a bump power, or something. You're going to look at the mode here. It's going to be changed into the optimized mode. And once the calculation is done and the result is finished, then the optimized parameter will be displayed here. So the optimized results will be displayed in the field beside the component which you optimize. Okay, so in here, I'm going to show you an example which we did recently for optimizing this block here, which is a hybrid optical amplifier using semiconductor amplifier, erbium doped amplifier, Raman amplifier. So in the optimization exercise, we did optimize the wavelength, the bump power of the Raman amplifier. The paper is published here, and this is the block diagram, and this is the process. We choose the optimization process to control the bump wavelength, the bump power to achieve certain gain target plus minus certain range, and which is related to the gain value, and then gain value and the gain flatness, which are the control parameters. Okay, this is like, again, going through the different parameters, settings, and this is, let's say here another example. I'm doing EDFA optimization. So EDFA, I'm choosing the power. Here I have double stage, and the bump, I can choose the bump power, the length, and so on. And then I choose the results. I need to control the gain of the amplifier. I have 48 wavelength in here, and I set for each wavelength the target gain and the tolerance. And then after I run the example under optimization, I see that this is the window for the target gain. And after the number of iterations, sometimes you don't reach the target within certain number of iterations for all these wavelengths, because you need to monitor all these wavelengths, okay? So to monitor all these wavelengths, you have to meet the target within all of these wavelengths. So sometimes the target is, let's see here, it's okay, but the other wavelengths is not reaching the target. So you have to be getting stable output for all the wavelengths within the gain range achieved, okay? So this is quickly done. I'm gonna move into another topic, which is called scripting. The OptiSystem offer scripting, VB scripting, Python scripting, and the scripting applications can be used for, as we saw initially, arithmetic expression. We script a wavelength, if you remember at the beginning, and then what we can do, we can script parameter in the global parameter as we saw. We can manipulate and control of the system in the calculation, layout, processing, and so on. So the scripting, if you go to this field here and you click on it and you do the script here, you can generate a script for the project. And this project, you can save it and send it as a text file. You can save it as a VB script or a Python script. And then you can run the Python script separately, and for example, or you can run the VB script. You can load the VB script into OptiSystem and then create the project from it. And then as well as you can manipulate parameters in the script. Okay, so there is, this is the script here. Once you run the script for the project, create the script for the project, you can load it, you can save it, you can run it, and so on. I'm gonna show you quickly here an example, which actually I didn't calculate, but let me see here. Okay, so if you go to the example here, in this example, it's called Reed-Solomon FIC calculation. This is an example in OptiSystem. In OptiSystem, if you double click on the example, this is the example using Reed-Solomon coding. If you go to script, this is the script. The script is reading the parameters from the file and saving the results into an Excel file, controls the parameters. So if I want to run this script, you can use this script, by the way, for any other projects. You can copy it and see the structure of the script, and can be used here. The purpose of this is to generate waterfall curves. As you can see in here, this is the results is going to look like. So it generates a waterfall curve under different conditions of signal to noise ratio, and then sketch the bit error rate versus EP signal to noise ratio. And if you see the project, is you can go to script, run the project. If you run it, it's gonna go through the process as you see here, and then they do the calculation and then start to update. It's a longer process. I'm gonna leave it running, but this is the way how to run a script. You can generate a script, as we mentioned, using the script generate and so on. Okay, so I'm gonna move on fast because not much time left. Okay, here you go. So this is the example. You can find this example in the example library of the system under advanced modulation, error coding techniques, Reed-Solomon. So this example, you can run it. Make sure that you have the path for the Excel file correctly saved in the script, and then you can run it and just try it. And then you can use again the file there into the other designs and other scripting for the data processing, post-processing, and data collection. Okay, now I'm gonna move quickly into the kind of last topic. Here is the co-simulation of the components. OptiSystem has a capability of working with other software like Python, like MATLAB, like C++, Scilab. And OptiSystem has a component called MATLAB component, and it's located into default external library, MATLAB library, as you can see here in the example. Okay, in here, the issue is because it's running right now, I have to stop it. Okay, so let's pause it, or actually I can open a new window here. Okay, so I can open a new window. And then if you go here under default, you can go external software tools. And external software tools, you have MATLAB now. You have MATLAB here. This is MATLAB component. If you drag it, you double click on the MATLAB component here. You can, as you can see, the most important part in the MATLAB component to be able to run a MATLAB code into OptiSystem. You can see you have input ports here. You have output ports in here. So let's see the component. Initially, you have single input port, single output port. You can expand the component as you see here. For any component, you can do that. If I need to increase the number of ports, I go input ports, increase it, let's say here 2, and then press OK. Then I create, as you see here, now press OK. It's going to be creating 2 ports, 1 output port. Now, if you go to input ports, this is what you need to do. You need to get each port, you need to define the signal type, optical, electrical, binary, and memory. And this has to be defined in your code, in the MATLAB code as well. Okay, and then so let's say first one is optical, second one, let's say electrical, and then I go to the output port, same name. I can control what is the port type. In here, I have to run the command, which is I have to write the name of the file which I need to run, or I can put the path of the file, which is a MATLAB file. Okay, and then I can define where to run it in the time domain or frequency domain. I can go into space as well, and the frequency domain, can control the wavelength, and so on. So once I write the MATLAB component code, I can load it again, I load it here through this file, and then once I do, I run it. So I'm having here an example where OptiSystem has the capability, by the way, to run a MATLAB code, or it can allow MATLAB to run OptiSystem. So if you want to run OptiSystem from MATLAB, you have to make sure that the project, OptiSystem project, doesn't have any sweep in it, and it has to be closed when you run it. Okay. However, if you run the MATLAB program into MATLAB component inside OptiSystem, you can load MATLAB during the calculation, keep it open, or you can just unselect it here, which means it's going to be called by OptiSystem and then closed after usage. Okay, so I'm having a couple of examples in here, which are in this example. Let's see here in MATLAB. So I have one, it's called binary switch. This is the MATLAB codes, and this is the OptiSystem component project. Okay, so I have to open them actually from another project layout, because, so let's say open them here from, because that project is running still. Okay, so this is the project. So this is the binary switch here. I can load the project. Okay, because it's I'm running the project right now. I should stop it actually. Let me see if I stop it. Yeah, so I'm gonna stop it because it's okay. Let's go to the presentation while this process is done. Okay. Okay, so the simulation here, it's we have the MATLAB, as I mentioned, the location of the component. We can do Python, C++, and then the functionality can be done. You have to be able to run MATLAB into with OptiSystem. You have to have MATLAB installed in your computer to be able to run it. And you have the advantage of running the codes in C++ is the software is faster, and it can be done in a faster way compared to MATLAB. So C++ language, when you execute commands, is much faster. This is an advantage sometimes you can counter when you run the project in C++. Okay, again, we talked about the MATLAB, how to be called from OptiSystem or from MATLAB, you can call it. And we talked about the settings here. Okay, and we talked about the port setting. And now this switch, I hope now we go to the example. So let's see here. Okay, so now save all of this. Okay, so let's see here. I'm gonna create. Okay, just trying to see. I have to get out of this window to be able to initiate here. Initiate, okay. And so let's take this one here. Okay, and then go to the presentation mode. Okay, and let's see here, OptiSystem. And let's run example. So this is the binary switch. And this is the binary switch as you defined here. This is the name of the file. We have input ports, one optical, one binary, output ports, two optical. Now, if I run the project in here, the project here takes now you're going to see that it's going to load calculating MATLAB component right now. It's going to load the MATLAB. It's actually on my other screen, it loaded. Let me see if I can run it here. I'll show you. Okay, it's done. Let me close this one. You can see here, finished the calculation. Now, if you double click on the signal here, initially I have CW light. In the time domain, it's continuous. In the frequency domain, I have pulse. As you can see here, the line width of the laser, I set it to 10 minus 12 megahertz, which is like 0 hertz. And at the output here, I'm doing some kind of filtering actually, and non-return to zero modulation here, and modulate the laser. As you can see here, the pseudo-random sequence. So I'm going to open the MATLAB code. It's actually here. So this is the binary code, the MATLAB code, just quickly to show you. This is an example in OptiSystem. You can call it, okay, so here I'm going to take it to the other screen. Okay. Okay, so this is the code which is used for binary signals. As you can see here, first is defining the input ports, output ports, and define the signal samples, parameter signal, noise bands. So you define the signal types. You kind of define the process for this loading the signal, and so all steps here are defined. As you can see, this is the output sample signal, the binary signal creation, low pass filtering. So it's going to call this function here low pass filter. And so on. Okay, so just to quickly go on this example, you can just run it. It's in OptiSystem example library, as you can see in here under you go file, examples, and software interworking, MATLAB simulation, and this is the examples. You can see them, all of them in here. Okay, so I'm gonna run just another example quickly, which is related to OptiSystem called by okay, here OptiSystem is called by MATLAB. So this is the program. So this is the MATLAB code. This MATLAB code here established the communication with OptiSystem, and then after that it called OptiSystem program and then plays with the gain of the fiber, amplifier, noise figure measure, and all these things. So the project, if you look at the project in OptiSystem, this is OptiSystem project. We have a CW laser, and we have an amplifier, and in the amplifier we control the length of the fiber and so on, and then we do the measurement. Now, all of this is being done by basically the MATLAB code. So what I'm going to do here, I'm going to go run the MATLAB code, which is you see here. If you run it, change folder, okay. So you run the code, and then the results would be generated in here. I'm going to take it to the other screen. So as you see here, the code call MATLAB, and then do the calculation and then simulation, and all these results are displayed in here, MATLAB. So this is the idea here is you can call OptiSystem from MATLAB, or you can call MATLAB from OptiSystem. So you have full flexibility on the process of dealing with the OptiSystem here. Okay, so quickly here, this is the example we did, and then this is the MATLAB code. This OptiSystem software, as I said, it must be closed, no simulation, no sweeping, and you're gonna run it from the MATLAB as we saw here quickly. Okay, just this is comparison between the results, just to show you. Here quickly, I'm gonna go through some examples. I just put them to show you some of the functionality which you can do here. You can generate, let's say, you can run 4-band signal modulating the VCSEL laser, and in multi-mode. This is an example of the system. Another examples here, VCSEL multi-mode example in spatially. You have, this is a webinar we did on supercontinuum generation and using designed photonic crystal fiber. We designed the photonic crystal fiber in a software called OptiMode. We took parameter from OptiMode, we put it in OptiSystem, and we simulate in OptiSystem, and we generate supercontinuum in these two papers published this work. And here, just to conclude the presentation, this is OptiWave's representative in India. It's HR universal system, and you can communicate with the owner. Here is named Harish Bandi, and his phone number. And thank you very much for listening. And if you have any question, I'm open for questions. Thank you very much.
Thank you, sir. Participants, if you have any queries, please unmute yourself and ask Dr. Ahmed, sir.
Hello.
Good evening, sir. Hello, good evening, sir.
Yes, hi, good evening.
Sir, can we use this tool for optical characterization of micro lenses and optical MEMS?
Is actually we are developing at this moment models for MEMS. So we don't have a component yet to represent MEMS, but we are in the process. Hopefully we are planning to introduce it in the next release, major release, which is like 18.0. Typically 18.0 comes in March, which is at OFC time frame. But the component already we have it, we tested it, it's working fine. Yes, eventually we're gonna include it into OptiSystem.
Okay, sir, thank you.
You're welcome.
Hello.
Yes, hi.
Hello, sir. Good evening.
Good evening to you.
Sir, do you have anything related to wavelength converters or related to some fault tolerance?
Yeah. So wavelength converter, we have a few examples, I guess, in wavelength converter. If you send me an email to my email here, which is at the screen right now, I can send you a link to this example.
Okay, sir. Thank you very much.
You can do the wavelength conversion in principle in nonlinear media, right? So in optical fiber or in semiconductor amplifiers or so on.
Fine,
so we
sir.
have, yeah, you're welcome.
Yes, sir. Thank you, sir. Thank you.
You are welcome. You are welcome.
Any other questions from participants? Sir, I think they don't have any question now at present. If they have anything, they will post it to your email ID, sir. Sir, I have a one
Perfect.
question here.
Sure.
You showed that the we can convert the project into a Python script or a VB script.
Right.
Can we do it in a reverse way? I write my the component in the Python scripting, and
Right.
can I find that in the Opti system for any
Yes, there is
use?
a there is a component similar to the one in MATLAB. There is another component called Python component
Yeah.
where you can load your code in Python into it and run it in OptiSystem. And there is a few examples as well in OptiSystem. You can look at them in the example library, which I mentioned to you in here. I can show it to you as actually, let's say here, library. If you go this OptiSystem, oh no, not here, but let's say again, go, it's easier here. I take it, okay, so you can take here a software interworking, and you can see here Python. You can search it actually here. Say Python, and you can go star.osd. Like there is a few examples definitely in the system and here, and you can find them in OptiSystem example library. I have to look at them. I think it's for some reason. Let me see here. Here, okay. Python script.
Okay.
Yeah.
Okay.
You have lots of examples in here. You can have the SDK information, tutorial, and so on. Yes, definitely.
Okay, sir. Thank you.
Yeah,
Sir,
okay.
one more thing. I was actually trying with the trial version of the OptiSystem, and I was experimenting for frequency response of a component. And
Okay.
when I was using this sweep component, sweep parameter.
Okay.
It was not changing the once if I have set for 10, in the next time if I would like to change it to 20 steps, it was not changing. Is it because it is a trial version, or in the license version we can do these changes, sir?
It's the trial version is supposed to function exactly like the release version, but I'm not sure honestly what's the issue. Could be if you like, you can send me the file as a zip file and can take a look at it.
Okay, sir.
For you.
Yes, sir.
No problem.
Okay. Sir, we'll conclude it.
Perfect. Thank you very much.
Yeah, thank you, sir. I'm very grateful for the time and effort you put in for this session, sir. And I'm look forward for collaboration and publishing some papers. And this session was very informative for all our faculty members, and they are very happy that they can include this in their curriculum and go ahead with enhancing the information which they normally convey it as only a theoretical concepts, but with the practical hands-on also they can do it. I once again thank you for your efforts, sir. And I'm very sorry that I've asked you to give the session early morning for you, but for us it is the end of the day. So
yeah, thank you. No problem. It's fine. I'm still awake. I have 2 cups of coffee since the morning, so I'm up. So
okay,
thank you very much.
Yes.
Have a good day, guys.
Sir, will you be able to share this PPT? Is it
Yeah,
possible?
so what I'm going to do, I'm going to make a link for it and I'll send an email to you and you can share it with all attendants.
Yes.
And or we can, if you can send us the emails, like we can send the link to them. So it depends on how you're going to do it. But for us, is I'll send you the link soon.
Yes, sir. Yes, no problem. So okay. Thank you, sir. We will sign off.
Yeah, perfect. Thank you very much.
Sir.
Have a good day, guys.
Good day, sir. Good day. Participants, we will sign off for the day, and tomorrow morning again by 9:15 we will rejoin for the
Excuse
NS2
me, sir.
session.
Sir, Prashant, sir, that link is not working.
I have checked, sir. I'll send it on the Telegram group. If it is not working, again I'll check it out and send you. Okay.
Okay, sir. Thank you.
Okay. Yeah. Thank you.
Bye bye.